Very good morning to all of you. So this is our third day, first session. In this session, we have talks. First talk is by, I think, Skype, no? Yeah. So each talk, as usual, is a total 40 minutes duration with 35 minutes presentation and 5 minutes discussions. So when it's 30 minutes, we'll give some signal so that you will know that 5 minutes will left over. So with this, let us start our first talk by Lucas Harris.
Okay. Good morning, everyone. Thank you for inviting me to your conference. I'm going to talk a little bit about S2S prediction efforts here at the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. Before I begin, I want to acknowledge my coworkers on the FE3 team, as well as the people who have inspired or contributed to this work that I'm about to present. Can everybody hear me okay?
Yeah.
Okay, great. So the GFDL has a couple of different models that we use for prediction modeling here. And you can see a couple of different ones here. We have a combination of both atmosphere models as well as a couple climate models that we use. The previous generation, the CMEP5 generation of models, are HIRAM and FLOR and HIFLOR, which are a little bit older. I'll show some results specifically from HIRAM, which is means a high resolution atmosphere model. We've also developed some new models for the CMIP6 generation, one called SHIELD, the System for High Resolution Prediction on Earth to Local Domains, as well as our couple climate model, SPEAR. And now we do have several different models here, which have different physics and different representations of the ocean and the land. They are all within the same modeling framework, the same flexible modeling system, and they all use the same FE3 dynamical core, the finite volume cubosphere dynamical core developed here at GFDL and implemented at many other locations. So one of the earlier applications that we use with HIRAM is that HIRAM is one of the first GCMs, global climate models, that had a good representation of interannual variability of tropical cyclones, particularly in the Atlantic Ocean. And that's for the development here of a version of HIRAM that we used for seasonal prediction of tropical cyclones, in which SST anomalies are frozen and kept constant throughout the course of the integration. And so in this case, HIRAM, this is a S2S type atmosphere model with the prescribed aerosols and six category GFDL microphysics. So this is somewhat simpler in terms of aerosols and other GFDL models with a more complicated cloud and precipitation physics. And there's two versions that we show here. There's the 2012 version that used a hydrostatic dynamics and 32 vertical levels with the older single plume convection. And a 2015 version with the non-hydrostatic dynamics, 63 vertical levels, and the double plume convection scheme that we'll revisit a few times here. And both these models are a little bit different, but they do show a good predictive skill in hindcast mode of the interannual variability of tropical cyclones in the North Atlantic Ocean. And in particular, we found that during the decade of the 2000s that there was this remarkable interannual predictive skill of Atlantic hurricanes, with a correlation coefficients of 0.94 and 0.96 in both of these models. So this is the starting point of the seasonal and then into S2S predictability in this class of models. So then we can move a little bit. We can move a little bit closer into the shorter time scale. So we were referring to this as a beyond weather time scale predictions of a couple of major events of Hurricane Sandy and Typhoon Haiyan back in 2011, 2012. And one of the interesting things that was found, this is by Baocheng Zhang in our research group, is that he ran a large ensemble of a 50-kilometer HIRAM, which was coupled to a 1 degree ocean, but also used the double plume convection scheme. And we actually found that both these storms were predictable up to 11 days in advance of the actual genesis of the events. And predicting the track itself of these events was difficult, particularly for Sandy, which is difficult to predict even after genesis. But we were able to predict the genesis quite well in this model. And it turns out that a big part of this is being able to have a good predictability of the tropical wave modes, particularly the westward propagating modes and the Matt and Julian oscillations, something that I'll come to again repeatedly in this talk. And so you can extend that beyond just these two storms. This is done of a large set of hindcasts, again using that coupled HIRAM. And what we found is that up to 30% of tropical cyclones the genesis could be skillfully predicted within 1 to 2 weeks of lead time of the actual event. And in particular, in the Western Pacific, we found that there's actually quite a good ability to predict the genesis of storms, even up to 14 days in advance. And now, while prediction of 30% may not look too good, this is actually quite an advance over existing systems. Predictability of genesis events at long ranges is quite a difficult problem. Deterministic predictability in that case, I should point out. This shows that there is some promise that at least some events can be predicted within weeks 1 and 2, particularly in some regions of the tropical basins that are some of the most active regions. And this kind of gets into the idea of what exactly it is that allows us to do this sort of predictability. I alluded to the Madden-Julian oscillation already. And so we're taking a look once again at the same coupled HIRAM with the double plume convection scheme. And the ensemble predictions over a large set of hindcasts actually found that there is useful skill up to 27 days in this prediction model, which is better than all of the operational models of the time, with the exception, of course, the European centers model. So, but this is already an advance over what is already available. One interesting thing that was found from the study, actually, that it may not, in retrospect, may be somewhat obvious, but is actually a useful result, is that the potential predictability of initially strong events is quite a bit more than initially weak events. And this suggests two things. One of which is that when you do have an MJO already, that we can get enhanced predictability of the Madden-Julian oscillation, perhaps it was related teleconnections. But it does perhaps ask the question of, when you don't have a Madden-Julian oscillation, or if you have a weak MJO, what hope do you have of S2S predictability? And that's a question I don't have the answer to right now. But at the very least, it does say that there is perhaps some opportunistic nature that could be taken advantage of to extend our prediction skill on S2S timescales. And now, so one thing that we do hear quite a bit is that the Madden-Julian oscillation is not well represented in global models, and as we have found, in that the CMET5 class of models, both at GFDL and global, and at the other worldwide modeling centers, that most models did a very poor job of simulating the MJO with any good fidelity in their climate models. So some analysis was done in our AM4 model. This is the atmosphere of both CM4 and SPEAR, our CMEP6 class coupled climate models. And it was found that if you have an uncoupled atmosphere with specified SSTs, that the propagation of the MJO was indeed quite poor. However, when you couple this model, this relatively low resolution 100-kilometer grid cell model, that if you couple to an ocean, three-dimensional, in this case, MOM5 ocean, that you did get actually a good propagation characteristics of the MJO that matched the observations quite well. And we can express two reasons for this. One is that as you see here, that coupling has something to do with improving the quality of the Madden-Julian oscillation, but also that the UW double plume scheme, which is introduced in AM4 and is also used in a number of presentations or a number of different models I've already shown you, a number of different results, that it does permit to have a better representation of the MJO than the earlier convection schemes, particularly the RAS scheme that we used in the previous generation coupled models in CMEP6 and CMEP5 and CMEP3. So it's those two features, the convection scheme and the coupling to an ocean, that really are really the key ingredients to getting a better representation of the Madden-Julian oscillation, at least in terms of the climate sense, even at relatively coarse resolutions. So then we can go on to say, okay, well, we've got a decent MJO. What are the impacts of that? And again, I alluded to that earlier with the beyond weather timescale prediction. And this makes it a little bit more concrete. This is a study done with a 25-kilometer global non-hydrostatic HIRAM, the 2016 version I mentioned earlier. And this is with specified SSTs, but it still has enough of the effect of the MJO in it that we can begin to look, that we can start to look at the impacts of the MJO, and in particular the genesis of tropical cyclones to the MJO. And you can clearly see here that we are doing that high RAM in the two phases or the two components of the MJO here, one of which we have enhanced activity over the Caribbean, the Gulf of Mexico, and the Eastern Pacific areas of the areas of responsibility for the National Hurricane Center in the United States, that we do see enhanced tropical cyclone activity in this model, and that we see it in phases 4 and 5, when you have effectively suppressed MJO phase, that we see decreased activity in these regions as well. And this is an important result because, to the best of our knowledge, no model has been able to represent this characteristic within in these sort of climate type integrations. It's the first time that we've directly shown this sort of enhancement and suppression of tropical cyclone genesis activity around North America. And you can see we also have this sort of a relationship in the Indian Ocean and in the Western Pacific. Though it's my understanding of this relationship is has been a bit easier to pick up. Unfortunately, I'm not an expert of these domains, so somebody can correct me if I'm wrong. And we can go, so now that we have the MJO waveguides, we can start to use that to say, okay, how can we predict subseasonal hurricane activity with a focus in this case on the North Atlantic? And so what we've done here is we've taken two versions of high RAM. One is where we take our global 25-kilometer domain. This is the non-hydrostatic high RAM again. But we've also taken advantage of the variable resolution capabilities in FV3. We have a couple of different ways of resolving locally over a domain. In this case, we're using our two-way nested grid capability to nest down to 8 kilometers over the North Atlantic Ocean. And what we do is what we find is that the 8-kilometer nest gives us a substantially better predictions of anomalous hurricane activities, particularly for accumulated cyclonic kinetic energy measurement, particularly for hurricanes, and especially for major hurricanes. In the 8-kilometer domain, it's substantially better than using the 25-kilometer uniform model. And there's two ingredients to what's going on here. So first of all, we take a look at the shear anomalies over the main development region in the North Atlantic. And we find that both the 25-kilometer model and the 8-kilometer nest, they have a good representation. In fact, they have a good prediction of the monthly anomalies of shear over this region compared to the observations. In fact, the skill of the 8-kilometer nest is actually slightly less than of the globally uniform domain, but it does say that the nested grid is able to maintain the large-scale skill that the uniform domain has. So that's one part towards being able to capture a good tropical cyclone, especially hurricane activity over this region. The next question is, well, what exactly about the 8-kilometer nest is giving us better results? And the results it's actually kind of obvious in retrospect, but we'll dig a little bit into this. So you see here in the lower left-hand panel, this is the representation of the maximum surface winds. These are our 30-day predictions. Again, these are month-long predictions, initialized every month during hurricane season for 15 years. You can see that the globally uniform 25-kilometer simulation does not capture the small radii mean winds that are typically associated with the more intense tropical cyclones. And this is perhaps expected. With the 25-kilometer model, it would be difficult to simulate a eye wall that's much smaller than about 50 kilometers. That you do see for more intense wind speeds. However, if you take a look at an 8-kilometer domain, we're actually able to capture this relationship between the radii maximum winds and the maximum surface winds quite well. We're able to represent the small scale features in the most intense tropical cyclones. And that can lead to better ability to simulate, and perhaps better predictions of major hurricanes in particular. But we don't necessarily need to stop there. We also have this result that we find that the 25-kilometer domain has very few examples. It very rarely is able to undergo rapid intensification, in which the maximum intensity of tropical cyclone increases by more than 15 meters per second in 24 hours. The 25-kilometer domain very rarely does that. However, the 8-kilometer nest allows us to correctly match the observed frequencies, the observed PDFs of rapid intensification rates. So this strongly suggests that when we're able to get better representation of these small intense cyclones, that we're not only able to better predict them, which you can't get good predictions unless you can represent them, but further, this perhaps opens the door to the idea that we might possibly be able to have seasonal predictions of rapidly intensification. You can get a good idea. Well, what is your threat of rapidly intensifying intense cyclones over a 30-day period? Okay. So that's the results of our CMIT 5 class models. Now I'll introduce our CMIT 6 class models. In particular, I want to focus on SHIELD, which is the model that we used to call FEGFS, which is the prototype to the currently operational GFS. And then from there, we extended to a whole class of models for a variety of different prediction purposes on weather time scales. We call this our implementation of the unified forecast system, just one part of the NOAA's complete unified forecast system package. The particulars of this particular model, this is the FE3 dynamical core, coupled to a heavily modified version of GFS physics. The particulars will be on the next slide, and the NOAA land surface model. And this is part of the unified Earth modeling system that we're developing here at GFDL, which we have a whole class of models, including our coupled climate models, CM4, ESM4, and the prediction model SPHERE, all within the same modeling system, using the same dynamical core and also often the same components like similar land models and similar ocean models when available. This model gives us a couple of different capabilities. One is that this modeling system allows us to demonstrate the basic capability of the components in the model, dynamical core, physics, land model, and so on, as well as giving us the ability to demonstrate new science capabilities in our dynamical core and in the physics that we're developing. It allows us to inform. Being able to use a prediction model is a very strong test of the quality of your model, and it really helps us to inform what things are going wrong on our model and gives us pointers to what further things we want to do to develop the model. And finally, this advances in SHIELD can be seamlessly transitioned to other UFS implementations, such as the operational GFS or the experimental HASS model, Hurricane Analysis and Forecast System, or also into other FE3-based models, the other atmosphere models at GFDL, or other FE3-based models within NASA in the planned CESM FE3 in Taiwan and in China and so on, which ties into the whole philosophy that's kind of built, that FE3 has been built on, is that a lot of different people are developing different models for different applications, but they can all build off of one adaptable dynamical core that can be put into different frameworks, or just can be plugged out into different frameworks. So there's some benefit to being able to build all around one dynamical core, but ultimately control of the modeling system depends on what you want to use that model for. So here are the particulars of the SHIELD model. The microphysics, it's built off of the GFS's physics. We've made some further improvements since then. We're using the GFDL microphysics. It's a 6-category cloud and precipitation physics scheme with a lot of nice numerical features. And in particular, the most recent version uses the inline physics, in which you can run the entire microphysics inline within the dynamical core, allowing us to run the microphysics at a faster time step. This is useful particularly for a convective scale simulation than the rest of the physics. We're using the YSU PDL scheme in these examples with a number of different modifications that are useful for global models, in particular models that have relatively small vertical grid spacings and long physics time steps. So these are modifications that are made by people in our group. We are using the NCEP scale-aware SAS convection scheme, which is helpful for our variable resolution simulations, as well as a mixed layer ocean that's implemented by Haocheng Zhang. And this uses a relatively long time scale to restore to SSTs, and it also has a prognostic mixed layer depth as well as the ability to cool from rainfall. So here's one more version of SHIELD here. This is called SSHIELD, which is our S2S prediction model. This is the global 25-kilometer resolution model. This is all the SHIELD models are run as non-hydrostatic models. And here's one example of the MJO propagation in a 10-year climate simulation using specified SSTs and the mixed layer ocean. So the mixed layer is relaxed to climatological SSTs. And in this case, we find that we actually are able to replicate the Madden-Julian oscillations propagation quite well in this model, even at a relatively coarse resolution of 25 kilometers again. And we don't capture all the amplitude, but we do see that we get the correct propagation through the maritime continent. So this is a very good beginning for developing S2S type models, and in particular taking a look at their effects in this. One thing that we are interested in one thing that is often quoted as being necessary for a good MJO is having a good diurnal cycle. Indeed, what we found is that in SHIELD, we have an excellent diurnal cycle, even this relatively coarse 25-kilometer resolution. And in particular, we have a much better diurnal cycle than the CMIP 5 class models, particularly over land, which have trouble both the amplitude and the phase of the diurnal cycle. In S-SHIELD's diurnal cycle has the right phase and about the right amplitude. And this is actually a benefit of the SAS convection scheme, and I'm going to come back to this point a little bit later when discussing the results of the maritime continent. So from there, we have a good MJO in this simulation. We want to go beyond just having a good mean state MJO and getting good variability, but then go into being able to predict the Madden-Julian oscillation with good fidelity. So to that end, we take a look at this model called T-SHIELD. This is the variable resolution version of SHIELD. And this is based on an idea by Tim Palmer when he said that if you want to improve S2S prediction, particularly over the continental United States, which is where the people who are paying the bills are paying my bills are located, what you could do, one of the things you could do is just put a nested grid over the maritime continent and perhaps get a better representation of the MJO. So that's the idea here. We take a global 16-kilometer domain and we put a factor of 4 nest into it. It goes down to 4 kilometers over the maritime continent and surrounding waters. And so we've integrated this using a variety of, we initialize from GFS analyses, and we integrate to 40-day forecasts. This is again using mixed layer ocean and the SHIELD/GFS physics. And we're focusing particularly in the dynamo period, but we are looking at some other periods, particularly in 2015, 2016. And one thing I do want to point out is that this is using the GFS's vertical level setup. This is 63 vertical levels, with the first mid-level about 15 meters above ground, above the surface. So here's a set of hindcasts, and in particular, for this set of hindcasts, we're focusing on the 34 cases during this period. We're initialized each day that the MJO is in phases 2 or 3, and this covers a period where the MJO has already formed, but has not yet moved over into the region that's covered by the nested grid. So we want to see what exactly the nested grid is doing to improve the simulation of in particular, this prediction skill of the MJO. And what we see this actually quite nice result that we get good skill out to 24 days in the uniform resolution, and then extend beyond that with the nest to 26 days. We have usable skill out even to 39 days for this particular set of hindcasts. That's almost to the end of the simulation. And that's 11 days longer than just the uniform resolution run. And this suggests a couple of things. One of the big ones is that the MJOs, that at once you get to day 40, the MJO should have already moved off of in the case in which it's propagating beyond the nested grid region, beyond the maritime continent. It should have propagated off the nested grid by this time. So this suggests that we're improving this predictive skill of the MJO even after it's moved off from the nested grid. This is not merely a local improvement. This actually improves the oscillation once it moves off of this high resolution region. And we have done the tests we have done a number of different hindcasts at different times as well, periods in which the MJOs are other phases. And we do find less skill for both these runs. So we get about 27 days of good skill with the nested grid for the aggregate cases. But we still see the nested grid does allow you to improve your skill even in the other phases of the MJO. So here's an example of a couple of characteristic forecasts. This is one a little later in the season. This is initialized on the 25th of February, 2012, and this is when you had an MJO event in phase 2 here that's beginning to propagate into through the Indian Ocean. You can see that actually in our 16-kilometer uniform run, we get too strong of an MJO that propagates too quickly. So what we do is we apply the nested grid simulation, and it actually gets the amplitude of the MJO quite a bit better than the uniform resolution run, and it still propagates a little bit too quickly, and we see some weird behavior later on in the simulation. But on the whole, this is indeed a better simulation, better prediction than the MJO. It doesn't overpredict it as much, particularly in the critical period where it's going over the maritime continent. And we can ask how robust is this particular result, and we did a number of different forecasts. We did, remember, one each day, and we did a couple. We take a look at a couple of cases, a few before and a few after the 24th and 25th. And what we found in all these cases is that the nested grid is that while both models do a good job at simulating the MJO during this period, particularly in the first couple of weeks after initialization, that we do find that on the whole, the nested grid tends to do better. It does less of an over prediction of the MJO's amplitude. You can see that in all these cases that very long, going towards the last 10 days of this period, that the predictive skill does drop off a bit. It does some weird things, but this does open the door towards, this does imply that we do have some robustness to the predictability of this event. Now we can move to a more challenging case. This is the case of, and this is initialized the 24th of November, a little earlier in the season. And this is a particular MJO that formed, started propagating to the maritime continent, and did indeed get stuck. In reality, did get stuck there. Not all MJOs do propagate through the maritime continent. But you do see that in this case, the nested grid again is able to do less of over-prediction. And there is some evidence that, perhaps by chance in this case, that the MJO, that the nested grid simulation is being able to better simulate the beginning of the next MJO event. Which then brings me to my next topic about initiation. And this has less to do directly with the variable resolution, but it is an interesting question. What can we do to predict the MJO when there is no MJO yet? And how predictable is the appearance of a new Mann-Julian oscillation event? So here's a couple of examples. This is a little earlier in the season. We do find that models initialized on the 3rd of November of 2011. And they aren't quite able to predict the initiation of the MJO in this case. Once the old one disappears and the new one begins to form in the Indian Ocean, the Western Indian Ocean. We move a day later, and the models do perhaps pick up some signal of the MJO forming in the late part of the period. And then it's on the 5th, however, that we are able to begin to show that the models are able to pick up on the MJO's formation about 2 to 3 weeks within the simulation. And actually, in this case, do have good predictive skill out to 40 days towards the end of the simulation when the MJO begins to impinge upon the maritime continent. So, so I'm not suggesting that there's something magic going on the 5th that allows the model to be able to predict the MJO, but it does predict that it does begin to suggest that there may be some predictability of initiation that, however, may need to be thought of as may need to be predicted probabilistically rather than deterministically. And then I want to come back to the topic of the diurnal cycle over the maritime continent. And we analyzed what the precipitation was over the maritime continent region in both of these models. And what we found is that the 4-kilometer nest does an excellent job with the diurnal cycle. In particular, it gets the right phase in the amplitude. Maybe it's a little bit too weak in the afternoon and evening in this case. But we are able to capture the amplitude of the MJO very well over the maritime continent as well as the phase. The 16-kilometer uniform domain, it has the right phase. It's maybe a little bit weaker at simulating this maritime continent. In this case, this is just over land. But this does provide good circumstantial evidence. This is maybe one of the things that is allowing us to get a decent quality MJO, and in particular, maybe perhaps why we're getting better skill in the 4-kilometer domain when we put in the 4-kilometer nest. And 2 points come to mind over this right here. One of which is that one thing that we've noticed is that weather prediction models in particular are designed to get very good diurnal cycles. And a big part of this is because predictive skill, which tends to look at the high and low temperatures, what time of day your high and low temperatures come, and what your 6-hour precipitation looks like. If you have a messed up diurnal cycle, you wouldn't get very good skill in these quantities, and your weather prediction model would not be particularly good. It may point to this, there's different priorities between weather and climate models. Weather models we found when you run out to long periods tend to not get as good mean states as most climate models, but they do seem to pick up variability to a very good degree. The other point that I want to make regards the SAS convection scheme, which plays a big role in getting a good diurnal cycle, particularly coarser resolutions. And I remember a while back I was on a teleconference with somebody who said that everybody knows the SAS convection scheme sucks. And I wanted to point this out by saying, well, no, the SAS scheme doesn't suck. It just depends on what you're using the SAS scheme for in this case. I think what people are looking at is more from a mean state perspective rather than the variability, especially where the variability is important for good short-term predictions. Okay, I'll be wrapping up here soon. So one thing I want to mention, that's a bit of an advertisement for us, is S2S modeling using a global cloud resolving model, or GCRM. And this is something that GFDL has been collaborating with NASA Goddard for over a decade using FP3-based GCRMs. But now we've gotten to the point where computers are large enough where we start to run long enough simulations, start to pick up some of the general circulation features, which has been done as part of the Diamond project, in which 40-day simulations were done by centers around the world and submitted to a common database. And we're developing a model called XShield, or Experimental Shield, which is a global cloud resolving model to be able to explore the capabilities of GCRMs, that we can use them for model development. They can provide us a artificial, like a nature run, that we can then use to calibrate our convective schemes and model parameterizations. They give us something to understand processes in the models that we couldn't do before with either high resolution limited area models or coarse resolution global models. And then just as a prototype of a future prediction model, that as models get higher and higher resolution, that hopefully this will be able to be the predictive model of the future. That may be a long ways down the road, but it might be sooner than people think. Now, of course, global cloud resolving models are expensive. They're 200 times, the one that we have, even though SHIELD is a fairly efficient model, the global cloud resolving model is 200 times more expensive than our 25-kilometer model. However, while there's a lot that could be gained from a global cloud resolving model, it may not necessarily be necessary for all prediction purposes. And in particular, there's a sort of belief that maybe you need a global cloud resolving model to get a good MJO and other convective features. But we found that with less expensive models, you can actually get a very good representation, particularly the MJO. Most notably, the 4-kilometer nested run in T-Shield. This is only about 12 times, this is less than 12 times more expensive than the uniform 25-kilometer models used for S2S. Still a little bit on the expensive side, but within reach, at least for research purposes. And it's only about 4 times more expensive than uniform resolution domain. So I just want to sum up here about our perspective on the MJO. And this kind of asks this question that, do you need a global cloud resolving model for a good Madden-Julian oscillation? No, but as you go to higher resolutions, we do get better predictive skill, particularly when we use this nested grid. And in particular, we've seen the effects that when you go beyond the nested grid, you can still, that even when the MJO propagates beyond the nested grid over the maritime continent, it can still give you a better predictor than if you have just a coarser resolution, uniform resolution domain. But what we have found is that there's the 2 main ingredients. One is that interactive ocean, whether it's a mixed layer ocean or a fully dynamic ocean, really improves the resolution, really improves the propagation of the Madden-Julian oscillation. This is true even at relatively coarse resolutions. I showed you 100-kilometer resolution AM4. It turns out even at 220-kilometer atmosphere resolution, that having a low-cost ocean can improve the Madden-Julian oscillation substantially. And furthermore, having a good convective scheme, whether that UW convective scheme or the UW double plume or the SAS convection scheme we're using in SHIELD, is a bit key player in giving you a good MJO. And in particular, we found that having a good diurnal cycle, partially the gift of the SAS, does really help us improve that propagation. And one thing that we also looked into but didn't show is that we tried a few different PBL schemes and these nested T-Shield simulations. What we did find is that the skill of propagation is not particularly sensitive to the choice of the PBL schemes. Surface interactions are important for the ocean interaction, but in terms of the atmospheric mixed layer, it may not be quite so important. And that's all I have, so I'd love to take your questions now. Thank you.
So 1 or 2 questions or comments?
Very interesting talk, thank you. So I've been involved with Murat Karatnadov in running global sort of aquaplanet models without any convection scheme at 20 kilometers, which seems impossible, but we have reasonable MJO. So I have actually two very closely related questions. One is, how much in your sort of standard configuration at 16 kilometers, so how much of the precipitation that's associated with the MJO is produced by SAS relative to explicit condensation? And then have you tried, in the SHIELD model, have you tried other convection schemes in that particular model? Yeah.
Okay, thank you. So we haven't specifically looked at the partitioning between the convective and the resolved scale precipitation. It's actually something that we perhaps should look at, and that's a very good suggestion. We haven't tried other convection schemes in this sort of model. I do know there's a team at the Earth System Research Laboratory that has looked into replacing SAS with the European Center's TIDKey convection scheme, and they did find a improvement of the MJO and the tropical and some of the tropical convective modes. We do find that we get a good representation of tropical convection in S-SHIELD or 25-kilometer model. But we do have a slightly different configuration than what they're running. Particularly, we have that mixed layer ocean. We have the different PBL schemes. They're using the EDMS scheme and a specified SST. But thank you.
Thank you. So is there any remote?
Yeah, hi, it's Roberto Buizza. In your early presentation, you called predictions, I think what you, some integration that you did with prescribed SST, if I remember correctly. When you moved to discuss SHIELD results, and there it was not clear to me whether again you were using prescribed SSTs or whether you had actually an initialized run where the SST would be evolved by your dynamical ocean. So can you please clarify exactly what you did with the SST in your integration earlier part and later part of your talk?
Okay, so that's actually a good point, and it is a little confusing because we have a couple of different models here. So first of all, so the result here for HIRAM, the 25-kilometer HIRAM models, those are using specified SSTs, but they're using frozen anomalies. So we take the anomaly at the beginning of the integration, and we keep that anomaly, but we allow it to ride on top of the climatology over that time period. So it is indeed a prediction. We're not using the actual SSTs from further out in the forecast period. We're using just the anomalies at the initial time. For SHIELD, that has a mixed layer ocean, but again, we start with the initialized SSTs, and then we relax that to climatology with a 15-day time scale, modulo the dynamics of the mixed layer ocean. The coarser resolution the coarser resolution HIRAM, that again uses an initialized 1 degree ocean, the same one that's used in FLOR. That one used a nudging of the atmosphere and ocean prior to the initialization, but once again, it is an actual forecast. It's not using information from after the initialization time.
Okay,
But
thank you.
Thank you. So now actually, okay. Yeah.
Peter Bechtold. As you said, it's astonishing that the MGO is sensitive to the resolution in your SHIELD results. Because, so my question is, what did you use as initial conditions? Second, you showed only winter and 34 cases. Or if you run typically 20 years, 20 winters or 20 full years, would the results be the same? And the third question is, if it's true, then is it, as we just discussed, a bit the ocean coupling, because you can get drifts and wrong wind response, or is it, as you mentioned, better land and diurnal cycle?
Okay, that's a very good question. Thank you. So to answer your questions in order, so in SHIELD we always initialize from GFS analyses. We have the ability to initialize from the European Center analyses, although I haven't tried that for these particular simulations. Second of all, I mean, yeah, we have focused mostly on the winter during the time period where the MJO is most active in this case, which is admittedly it's a little bit unfair for the take a look at the qualities of the MJO just this time period. For the coarser resolution SHIELD, this does have a full annual cycle in it. It's not really predictions, but This is more of a climate type integration, but it does take a look at both winter and summer. The coupled HIRAM, that did use a large set of hindcasts that were year round in that case. The propagation results for those other models, the only one that we haven't done in anything but the winter is the high resolution SHIELD simulations. The other simulations, S-SHIELD and HIRAM, those were more either year round or they focused on the hurricane season, the summer in the northern hemisphere.
Okay, thank you very much, Dr. Lucas. Very interesting talk, and it has given a lot of discussions. So
thank you.
Then our next, I think already time is over. Yeah, we have 3 questions already. Yeah. So next one will allow remote. Okay. So our next presentation is by Dr. Graham Stephens from JPL. It is his second talk in these 3 days.
Does this work? No? Yes, does? Yes? Very good. Oh, this is good. That's even better. Yes. Okay, so I guess this talk extends the scale yet again from the previous talk towards climate, but very much reaches back to weather. So it's kind of a connection and a bridge between weather and climate. And I'm going to provide you some thoughts on cloud convection feedbacks. The figure on the left sort of is a cartoon of different ways it is thought that convection might change in a warming world, such as, for example, there are suggestions that the convection scale compresses and aggregates, precipitation intensifies, convection deepens. But one of the questions that's not been well addressed is what happens to the high clouds connected to convection, and then who actually cares? Do actually care? So I'm going to try to convince you actually we really do care. And I start with this quote from Tony Del Genio, and he hates me using this quote, but he did make it. And he basically said that high clouds are the climate modeler's canary. They're basically the modern community's last line of defense against top of the atmospheric radiation budget observations. So when you have all of the biases that are in the model below, in the atmosphere below, you can try to eliminate those through the eyes of the radiation budget by tweaking the high clouds. And so if you look at, for example, the distribution of tropical high clouds from CMIP5, which are from the various models of CMIP5, which are these histograms, versus the observations of our definitive measure of high clouds and tropics that comes from CloudSat and Calypso, you'll see the model representation of tropical high clouds is kind of quite varied and quite a lot different than the observations. So then the question, of course, is: do we actually care? Does it really matter? So I'm going to suggest to you that talk a little bit about why we care, and I'm going to sort of frame it around 2 main points. The impact of high clouds and the radiative heating is central to how convection gets aggregated, my arguments, and how the hydrological cycle associated with convective storms gets modified. They play a really important role in the whole hydrological cycle of storms, and from a point of view of the storm scale up to the seasonal and to the climate scale. They represent important feedbacks that influence both climate and the hydrological sensitivity. So I'm going to talk a little bit about the climate and hydrological sensitivity, and with a view towards what high clouds actually do. And then we're going to sort of come towards the end and talk about what steps are underway to address advancing our understanding of the relationship between high clouds and convection, because it's quite poorly, I would argue, it's quite poorly understood. And I'll provide 2 kind of example activities that are kind of leading us towards some degree of understanding, or hope to lead us to some degree of understanding. One is the GeoX upper tropospheric clouds and convection PROS activity, which is identifying some very interesting characteristics of high clouds and in association with convection. And then we'll talk about the concept to really go after measurement of convective transport and its relationship to the high clouds produced by deep convection and convective transport. So that's sort of the outline of the talk. Okay, so I'll start with the climate change sensitivities. Let me start with the hydrological sensitivity first. Then I'll talk a little bit about climate sensitivity, but through the lens of feedback, rather than the sensitivity per se, but the feedback and the mechanisms and so forth that we think are perhaps important. Okay, so the hydrological sensitivity. So this, we can introduce this in the following way. It's basically the change in, this figure here shows the change in two key characteristics of the global hydrological cycle, the column water vapor and the precipitation, as a function of the changing or the warming planet. This is the near surface air temperature change. This is derived from CMIP5 results. And basically, the water vapor increases at something like Clausius-Clapeyron, as we well know, but precipitation changes at something at a different rate. So the basic question is, why does this proportional rate of change of precipitation, why is it smaller than the water vapor change? What determines the magnitude of it? And what contributes to the model spread in it? And what you will find is that the model spread in terms of this hydrological sensitivity is largely influenced by tropical high clouds. Okay, so the one way the approach to attempt to answer these questions is, as you'll see in a moment, we'll kind of quantify aspects of this hydrological sensitivity, this rate of change of warming, is we would use something like CMIP analysis of abrupt CO2 quadrupling, using the Gregory kind of analysis as one approach that's kind of become favoured, and that's exemplified in the DeAngelis et al. Study. We also have the radiative kernel analyses that Brian Soden and others have been doing that allow us to look at sensitivities of the atmospheres, of the atmospheric heating as a function of changing clouds and water vapor and so on. Okay, so to start with though, you just have to start with the overall energy balance of the planet. And we've made some actually fairly major inroads in representation of Earth's energy balance primarily from an observational perspective. So much so that this is an example taken from the Alekiway et al. Study 2015, and this differs significantly from past representations of an energy balance. Not so much from the energy version that I produced in 2012, because mine was the actual very first attempt to actually put uncertainties on the fluxes. Previous to that, these energy balance numbers would just be given and stated with no measure of uncertainty. And so this is the beginning of understanding the hydrological sensitivity. And basically, if you think about the atmospheric energy balance, it's written down here in terms of a balance between the radiative heating or cooling that's going on in the atmosphere, this is this R term, and the flux of energy into the atmosphere from the surface, a turbulent flux of energy from latent heating and from sensible heating. And these are the magnitudes, the global annual mean estimates that are presently that we think these fluxes, that we can ascribe to these fluxes of energy. Now, the atmospheric rate of heating can be broken into a long wave part and a short wave part, right? We can further break these into a clear sky part and a cloudy sky part, right? And so for our observation, all of our observational tools that we've used and collected information over the last decade or more is basically made it very clear now. We now have a very clear picture of what role clouds play in terms of heating the column and what role the clear atmosphere plays. And you can see in this case, take a look at the long wave number here. It's a very small number, right? It looks very small. The long wave effects of clouds in the atmosphere and the radiation balance is quite small, but this is quite misleading because the global number is made up of a very large positive tropical response and a very large negative extratropical response. When you globally average, you get a kind of an almost zero number. And it's the large positive tropical response that ends up influencing the overall the global hydrological sensitivity, hydrological sensitivity of the planet. Okay, so let's just consider, just to answer the question, just to give you an idea how we answer that question about why is this precipitation rate of change globally constrained to be significantly less than the water vapor? And it ties to very basic physics as why this is the case. Whoops, there is a bit of a slope there. And let's just suppose, for example, that the radiative energy balance is sort of to first order, which it is, the first order, just look at the numbers, the net balance is about 100 and the net balance here is about, order of 100, 105. But just the first order, the atmospheric radiation balance is balanced by the latent heating associated with the precipitation, or the latent heat evaporation, which ties directly to the precipitation. So just consider the case where sensible heat is 0 and the cloud terms. These cloud terms are 0, just as first order, just to try to understand, what might principally control the precipitation change. Well, it turns out from basic molecular absorption physics, and this is well known in kind of the atmospheric radiation land, is that the absorption of radiation, and hence the emission of radiation, goes proportionally to the absorbing gas. In this case, it's the column water vapor. That's the principal absorbing gas. Goes to the proportional of that to some power. And that power more or less is about 0.5, the so-called square root law absorption effect, right? So this power is about 0.5. It's actually a bit smaller than 0.5, and it will vary a little bit, but it's sort of the upper limit is 0.5. So we know what this power more or less is through molecular absorption physics. It's called the curve of growth effect in molecular absorption. And so that means a proportional change in radiative cooling or heating, net cooling the atmosphere goes as sort of like B to the proportional change of water vapor. That means, if you then put it back into this balance, that the proportional change of precipitation goes like B to the proportional change of water vapor, and I've already said B is 0.5 or less, right? So that tells you exactly why precipitation globally cannot track exactly the water vapor change globally. It has to be significantly less. Energy demands that that's the case. And so basically you put some numbers in, for example. Let's suppose B is about 0.5. It's still really a bit less than that, but let's put 0.5 there. 7% per degree Kelvin for water vapor leads us to about 3 and a bit percent per Kelvin change in precipitation. And that's exactly what you kind of find in that slope diagram I just showed you. Okay, so then if we break this down now in terms of this Gregory analysis, you can take the various terms of the energy balance and how this gets perturbed with this abrupt increase of CO2 and watch this evolve as the planet starts to warm in response to that abrupt CO2. And that's how these feedback analyses are done. And basically from the slopes, from these analyses of the individual terms, you can take this term, you can take the radiation term, the sensible heat term, you can take the radiation term broken into long and short wave, you can break that into clear and cloud, and so on. And you get the individual slopes of this as a function of the global mean temperature change, and that's a sort of measure of the kind of the feedbacks going on in terms of with respect to the hydrological cycle. Okay, and basically this is just a sort of the summary to answer that question that I posed. Essentially, the net change of this is the hydrological sensitivity in percent per Kelvin. The net change is about just under 3 in this aggregation of CMIP models. The long wave clear sky water vapor effect is a dominant one. So the precipitation change globally is a consequence of the water vapor feedback. And then you've got the Planck factor, and the Planck factor and the water vapor factor are sort of intimately linked. They're you can't really cleave them apart because the Planck warming is a function, it results because you've got an increased absorption by water vapor and so on. Sensible heat factor is quantified here, and the cloud feedbacks are here, and this is factor turns out to be a factor that has come spread across the models, and water vapor factor. So you can sort of break this down, but essentially it's saying that essentially this is determined to a large extent. Why this is less than water vapor is it's set by absorption emission physics. What determines the magnitude? Well, these are the factors that determine the magnitude. What contributes to the model spread, which I haven't really shown, the absorbing aerosols is one factor, and the high clouds is the other factor. And this is just a diagram that's taken from, it's actually something recently we're pulling together. There's 19 different configurations of HADGEM in here. They're the green curves. This is the hydrological sensitivity, and this is the long wave atmospheric cooling. So to a very high order, the change in atmospheric cooling of the atmosphere correlates directly to the correlation of about 0.96 to the hydrological sensitivity. So just was saying what I've just said is that the long wave change of energy exchange in the atmosphere controls this hydrological sensitivity. The CMIP 6 points, there's too few of these to really, we don't have enough of these in the archive yet to kind of pull this together. The CMIP 5. Now the spread between these is mostly high clouds, and turns out mostly tropical high clouds that drive the spread between these models. Okay, now let me go on to the next aspect of the climate part of this, and it has to do with the feedbacks in the system. And this is sort of a diagram that kind of encapsulates the cloud feedback problem. Imagine you force the system, it perturbs the system through the radiation balance. It changes the clouds, which in turn changes the radiation balance, and ultimately the end result is some climate change. This is a view that was sort of popular in the 70s, but still relevant today, right? Now, so there are two parts of this loop, and sometimes the community forget about this. There's two parts of this loop. One part of this loop, in much of the 70s and 80s, focused on this part of the loop, and it was really about if you change clouds, what's it do to radiation? That was an intensive area of research in the 70s. You'd be surprised we didn't know how clouds affect the radiation in the 70s that much until we started to sort of focus on this. This is actually the simplest part of the problem. You know, given some change in cloud properties, we can determine what the change in the top of the atmospheric radiation is. Simply monitoring the top of the atmospheric radiation balance and associating with cloud changes, as we do now through radiative kernels and so forth, does not provide a measure of the feedback. It's just one part of the loop. The other part of the loop that's sort of the real challenge, and was the focus more of today, and shifted from the 70s and 80s to the 90s and today, is basically the problem of cloud parameterization and cloud prediction. Is given some change of the environment, in this case some change in the radiative forcing of the system, what the heck happens to the clouds? And that's a question that we still challenges us today to kind of figure this out. Okay, so I'm just going to kind of give you a few examples of what we do as we go around this loop. But I would say our basic dilemma, and one that I haven't seen a clear path forward yet, we do this incrementally, bit by bit, is that how does one go from mostly hypothesis? Most of our studies of the entire loop are through large-scale models, and the MIP activities of CMIP sort of have basically hijacked this whole problem. But that's not knowledge, that's more hypothesis. The models aren't really tested, they're creating hypotheses. How do we go from that to true knowledge-based? How do we convert that to knowledge-based? And I think that's really a kind of a dilemma for us all in this very complex problem of these feedbacks in the system. Okay, so let's just take the first part of the loop around here, the simple part, as I said. And one approach to answer the question of the sensitivity of the energy balance of the planet by changes in clouds is done through these radiative kernels. And this is Zelinka's study in 2013. And I've boxed in here the high clouds. And the high clouds have enormous spread in the long wave and the short wave effect that have a really large spread across models. For you saw how much the high cloud itself across models changed in the very first view graph of mine, right? So they're very large, but curiously, the long and short wave effects cancel, giving a kind of a small net effect. And this gets misinterpreted by the community as, oh, the feedbacks in high clouds are small. No, they're not. They're just, you've got these big factors. So if you've got a feedback that's altering just one of these factors, you've got a potential for a very large feedback going on in the system. We're still struggling with trying to understand the role of the high clouds and the feedbacks in the system. And a popular feedback that's been popularized by the group in University of Washington called FAT is all predicated on changes to the long wave part. And that's the FAT hypothesis, sort of operates in this part of the sphere. Okay, so that's the approach we take to go around that part of the loop. So let's go look at what we do to go around the other part of the loop. Okay, so let's think about this other part of the loop, the more challenging one in which we don't have a clear-cut, definitive ways to answer the questions, but we sort of do it like with incremental approaches. One approach is to basically through the MIPS. We go right around the loop in the MIPS and infer this cloud prediction influence on the entire feedback through MIPS. That's legitimate, but untested, and as I said, mostly in hypothesis land. We have process studies married to observations, for example, that try to look at more detailed processes involved in the cloud prediction problem, tied to observations to verify that we understand the processes that ultimately lead to the development of clouds, right? Radiative convective equilibrium experiments have been long used, many years, over years, and now we have a version with high-resolution cloud resolving modelling in radiative convective land. And we even have a radiative convective equilibrium MIP in this next cycle of MIPs, right? So, and then we have climate variability. The climate variability, we use climate variability, observed climate variability as a window into cloud response processes to sort of get a handle on the whole feedback. But this is climate variability, not necessarily climate change. And is this really a measure of climate feedback? And that's a question that, you know, we debate all the time, right? Okay, so I'm going to give you a couple examples in this area of some tantalizing looks into high cloud effects in the tropical system through climate variability analysis. Anyway, so let's just sort of highlight an example of radiative convective equilibrium as one example in this suite. There's probably others in this suite that I haven't really considered. The early experiments with radiative convective equilibriums in the 70s and 80s postulated the importance of the water content of clouds in feedbacks. How wet clouds are really influences these feedbacks, right? And then the CRMs became more explicit role. Really became popular in the 90s. And this is an example of a study that I actually did in 2008, where you look at a large domain radiative convective equilibrium experiment with a cloud resolving model, where you look at the evolution of the equilibrium, this time in terms of precipitable water, changing, this is like a Hofmöller version of changing precipitable water, with a constant radiation set across the domain. The radiation is just fixed for all time. And versus one in which you have fully interactive radiation, you start to see organisation taking place with respect to the moisture and with respect to convection. Which clearly just illustrates the point that the differential heating established by this interactive radiation and for which the high clouds play a principal role in this differential heating differences and driving a secondary circulation and helping to aggregate the moisture into these wet regions and dry regions, much as it was envisaged by Gray and Jacobson in 1977. So we're not really inventing anything new. It just is kind of an interesting kind of set of tools we use in the toolkit to sort of try to address this broad, complex problem. Okay, so I'm going to kind of give you two examples, quite quick, on how we use climate variability and use it purely from an observational perspective. And we're going to look at one example where we use GPS tropospheric heights, the tropical tropopause heights from GPS. We have a multiple decade time record of this. Top of the atmospheric radiation budget matched to this. Cloud properties matched to this. Convection intensity measures matched to this. And ENSO and Brewer-Dobson circulation indices, so forth, matched to this. And the other one is we're looking at the multi-decadal time series of various forms of data, looking at ENSO, the warm phase of ENSO, and what happens to the hydrological cycle and the role clouds and radiative heating plays in terms of the hydrological cycle of the warm phase of ENSO. And I sort of touched a little bit on the first talk on Monday, so I might skip over some of that. Okay, so let me show you the example from what we're discovering from observing the variability of the tropical atmosphere. Most of this is sort of set on 20 north, 20 south average. And it has to do what we might refer to as breathing, of the rising and the falling of the tropical tropopause over over the seasonal and then interannual variability of it. So the seasonal variation has been well known, well documented. Reed and Gage published something back in the early 80s, I think, on this. This shows you the Earth's energy imbalance, 20 north, 20 south Earth energy imbalance, with distinct seasonal cycle, just really more or less tracking the sun as the sun moves across. And this is the tropopause height, rising and falling. I'm trying to look at the time so I figure out how much time I got. Rising and falling, it's lagged, but there's a correlation between these. And Reed and Gage had argued that it was principally tracking the SST as the SSTs warm, and the convection of the warmed SSTs deepens, and the tropopause swells as a result. It's a little bit more complicated, it seems, than that, because there's also a fairly distinct correlation with the Brewer-Dobson circulation, which is this green curve here. This is a tropopause height. There's a Brewer-Dobson circulation index. So it may be a little bit more than just the warming of the SSTs, but lagged by the sun. But anyway, the bottom line is essentially that the tropopause height swells as the net energy going into the system increases, right? Okay, so the interannual variability of this is completely different. Completely different. It doesn't map in any way to the seasonal variability. It's quite fascinating. And we don't actually understand the consequences of this yet. This is kind of just something we're still trying to mull our way through. And this is the interannual variability, showing again the tropopause height variation over this 2006 to 2015 record of period of time. And here's the energy imbalance variation, quite somewhat strongly negative correlated. So basically what we find in the interannual, that net energy in, when you get a decrease of net energy in, it correlates with swelling of the tropopause, right? And it turns out, and I've got to skip over this next view, but it turns out a principal factor in this, in terms of modulation of the energy balance, are the high tropical clouds and the thickening of them. So as the convection deepens, the anvils get much thicker and much brighter. So this is a solar-driven potential feedback in the tropics, not a long-wave potential-driven one, right? So this is something we're kind of discovering, trying to figure out what it all means. So I'm going to skip over this because it basically just said what I just said. The next example is climate variability is ENSO. And so this is sort of a fairly standard approach to look at the Nino 3 SST variation and use the index and look at the warm phase, the ENSO warm phase, and then correlate to the SST anomalies in the Nino 3 region, various variables of the Earth's system, like relative humidity in the upper troposphere, for example, to the warming in Nino 3 region. And that correlation gives you the slope, and that slope tells us about the change in any region of relative humidity to the change in the ENSO, SST region, right? And so this looks like this as a map. So this is the upper tropospheric humidity change associated with warming in the Nino 3. So you get this big region of warm moist where the tropical equatorial warming is occurring, and you get this big region of drying around it. This looks very much like the kind of the gill response to equatorial heating. And this is kind of a sort of a dominant response. And so you can then sort of group the data in terms of this dry region and this warm moist region and contrast the properties, and that's what we basically did. This is an example of the precipitation change and surface ocean winds done the same way and correlated the same way. The precipitation change is 50-60% per Kelvin that we see occurring in that warm moist region. And so what we've been able to do is do this for a variety of parameters, and we now can come up with an idea of how the differential heating relates to this warming of the Eastern Pacific. And so you see a latent heating change. The warm moist region has quite a large injection of heating into that warm region, and the clearer, drier, colder region has a stronger a decrease in latent heating because all the convection and clouds have moved into that region. And the radiative, and this diabatic heating component is reinforced by the radiative heating component. So you get this dipole of heating cooling, a column heating in the moist region and a column cooling all that dry region around it, which it promotes a circulation that continually feeds moisture in, but there's a negative feedback going on in the oceans. You can see this here clearly in the radiation terms, where you see basically the solar shading over the oceans produces a very strong negative feedback, very strong reduction in the heat fluxes into the ocean. And we've been able to, over the many years, been able to now quantify these. So these are sort of measures of that feedback going on in this system that's sort of drawn here as a circulation system between an enhanced heating and enhanced cooling and the circulation between them. And we've also been able to measure exquisitely the heating profile differences in these two regions with the modern observations we have from active instruments. Okay, so I'm going to skip over that. Okay, so let me now just go to the close and wrap it up with a couple of examples towards an understanding of the relationship between convection and high clouds. What we're beginning to do to try to get an idea of how high clouds relate to convection before we think this is a very important topic for the reasons I've just described, right? Okay, so One study is the UTC, this UTCC Pros, and the group there uses air observations, hyperspectral sounder data. And the hyperspectral sounder data has many advantages over just simple OLR measurements. You can use the spectrum to work out the emissivity of the clouds, and that emissivity of the clouds tells you something about thick versus thin and so on. And you can take the minimum brightness temperature observed, and so, for example, you could plot the minimum brightness temperature in the regions where the emissivity is about 1, and you might interpret that to be the core, the convection core. That's why you would do it passively. And we're in the process of determining whether this makes sense or not. And so this is cloud top temperature of the core. So you've got deeper, stronger convection here and weaker convection here. And this is the ratio of the thin clouds to the total ample cloud. And what happens is that, curiously, the amount of thin cloud increases as the convection gets stronger, or proportionally the amount of thin cloud is, in terms of contribution to total clouds, a greater contribution to the total cloud than it is for the stronger convection. So we start to see some idea of the properties of high clouds are changing with convective strength. This is a fairly coarse way to do this, right? Fraction of thin cirrus, emissivity less than 5, increases as a minimum cloud top temperature within convection core decreases. Stronger convection cores associated with larger fraction of thin cirrus cloud coverage. Question mark, wow. Well, we don't quite know what it all means yet, but we're still trying to understand this from a purely observational point of view. Now, I want to close now with an initiative we're trying to move forward now, and we'll expect to see this occur sometime in the coming decade, where we're really going to go after measurement of deep tropical convective transport. It's framed around the amazing technological advances that have occurred with RainCube, and I showed this the other day. This is RainCube in a thermal vac. It's a tiny little toy thing making measurements of rain, a Ka band, that's the RainCube rain, matched to the GPM rain, and you can see its performance relative to GPM that. And so what we want to do is make measurements in a convoy separated by time. So we want to make measurements of the reflectivity of storms, but time tagged. And so you want to use time specifically as part of the measurement strategy. And we can do this now because of the cost of this, and the technology of this allows us to make these things in an affordable way. So the idea is as follows. We're going to be proposing a bigger radar than the cube and than the RainCube. It has a swath, and we want to look at this 90 seconds apart and 30 seconds apart. So the time difference is one of the dimensions of the measurement. The reflectivity of the radar is another dimension of the measurement. And just to sort of give you a sense, we've done quite an extensive amount of study on this. Just to give you a sense, this is a simulation through a tropical storm. This is the reflectivity itself through the tropical storm. This is the time difference of about 90 seconds through the tropical storm and reflectivity. And this shows you, for example, just a simple correlation between the maximum time difference of reflectivity is one of these. I think it's, I'm not sure whether it's red or green. I think it's green, versus the maximum vertical motion observed at that location. And so basically, the larger is the reflectivity difference that you see at any level, the more directly that relates to the vertical motion. And so we have two basic observables, the reflectivity, which tells us about condensed water, and the delta Z as a function of time tells us about vertical motion. And together that allows us to estimate the movement of water and the flux of water and then the flux of air upwards. And this last view graph here is just an example of retrievals applied to a very large CRM ensemble to test the idea and verify the idea that we can indeed retrieve mass flux. Here's an example of mass flux retrieved at 350 hectopascals. So we think this is an opportunity. The community is quite excited about this. There's an opportunity to measure critical information about convection as it relates to convection itself, storm intensity itself, but also to the high clouds that they produce. So that's it. Basically, we'll just close with this summary of what we've already talked about. We do care about high clouds, and here's some highlight results. Rather than put words in there, I just sort of show these key figures that talk about it. High clouds affect how convection gets organized and the precipitation that comes from organization and convection. It affects the hydrological sensitivity in the climate scale. There are feedbacks associated with high clouds and convection that we scratch our head, we're still trying to understand. There is connection between high cloud and deep convection that we scratch our head over and still try to understand. And then we have a strategy to go do some more quantitative measures of the transport within convection so that we can better understand and model and predict behaviors like this, which we think are central to the feedbacks going on up in these other aspects of the problem. So that's it. And take questions, I
Thank
guess.
you very much. Thank you. Yeah. Very interesting talk.
Rob, you can't see who's putting their hands up here because the light's right in your face. That's Kerry, right? Yeah, right.
Yeah, it's Gary. I have two questions
Yeah.
for you. One is, I sort of assume the beautiful paintings were painted by you. Is that correct?
Yeah, that was part of a it was part of a whole thing I did for cloud study painting and paper I wrote on cloud painting, art and science at the nexus, using clouds as a nexus.
They're really nice. Thank you. The second question comes to the science of your talk.
Yeah.
So, there's increasing evidence that the MJO, which we heard about earlier this morning, is really driven by the interaction between high clouds and radiation. So my question to you is really asking for your opinion on something. We've also seen this wholesale migration away from using convective parameterizations to sort of explicit convection. One of the drivers is the sort of failure of models running convective schemes to do a good job with the MJO. So my question is, how much do you think that might have to do with inattention on the part of people who design convection schemes to the coupling between convection and high clouds?
I think it's probably a lot to do with that. It may be that I've never wanted to believe that we can engineer the solution to a major scientific problem by just brute forcing it, right? But I must admit, as a scientific philosophy, we have to use tools that resolve the phenomena that's central to that thing we want to study, right? So I do believe we have to probably resolve convection, but we may be able to do a lot better job at dealing with unresolved convection by properly looking at its impact on things like high clouds. And I think high clouds have such an impact on the column heating and such an impact on the stability of the column that clearly it plays a role in terms of convection. And I think you're right. I think that we could still make major progress in the existing paradigm of convection parameterization, but at some point, convective resolved resolution is going to be needed. It just has a philosophical, scientific philosophy that, a probe that you want to study a phenomenon with needs to be able to see that phenomena, So at some point we have to face that, but it may be that maybe certain aspects of resolved convection isn't as important as reducing the high clouds in a net way from it. I don't know. It's a good question, but it's one we haven't really focused on really.
Any other question?
I have a question regarding this D train.
Yeah.
So whether you have any specific importance of this car-band radar from which you will get the wind over the Doppler radar?
This,
Yes.
okay, so we have plans in a decade for a Doppler radar,
Yes.
but our plans have to, unfortunately, focus on Ka band for Doppler because of the size things have to be to get into space, antennas and so on. This, this is an alternative to Doppler. It's a low-cost alternative to Doppler where you're using time difference, right? So it's going to give you an idea of the motion, as you see a convective core in reflectivity space, the reflectivity is going to rise, and so you're going to see the rising of reflectivity surfaces. Now, we have to be smart to convert that to vertical motion, but we already know that we can do that based on our extensive simulation work.
So the existing this GPM car-band DWR have this type of capability?
GPM?
GPM also have this car-band?
No, GPM has no motion capability. Okay. It doesn't have time difference, and it doesn't have Doppler. So that's what we're saying is the next step. We think the next step is to observe the dynamical aspects of water moving in the atmosphere. That's our vision for the next decade. We want to go away from static snapshots there's some sense of dynamics.
Okay, thank you.
And that's what D-Train is. That's a low-cost version of something we want to do,
Yes.
right?
Yeah, so now I will find out if any questions from remote, from those who are.
That painting, Kerry, that painting, by the way, flew on the rocket that launched CloudSat. It was put on the shroud and went
Any-
up, went poof.
So I will check.
Yeah.
Any remote question?
No?
Okay. So thank you very much, Dr. Graham. And our next speaker is Professor Sung-Woo Hang from Korea. Very good. Great.
Okay. This is Sung-Woo Hong from Korea. I'm going to talk about the new model development today. Two subjects. First one is a totally different subject. First one is KIOPS global model development for last 9 years. This is very boring. It's just one sentence enough. We have developed new model. Second one is the scientific issue. Subgroup modeling is becoming feasible these days. I'm going to share some finding we have done. Okay. KIOPS is established in 2011. The goal is to develop Korea's own global forecast system. 2011, actually, KMA adopted the UM model for global forecasting. It's a total budget of about 95 million, and we used 77 million US dollar for 9 years. So they have a 2 division, 6 team, and then development division and the forecast division. And then we have about 45 scientists and software engineers. Rest of them is administrator and hardware engineer. It's 3 steps. First 3 years, foundation and Beijing research. And stage 2 is the release beta version, so that we decided to have a strategy based on the KIOP's own research, set up the real-time forecast system. Stage 3 is the finalized operation system. And then I became to be a director since 2014. First 3 years, this is what the achievement in the before me. So that is there is a software very up-to-date software protocol, and then plug it into the CAM-SE, anchor climate model, 3D hydrostatic, and then replace the physics module in the CAM from the existing Anthony model, for example, Wolf-Grimm's GFS model. And there is some activity of the data simulation on the single point observation idealized test bed. So there are many various efforts. Somebody said is anchor model cannot be a Korea-owned model, so there's a lot of noise. So that after looking at also interview by individual steps, various efforts have been done. Then we decide to develop our own model by taking all the achievement first 3 years, also taking all of my experience before joining KIOPS. So that strategy set up September 2015, about 5.5 years ago. Name of the model is a KIM, Korean Integral Model. It was declared about a year ago. That then strategy is while we are developing our own dynamical core, we refer that the CAM-SE Grimm's MPAS model. So that develop major component model autonomously, but with a strategy of benchmarking performance of KIM with the reference models. In other words, mostly that is coded from the scratch, except for some physics model taken from the existing model. This is dynamical core, for example. We started from the very fundamental, starting from 2D shallow water equation, the set up the galvanic equation, non-hydrostatic, and then spectral element, and the fully compressible, and then expand perform the various ideal test bed in 2D, and then expand to 3D, core and coupled to the physics. So this is you can see that cubic sphere is same to the FV3, but it's a spec element instead of finite volume. Compressible time split integration is similar to the WRF model, but it's global. So that this is, for example, Damco core, ChemSE versus 2.0, our Kim Damco core. This is the scale of anomal correlation, the forecast day. That this is a typical measure of a scale. So there is a precipitation, light to heavy precipitation, higher is better. So as a reference model, GRIMS, spherical harmonic, and the ChemSE corresponding hydrostatic model, the new non-hydrostatic spherical element core was successfully formulated and completed, coupled to the physics package. Here, GRIMS model, here we mentioned that this is a long story since 1998. It was rooted in the NCEP MRF model and also combined with the regional spectral model. Also, this model is used to generate the NCEP realities too. When I joined the University in 2000, we expanded the single column model and the double free series Damco core. And then it is also, this model is used to develop a physics module, WRF model, for example, WSM326, YSPBL, WDM microphysics. So that not only the WRF model, it has to be evaluated in the variety test bed. So that global regional, one single source code can be easily tested without modification in the global and the climate to NWP. For physics, mostly adopted from the UX model. For example, this is a cumulus planetary scheme observation of a daily precipitation over 300 millimeter. This is NCEP GFS SAS, very little, less than 30 millimeter. This is our revision in triggering function, I think. Yeah, triggering function. Then reproduced at the heavy precipitation. So this is an example of a revision in existing physics module. And this is physics package development. Actually, we cannot wait until Damco core was stabilized, so that we used the WRF or GRIMS model in revising the individual physics module or entire package of physics. This is a 2-year effort. This YS 2013 is the time I was in Yonsei University. This is the version in 2 years in KIAPS. So that higher is better. Anomal correlation 2.0 is much better. Also, prep and skill score is much better in whole categories. So that while Kim core and the simulation were being developed, physics modules have been improved in WRF and GRIMS platform. And data simulation, very fortunately, we developed the direct transformation of observation data into the native grid, cubic sphere grid. It was done in early 2014 in Song and Kwon. And then it is very efficient. Because data simulation on a cubic sphere was very skeptical, many people worry about, but we made it happen. But we had to build all the quality control and the software in seeing the data by ourselves. For example, we started from the Zonde data and the aircraft and settled data one by one. It took a long time, but this is the way to go. We have a 2-track of data simulation, local ensemble transform column filter. And then we added the start from Zonde surface aircraft, just like a 3D bar. This is data processing. Because there's no data simulation on a cubic sphere grid, we had to build all the software. Zonde data, we took more than few years for initial development in the single point observation, and then evaluated in the test run, and the dark blue is the full system coupled to the model. So I think this is the way to go. We had to build it from scratch, but this is the best way to learn Anthony model, who never expressed modeling. It took about a few years, and then this is Kim physics packages 3.1. We declared the Kim model last year in the special issue of journal. Cumulus Plus scheme, we collaborate with GFS, actually NSEP, and then cloud microfiche from the WSM5. Radiation, which we unified also, we revised the GPEC very significantly, and some of them very new. For example, no mounting gravity drag is a newly developed source-based spectral gravity drag scheme. Okay. So it's a 9-year project. Exactly half was taken to build the full entropy system. We started the real-time forecast starting July 2015 here. It's a 2.0. And then version update every 3 months in stage 2 and every 6 months in stage 3. And then data simulation, we spent a lot of exercise, idler test, and then 3D bar and the Elite Cave started 2015, and then merged the 4D EN bar in 2017. And the resolution was with 25 kilometer, currently in 12 kilometer, 91 layer at the top of the 0.01 hectopascal. So that milestone is we have April 2019, semi-operation started. So that all the product is run in parallel with the KMA and then is used for forecast by KMA forecasters, and they got the feedback and the consequent update. So it will be operational early next year. So let's get the performance in semi-operational. Over East Asia or Korea is comparatively better than the existing operational model. This temperature forecast, I think 50 millibar is lowest 2 is a version of Kim. Kim SOP is the semi-operational, and then Kim 3.4 is the newest version. Okay. I think it's a typhoon, so that is it's interesting to look at typhoon forecast. There are several typhoons affecting Korean Peninsula this year. Very interesting. This is a Kim forecast at the semi-operational. This GDOPS is KMA-UM, it's ECMWF. I think that blue is the longer lead time, and orange is shorter lead time. So that is Kim is very consistent. Not always. If you look at the another typhoon was moved to the north, crossing the Yellow Sea. This is Typhoon Ling-Ling. It caused a lot of wind damages of the Korean Peninsula. So that there is something that they are not correct in the earlier forecast time. We have to improve that track error. Okay, this is KMA-UM and the ECM-WF. Yeah, ECM-WF is almost always best. Yeah. But if you look at it very closely from the forecast point of view, it is not true. They issued this track forecast based on ECM-WF and heavily criticized by the newspaper and the broadcasting. And then they issued that the typhoon will move late, but when in the early morning, it's a few hours earlier in the morning. So that this is the real observation, so that the KMA was criticized. He said, PASS is correct, but they still incline to the performance of Eastern model. So that they issued the forecast this, and then real PASS was like this, Kim. So let's get more typhoon track error. There are, I think, more than 5 typhoons affecting Korean Peninsula. This is the Typhoon Danas. Kim is semi-operational. 3.4 is the most updated. KMA is KMA-UM. So that day 1, there's another typhoon, Francisco. Day 1 is Kim has some problem. It's day 2 or day 3, day 4. Actually, Kim is better. That is basically is analyzed by the KMA. In terms of intensity, actually, Kim, this is the solid line, is a time, solid line is observation for the Tanas and the Francisco. KMAUM is very good at is the deepening of the central pressure, but it's a little, it's a deepening further. It's a weakening, but it's still there. I think Kim as a problem in the intensity is not strong enough. This is observation, and this is a Kim. Yeah. Also same, it's a 3.42. It's a 990, so that is not deep enough. On the other hand, so also same that is true is another typhoon that is, Kim is not strong enough to develop central pressure, but it's also UM has some issue in the too deepening last longer instead when they are getting weaker. So that this is the problem, but I will show you that this has something to do with the dynamic core issue. I will show you later. This is the latest forecast last year. I think initial time is 26 to 12G. This is Kim and this is UM. With sea level pressure and the precipitation, you can see that very similar. This is a typhoon developed. This is a 10-day forecast and 3 hour up to 84. So that this forecast time, 7 to 8, you can see that, where is it? Here, timing is really different, but it's still 180 already 10-day, but it's high pressure, low pressure, high pressure, low pressure. So both two models are different in all aspects. Data simulation, time core, physics, but the forecast pretty much. So that KMA forecast favor now. Okay, just enjoy this. Actually, 00G forecast now just finished, but I didn't have a time to get the file yet. Okay. See it? 96, so the precipitation over here. Next one is over this region. This is the first time to get the result over Indian region. This is a precipitation again. Something different, you can see. It's a Kim and a UM. But here also they are pretty much, but something different. You can figure out which one is better later. This is 10-day forecast. But there's a lot of similarity, you can see that. Here is something different. Now it's 1 week. This cyclone develops. You can see that December 5th, whether the cyclone develops or not. Okay. Yeah. This is a 10-day forecast. Yeah. Okay, so that objective scale over northern hemisphere, for example, anomalous correlation coefficient need to be continuously improved, obviously. Subjective forecast scale by KMA forecast or the objective scale over East Asia, Korea, very competitive or better than KMA UM. It is very reasonable because our focus on the East Asia, also Korean Peninsula. So this is the Kim evolution in terms of standard measure of medium range forecast scale, 5 millibar anomaly correlation coefficient. In the early time, 2015, the scale was very bad, obviously. This is not, model was not set up yet. It was about 1980 performance. Then gradually increase. So then now, 3.3 was 97.7% in terms of anomaly correlation coefficient, but keep improving. And then this is 3.3, and we already updated 3.4 October, and 3.5 is a final update in December. So this is a major update. Let me briefly let you know what will be updated next version. So that is radiation cloud. It's a cloud radiation based on the cloud model result and the in-cloud effect radius. This is a planetary scale bias in the Kim in the current version. cooling and warming of tropics, cooling the middle latitude, the cooling of the troposphere of the tropics. So this is the deviation of the modification from control. So that this warming is roughly opposite to the bias in control. So that I think this is my own contribution this year. Another one is time core hyperviscosity. Almost all the model has a constant value of hyperviscosity, so that over diffuse when the wind speed is smaller. So that hyperviscosity coefficient is determined considering the maximum wind speed. But we developed the so-called dynamic hyperviscosity formula such that the dispersion property of spectral element advection hyperdiffusion system to be optimal as much as possible. So that this is, for example, value of diffusion coefficient. In the hyperviscosity, the constant value is a maximum. So that we have energy gain in the small scale. The green line is the hyperviscosity, and the black line is the traditional viscosity. So that total work clock time was reduced by 15%. Numerical point system, this long-term, long-lasting problem in the bullseye in precipitation is elevated near the typhoon. And intensity of typhoon was improved, over-improvement in the anomaly correlation. Another one is data simulation. We need 4 more data should be added in the final version. And then IAU and the analysis and the LSK also be improved. So that this red color will be early next year. Also, we participate in intercomparison project. So that because the model itself is most likely now 98% completed. I think Lucas mentioned the diurnal cycle of SAS. So that diurnal cycle, there's intercomparison, and then this is our own evaluation. This is northern hemisphere land. This UM is green, and IFS is orange, brown, and the KIM is red, black, solid. And the TMP observation is a dot black. So that pretty much good. By the way, the reason is the diurnal cycle in the SAS is due to the triggering function that follow pen I made about more than 20 years ago. It was not changed much. Also, we attended the other crude intercomparison project, so the graduate area project. Green is a KIM, not outsider, and it's something similar to the IFS, but it's something different in the higher altitude, which may have something to do with spectral gravitational scheme. Okay, this is the first part. Now it's changed to the very high resolution experiment. Subkilom modeling is a background is actually in the literature very little sensitivity when the grid size getting smaller and smaller. We have a gain of a small scale feature from 9 to 3 kilometers, 3 to 1, but 3 to 1 kilometer below the 1 kilometer, very little gain. Also, excessive precipitation at sub-kilometer resolution was found in the. This is very common, and then we have also there is issue scale aware gradient CPS PBS scheme. So that at first coming high resolution in the workshop organized by myself and the Dudia, also Weiko Tao, Saito was the original member. We introduced that gradient of the CPS scheme, and then also gradient for PBL scheme in coming 10 years. Coming 10 years is already 9 years. It was workshop 2010. Okay. So gradient is partly resolved, partly parameterized. For example, your grid size is 5 kilometers. It should be partly parameter, partly resolved. So that we have developed gradient similar parameter scheme is based on the SAS, and then there is a grid size dependence suppression of a parameterized updraft when grid size is getting smaller and smaller. So that this is a sigma 1 cloud fraction. Another one is a dependency of grid scale motion average of the column. So that convective mass flux, the idea is that the convective mass flux is a combined product of two cloud fractions, so that mass flux modulated dynamically in relation to grid scale motion in a sense that MPS, or grid scale microphysics reign, takes it over when grid scale flux becomes strong. So this is a result, 3 kilometer, normally no CPS. This observation. If we have a no CPS, we get the heavy precipitation, but wrong place. But this is better than with the conventional CPS scheme. If we have a conventional CPS scheme, quickly neutralized by releasing CAPE too efficiently. So that this is the gradient CPS. It's a 3 kilometer. Somebody say 1 kilometer, but it's even 1 kilometer, same is true. 1 kilometer is a very organized precipitation, but then without CPS, we have a precipitation wrong place. There is a core, but wrong place. So still did it. For PBL scheme, this idea was devised by the 2013. It's derived from the WRF LES simulation. Scheme was devised for the revision of YSPBL. This is the left column 1 kilometer, right column is a 333 meter resolution. I hope three-dimensional data. This is shading is a vertical motion. You can see that vertical motion of even 1 kilometer, YSPBL, conventional PBL scheme, suppress all the grid scale eddies, mostly. 1 kilometer, even 300 millimeter. Because this is the, in the new scheme, we have a grid resolvable eddy develops, so stronger in the 300 meter. I think that might be the reason we don't have much sensitivity of the simulation when grid size is getting smaller and smaller. Okay, purpose is that investigate the effect of the scalar PBL scheme against the conventional PBL scheme, which is YSPBL, to understand the role of the turbulent vertical transport in simulating precipitation in aspects of the interaction between turbulence and microphysics. This is experimental design, WRF 3.9, and the Kim physics. Actually, Kim model has a physics driver so that we can select WRF or Kim. Very conventional setup is, I think we started at 27 kilometer to 333 meter. We compared two YSU and SH PBL scheme. Interestingly, that this convection scheme is applied even 300 meter resolution. Okay. This is a case of a lake effect precipitation of snow over the Yellow Sea. This is a precipitation amount. This is an island, small island, because it has an observation point. This is a cloud street. This is a scuti look profile. It has an amount of a cloud. This is an overview of a simulated precipitation. I think a radar and then total rain. I think it's hourly precipitation, maybe. This automatic weather station of 24-hour precipitation. This is simulated. Yeah. So working pretty well simulated. This is, I think, 3 kilometer. Then we will look at the sub-kilometer simulation, focusing on 300 meter resolution, comparing precipitation and the background atmosphere. Okay. So this is a 1 kilometer, 300 meter resolution. I think this is 24 kilometer precipitation, control YSU, new SH. You can see that maximum core was reduced, so that reduction of precipitation. And this is a validation against observation. So that this control is a gray line. New one is a black dark. Observation is a point over here. Point. So that you can see that control overestimate precipitation. And then this is a whole domain, so that when the YS to SH amount of precipitation is reduced, then what is the mechanism for the reduction of this? That's the question. Also, vertical velocity, look at this, control and the new. You can see that looks similar, but if you look at the power spectrum of a vertical velocity, control is control y is PBL is gray, and the new scale away is dark. So you can see that given the spectrum 2 to 7 kilometers, so that WK power is increased. So that vertical velocity increased when the scale away of PBL is used. And then this is the water vapor and the potential temperature. In general, drier when the new minus control, the drier in the PBL and moisture above. And then temperature is cooler within PBL and warmer above the PBL scheme, PBL. So then let's look at what caused this difference. This is the profile turbulent moisture transport. So that this is the gradient of vertical flux determine the tendency of moisture. So that is when YS to SH parameterized flux is reduced, and then reserved flux is increased. Actually, this is a counter effect, but it's not 100% offset. So that is a, and then let's see. Yeah, so there is this part, parameterized moistening and the drying moistening. But manganese is slightly different. And the hydrometer wise, so the liquid water pass is increased, and the cloud ice and snow is decreased. Yeah, so that the reason is that increase of warm rain physics is that because the W is increased in the parameter scale aware PBL scheme, so that it is a vertical transport moisture enhanced, and then condensation enhanced, and cloud or rainwater increase, and auto conversion increase. But when the raindrop is false, that the PBL is drier, so the evaporation enhanced. So that is the amount of precipitation falling to the ground is not much change. So this is drying and moistening. So this is the contribution from the microphysics. You can see that enhanced rain evaporation, and then this is increased evaporation of cloud water, moistening. Yeah. Also increased condensation is a reduction of moisture over this level. This is the contribution by the microphysics, blue line, and they combine the two as this moistening and the drying. This is potential temperature, about the same. That is a microphysics contribution and the turbulent transport contribution. We have the colder boundary layer and the warmer above the boundary layer. Okay. So that for the ice microphysics, so that we have a drier above it, so that deposition sublimation increase, as that aggregation of snowflakes is reduced, so that falling of snow is reduced, so the precipitation is reduced. This is a little bit busy, but this is a schematic. When the conventional scheme to the scale-aware scheme, first, residual flux is increased, so the parameter flux is decreased. That increased the vertical motion, enhanced the relative humidity at the cloud bottom, the condensation increase, it's a QC QR increase, but the drier of a boundary layer compensates the increase of hydrometer. Also, that the overall drying of a boundary layer reduced the deposition of water vapor onto the ice face, so that cloud ice and snow is reduced, snow melt reduced. So that surface precipitation is eventually reduced. Okay, this is all I want to say. Thank you.
Thank you very much. Any?
Yeah. What is the resolution of Kim, the global Kim?
12 kilometer for now, but it will be 8 kilometer sometime next year.
And what is the computational requirement in operational?
Operation requirement is a 2-hour window. We are using 30,000 core. It takes about 2 hours. So data simulation, I think 40 minutes, and the model is 1 hour, 1.5 hours. But we will have a new supercomputer next year, so that it has 600,000 core, so that you can even see it.
So impressive, thank you. Can you say a little bit more about your data simulation scheme and what are your plans? And second, on your plans for ensemble prediction, whether you're planning anything?
Yeah, that's a very good question. That is actually the ensemble prediction, not the mission of KIOPS, but we have to do it. So that KMA staff came down to the KIOPS building and they stayed 1 year to work on it. So that ensemble run will start at the same time of the KIMI's operation next year. Yeah. Resolution will be currently course at 32 kilometer now, but it will be higher when the next computer is available next year.
Great. Great efforts. Yeah. Very good.
Well, thank you.
So any other question or suggestions?
I may, okay.
One more.
In your scale, where under your scheme, you show the change of vertical profile of temperature and moisture. That change correspond to the observed evidence, or do you have you compared with observational?
Yeah,
vertical
actually,
profile?
also that's a good question. It is based on the LES data. So from the entire point of view, LES is kind of true. Yeah, so that is the base. But they said a lot of uncertainty in LES, but that is the bottom line, I think.
Any question from outside the hall?
I may have one comment for the people. Many people using WRF model. Some tip so that you may use to change the SHPBL. It's not been updated at all now. This is then we developed with the Waco Tower that you may think about move to this. Yeah. Because I'm not going to update any of this.
Very good. Great. Yeah.
Okay. Okay, thank you.
Okay, thank you very much, Professor Hung. And with this, let us give a...
Before ending, I don't want to miss the opportunity. Today is Dr. Hong's birthday.
Oh!
We should wish him a very good health and request Chair to give a small gift, not a birthday gift, but yeah. Please, Dr. Hong. So we'll break for tea and poster. And we'll assemble at 11:45. Yeah.
Thank you very much. So I'm going to be talking about what is my job description actually at the Jet Propulsion Laboratory is, except for the passive microwave part. My job is to figure out how to use, so once measurements are being made by microwave instruments, whether it's passive or active, to use these observations to produce estimates of instantaneous geophysical quantities for atmospheric science, but also for other applications in Earth system science. And of course, at the beginning, on the other side, motivate and provide the quantitative justification for why you need exactly those kinds of observations with that kind of an observation system. Again, microwave, passive or active, radar or radiometers, and how you think that they will produce the answers, or at least the instantaneous estimates that will help answer the scientific questions concerned. And in this case, the motivation was to try to use the microwave radiances that are currently being obtained over clouds we have a very large constellation, 10 radiometers today, heterogeneous, they're not all the same. Saphir is called a sounder, but it's one of them, and it doesn't work the same way and doesn't produce the same kinds of brightness temperatures as, say, the GMI on the GPM core platform, and not the same as MHS and et cetera, et cetera. And so how is it that you can use those radiances to obtain information about the clouds that they're looking at, the deep clouds, the storms? In fact, that's the main focus here. And to turn it into a more specific problem, how can you represent the dependence of these observations of the radiometers over clouds to the two quantities or two vectors of quantities that they are most sensitive to, which is the condensed water and the water vapor? And the reason why you would think that they should be most sensitive to these quantities is, of course, well, they're microwave instruments, and that's the whole point of being in the microwave, is that you are sensitive to the three-dimensional distribution of the water and of the condensed water, the vapor and the condensed water. And up until today, even now, this sensitivity is not very well taken advantage of. It's not being used correctly. In fact, what these passive instruments are most used for is in the clear, of course, because with the humidity channels, the absorption channels, they're used to estimate vertical profiles of temperature and moisture, and in fact, pretty much discarded in the rain, except for trying to estimate near-surface rain. And not just near-surface rain, but they try to estimate, you believe this, the surface rain flux, rain rate at the surface, from instruments which are really not that sensitive to exactly that quantity. In fact, they're much more sensitive to what's happening up in the atmosphere. The three phenomena that are most, that one. The three phenomena that are most at play in shaping what the brightness temperature that's measured by the radiometers. So you've got radiation that's welling up from the surface mostly. There's some comes from the condensation itself, but the upwelling radiation gets absorbed and therefore emitted by the condensation and scattered out of the beam of the instrument. And these three mechanisms, sort of like Trimurti, absorption and re-emission and then the scattering, are the three phenomena at work in creating the variability in the measurements. This is an example of what this specific instrument, the GMI radiometer, can see in 4 of its 13 channels. And at the very lowest channel, this 10 gigahertz is about 3 centimeter wavelength. So the wavelength is much bigger than the typical side of a hydrometeor. And so as far as it is concerned, in that part of the spectrum, all the condensation pretty much looks Rayleigh. It doesn't really, so it doesn't do a whole bunch of out-of-beam scattering, and the sensitivity is mostly to absorption emission. This is an exception to all the examples that I'm giving, or the illustrations. I usually try to look at tropical cyclones because you can identify features because of the high degree of organization. In this case, you're looking at the ITCZ a portion of the Atlantic ITZ, so it's a little bit amorphous, unfortunately. It's extending here. Brazil is down here, and Senegal is up there. But whatever, in this particular case, what you're seeing here is a precipitating portion of the ITCZ, so the sensitivity at that channel is mostly to what's happening in this bottom portion, absorption and emission, and it is manifested by the fact that the background is cold, and then you see warming where there is this signature. And then as you go to the other extreme, so from 3 centimeters to 3 millimeters, well, 2 millimeters, 3 millimeters, yeah, a little more, then you see the opposite behavior, because here the sensitivity 2 millimeters. Now you're comparable to the size of, most of the hydrometeors. It's the main mechanism that you are sensitive to is the scattering out of the beam, and so the signature is wherever you have a very deep cloud, you see very cold temperatures. And in fact, it works so well it's so sensitive to this that the coldest parts of the signature indicate the convective cores in this case. And so I wanted to give another example at the other end of the instrument spectrum. This is the Saphir radiometer. So all of these were taken by Saphir in the 3rd month of the mission after launch, back when Madras was also functional. And this is over the one tropical cyclone that was seen. This was in December of 2011, and this is Tropical Cyclone Elenga in the southern hemisphere. And what you see here is the dependence, not just, so these are the 6 channels of Saphir, all of them near the center of the absorption line at 183.3. The channel that's very close to the center is very sensitive to the water vapor. And as you keep moving out, you get less and less sensitivity. Now you're on the edge of the line, the absorption line in the spectrum. And that 6th channel, as you can see, is much more sensitive to the actual condensation in the eye wall. Well, you can now see the structure of the tropical cyclone where you couldn't see it there. And this is by comparison with Madras. Back then it was still producing beautiful data. And these are the much lower frequency. This is basically absorption. This is absorption by water vapor. This one is the difference between that and the scattering, the emission at 19 gigahertz. Just to confirm that, the signature that you're seeing, the sensitivity that you're seeing in the Saphir really is to the condensation in the cloud, not so much to the surface rain. So why are we not using this, and why don't we exploit this to express the information that these radiances contain about the deep cloud? So these are simulations. Maybe I don't need to dwell into them. They're basically, if you're using cloud resolving simulations, you can more objectively confirm the sensitivity of either different channels. So this is, I'm looking at the MHS radiometer. The reason I'm looking at MHS rather than anything else is because all the channels have fairly good resolution at nadir. They have a 15-kilometer footprint, which is probably not enough to resolve convection per se, but you do see the traces of the signature of convection quite well. And what you're seeing here is for each one of the 5 channels of MHS, this is just the linear first-order correlation between the radiance in that channel and the amount of condensed water as a function of height. So of course the problem isn't linear, but this does tell you, and it does give you an idea. I'm not sure why, maybe it's because of the AC, that it's above 5 kilometers is pretty much where the peak, between 5 and 8 kilometers, is the peak of the correlation with most of the channels, not all of them. And here is where I did a canonical correlation analysis. So instead of doing it channel by channel and looking at the condensed water, I looked for the best combination of the channels, either taking all of them, the 2 that are away from the water vapor line, and the 3 that are right around the water vapor line. So what is the best combination of those linearly again? This is just the first order expression of the correlation, the sensitivity of these channels to the condensed water. And unfortunately, you can't see it very well, and I don't have glasses. I always carry my glasses in my backpack and never use them. But the first canonical correlate, which is usually always an average that's peaking somewhere above 5 kilometers, has a correlation of greater than 0.8 for all of these combinations. What's a little bit perhaps more surprising or equally surprising, I don't know, is that when we do the same thing, but for the specific humidity now, I don't know, it says RH, but it's not RH. And again, these are a few simulations. This is not meant to be exhaustive, and I culled from the simulations only the columns were for this particular, well, I mean, I have the other ones, I'm not showing them. We're looking at the columns that where where the trim radar top, the top of the cloud condensate as sensed by the trim radar is higher than 12 kilometers. Oh, there we go. You do have quite pronounced sensitivity to the water vapor, to the specific humidity inside the cloud above freezing, which is, you know, it's telling you something. It's telling you that, you know, we should be using this information rather than just either throwing the data away because it's cloud contaminated, or using it as an estimate, a proxy to estimate the surface rain. Now, there is a problem, of course, with doing this. I mean, of course, you could, and I will show you how they do, certainly, for example, at the European Center, that's what they are doing. You can use a single shot forward radiative transfer. I mean, forward radiative transfer, up to whatever simplifications you're making, whether it's two-dimensional or whatever, can express the dependence of the radiance at the different part of the spectrum to the condensed water, depending on what you're assuming about the habit and the dielectric properties of the condensed water and the distribution of it. The problem is that typically what you will get are, it's maybe an oversimplification to say it that way, but there is a bias in that single shot deterministic forward transfer. I have a column of condensation together with whatever the temperature and the humidity profiles were and the surface emissivity. And I just make one calculation that gives me a radiance at a particular thing. If I compare with actual radiances, typically there won't be a match. And there's no reason to expect that there would be a match because many simplifications went into the problem, not least in describing the properties of the hydrometeors, which, by the way, if what you have came from even the most sophisticated models, the models don't have any dynamics for you know, how spiky the aggregates are, or what you know, they'll have some bulk density or some the descriptions. In other words, to calculate the scattering efficiencies that you need in order to do any kind of radiative transfer, you need more information than a dynamical model has or cares about, because the dielectric properties are not part of it. And what I'm showing here is, okay, failing a point-wise comparison, you're going to get what people call biases. At least what you would like is, if I did collect 3 years worth of data, and that's what this represents here, from, say, MHS, and if I looked at some empirical distribution of the temperatures in those 5 channels of MHS, and I'm reducing it here, I can't plot 5 dimensions, so I'm reducing it just to the first 2 main directions in the distribution. They're supposed to be, well, they're orthogonal, so they're supposed to be uncorrelated, and they kind of are. And if you take the definitions that you get from this empirical analysis and apply them to simulations that may have assumed different microphysics, then you get the surprise that, or maybe not, it's not too surprising, but you know, the distribution of the calculated radiances does not look like what the measurement is showing. And that's when faced with, for example, the problem of doing data assimilation, that's where you have to do some debiasing. You have to bring things into, but this, the reason I'm showing it is, it's more than just a debiasing problem. I mean, 2 quantities that come directly and are supposed to be the main descriptors of your synthetically calculated radiances and that are supposed to be correlated are anything but uncorrelated. Now, not all the schemes do it the same, and there's, you know, we found one scheme, well, we created a scheme that does it better maybe than the others, but that's not the point. The point I'm trying to make is there is value in maybe trying to represent the dependence of the brightness temperatures that are measured, maybe represent empirically how they're sensitive to the condensed water and the water vapor. Now, the dependence on the water vapor, representing that empirically I haven't been able to do that. But I'll come back to that slide. But what I've tried to pursue is some way where we can represent the observation. So these are the radiances, instantaneous radiances that are measured in one beam, as a function of the control variables in the model, together with the additional parameters that are needed in order to be able to get the radiative properties, and average somehow offline over all the quantities which I'm treating as parameters here. I mean, those would be the errors in my forward model, if you like. They're not errors, but they're just unknowns that I have no way either of knowing or of analyzing in the assimilation. They're not going to change because, well, the model doesn't care what they are. And the main distinction, why do I call something a variable and why do I call it a parameter? So a variable is anything that has modeled dynamics, and a variable is whatever doesn't. And so the idea is, can we produce a representation like this that is somehow automatically averages over all the things that we don't know and that the model won't care about? And what I will show you is the results of the attempts that we did to do it in a two-step process. So the first step is ignore the second term. I'm going to write my observation operator, which depends on the things I care about and the things that the model doesn't, in two pieces, but mainly a piece that would be empirically determined, and that would come from coincidences between a radar, which is assumed to be giving me the truth, because I mean, that's far from a given, but the radar is much more directly sensitive to the vertical layering and distribution of the condensed water than certainly than the radiometer is, with the bulk that it's producing. But somehow get the dependence on the precipitation empirically. So get that from by analyzing appropriately statistically a large set of joint radar and radiometer measurements. So I can always do this. And then whatever I find, I can always subtract it from any synthetic calculation that I will make and try to see how the remainder can be fit to the remaining variables that I will not have accounted for in my empirical matching. So one part is going to be empirical, and the other part is going to be coming from a match. The match will come from simulations. And what I'm showing here is, for example, just one case. These are two channels from MHS, the one that's very close to the center of the absorption line, the water vapor line, and the one that's the farthest away. And this particular simulation is of a tropical depression over a very large domain. Well, we had 5 nested loops, but the point about it is that 24 hours later it turned into, well, it grew to a tropical cyclone, Hurricane Isabel. And but we had a very wide range of convective cores and the clouds associated with them. This gives you an idea for how the different schemes would have differed from WSM6. So with departures that are not all that small, and this what ends up happening when we use 3 years worth of data to do the empirical match. This is the empirically calculated, not quite brightness temperatures. They're the EOFs, the first two EOFs are the brightness temperatures. And this is the remainder from a single shot forward calculation using the scheme that seemed to match empirically in distribution the archive, the historical joint behavior of brightness temperature is the best. And that difference you attribute to the water vapor, and it turns out that if you plot that difference, between the synthetically calculated forward EOF of brightness temperature and the EOF of humidity of the moisture, they do correlate quite well. Well, I'm tooting my own horn. If you call that quite well, the correlation is not 0. It's and the result. So this is we did this. This was in fairly early days when actually at the European Center they were considering how to do to implement the all-sky radiances, and this was one of the ways to represent it that was tested, just so that we could evaluate it. And I mean, it wasn't performing too badly. So this is a case of very severe rain from a tropical cyclone, actually, off of Madagascar. I tend to be partial to cases over Madagascar. So anyway, this is the no assimilation control, and as you can see, it differs from what the level 3 mosaic that's produced by NASA from the constellation said that the rain would look like. And this is the analysis using the operator that we did, that we developed with this, and these are actually, this is the exact fits for Saphir. And as you can see, so this is an instantaneous comparison of the outcome of the assimilation with what passes for ground truth. And yes, it does look, this looks a lot more like this than this does in many different ways. I'm not going to go over it. The point is that the results are not too bad. And we've also tested it on cloud resolving versions. Anyway, what the European Center ended up doing is a different way, because, well, they've invested a lot into the RT-TOV forward radiative transfer, and so they do want to be able to use that. And so what they do instead is somewhat different. I mean, you do have to be able to represent the dependence on what's happening inside the cloud. And so their approach, the approach that they ended up selecting, and that's implemented now, is you calculate, you make forward radiative transfer calculations for all the columns that you see in the neighborhood of the one that you're going to be interested in. And then you compare the resulting synthetically calculated temperatures with the observation over the point that you're interested in it. And you select as best match the column whose calculated radiances seem to match the observed radiances the best. But then you assimilate the values of the controls in that column as being the estimates that you've observed, sort of like a 1D var before you do the full assimilation. There's nothing inherently inferior between the assumptions that are involved here and the assumptions that that we're making in this other way. It's just that now you've kind of shifted the burden of describing the uncertainty to, well, what kind of an uncertainty does this X, do the variables in the column, which you're pretending that you observed but you didn't. They just happen to have created the synthetic temperatures that compared the best with the one that you observed. So in other words, you're claiming that you have made a retrieval of all of the fine detail values in a column from a handful of radiances that really aren't sensitive to that level of detail. And so you have to compensate, you have to accurately represent the uncertainty in order to not to bias or over fit the result. But anyway, that's all I wanted to say about the original motivation for what we're doing, because it's true that originally that was what I had set out to do, is to write the forward sensitivity and represent it in a way that is useful for assimilation. But the result has been quite a bit more and useful in many other ways for weather and for climate. And that's what I want to spend the rest of this presentation on. In addition to this operator, which is okay, it's viable, it's a viable option, comparable to others that are being used. The approach is producing an objective retrieval of both of these quantities, the condensed water structure and the water vapor in the cloud. And that's important because, so far, nobody has been either producing this or using it in any way. And what it means is that, well, practically, what does it mean? We can estimate things like, so these three different things. The first one is the different thresholds of height. So how high does a mixing ratio greater than 0.05 reach inside the cloud. So presumably, this threshold, this height, the height at which we have condensation that is this high, will probably be higher than the height at which it's above 0.1, and which is in turn higher to the height that's above 0.2. And these quantities are probably not independent of one another, but we can estimate them. We should be able to estimate them with this representation that we have. And in fact, it turns out that we can. I'm going to show you how that works. And that is useful. After I show you how it works, how well it works, we'll see why it is useful. You can also look at the vertical principal components of condensed water. The first one is basically just an integral of the water, of the condensed water concentration above the freezing level. And the second one is basically the difference between however much is above 9 kilometers and however much is below. This one, the higher its value, the more water you've got condensed in that cloud, in the upper level of the cloud, above freezing. And this one, the more negative means the more of that water is in the lower upper levels, versus if it's less negative, then it's more of it is in the upper portion of the upper levels. And this is, and also I showed you that we also have sensitivity to the humidity, the remaining moisture in the cloud. And let's just go straight to an example of how, so this is one case where not only did I have many radiometers that, so I'm showing you a few of the radiometers. I also have SSMIS and MHS, but it's okay. So this is what that very same scene that is over Tropical Cyclone Winston looked to the different radiometers and how the different variables looked almost, not exactly at the same time, but at closely separated times. So these two panels go together, these two go together, and these two go together. Here, you're seeing that same tropical cyclone, but about 2 hours away, well, sorry, 1 hour away. Saphir saw it 1 hour earlier than GMI saw it. And so you recognize, of course, you're not going to get an ideal picture, but this is an estimate of the height of this quantity, H02. So the maximum height, that a condensed water concentration that is greater than 0.2 grams per cubic meter is reached. And as you can see the features, I mean, you can see the vortex quite clearly. You can see the wall, the rain band. They don't look all that different. It's very plausible that over an hour, that's what the evolution would have been. Here, what you see is the effect of the two of the thresholds, the lowest one and the highest one that I have. And so you can see that the highest that this kind of concentration reaches is almost always, well, it's always lower than the highest that this concentration reaches. Not only is it highest, but the area that's covered by this level of water is bigger than the area that's covered by this level. So, I mean, in other words, there is a lot of information that is could not have been guessed, even though they are related. But it illustrates the usefulness of having these quantities, which can be estimated from all the radiometers in the constellation that we have today. And this is the last one that's, I think, interesting in its own right. It's showing the vertical principal component. The first one, sorry, this is, again, no, this is just the height. So this is exactly the same image as this. 1250, oh no, it's not the same one. Okay. It's not the same one. But 1250, it's the following pass. So it's GMI when it came on the next pass, which was about an hour later. And this is the first, this is the height, and this is that second principal component, which is a difference between where most of the water was in the lower portion of the upper level of the cloud, which is all the dark blues, and where more of it was in the upper portion, which is closer to the eye wall. So they're not entirely independent of one another, but you couldn't blindly guess this from this one. And the point is that now, you know, you can obtain all these structural descriptions that are not the surface rain from the radiometer constellation. Okay, great. So what are we going to do with this? Well, there are two things that were the first things that I'm interested in doing with it. The first one is to sample over climate scales, to sample storm heights and track their evolution over the past 2 decades. And I will get to that one first. And then we will look at how this information about the structure under the cloud can be merged with the geostationary IR in order to produce a better performing nowcasting system, where you're not going to be running a detailed cloud, atmospheric model. You're just going to rely on these observations, either just the geostationary by itself or geostationary with this microwave-derived information in order to perform the nowcasting of how convective storms are going to evolve. So the first, storm heights. So why are we interested in, what does this have to do with storm heights? Well, as I was saying at the beginning, my group is called Radar Science, and we're supposed to be figuring out how to make the most out of microwave observations. And one of the things that was observed, that was a question that I was actually criticized for not having done anything climate with ocean with the scatterometry, ocean wind measurements, estimates, is, so the first thing that we tried to do was to see if there was any signal about the evolution of the Hadley circulation over the past couple of decades. So here we're just looking at 1 decade at a time. And how would you try to look for, well, how did we look for a signal that is specifically tied to the Hadley circulation? This is a composite of 10 years worth of ocean wind estimates, near surface 10-meter wind estimates. And what you're seeing here is just the zonal component, so U. And as you see in the tropics, it's dominated by the trades, so you got negative U. And then extratropics, you've got the westerlies, and so you've got positive U. And there's a transition from the negative to the positive in the in the northern hemisphere and in the southern hemisphere. So, and it's happening around 30 degrees. So if you take this number minus this number, that difference between those two, and you average them zonally, you'll get some number that's about 60. And so from the estimates that are made by the scatterometer, not averaged over 10 years, now we take them 2 weeks at a time, you can do, you can look at the time series of the evolution of this difference. Has this difference been steady around 60, or has it been getting bigger or smaller? What has it been doing? And this is one way of looking at it as a function of latitude. So the purple or the dark numbers correspond to the beginning of the 1999s, of the beginning of the 2000s, the zeros. And the warm colors are the end of that decade. And as you can see, at the beginning of the decade, the 2 latitudes, the 2 zero crossings were closer in than they were at the end of the decade. And this is a plot over the 10 years of what they did. I have 2 plots here because one of them is the direct observation, and we just for verification, we took EC's estimates. The European Center assimilates these estimates, so it's not surprising that it should parallel this, but we haven't really gotten a resolution of why we have a slight discrepancy in the amplitude. But when you do the global zonal averages, you do see a signal. And it's not perfect, and at the beginning of the decade, it's like, well, how much was this, 1 degree per decade, 2 degrees per decade? It's a little bit clouded by the fact that this is only an ocean measurement. This is all measurement. I'm not a modeler in any way, and so we're just trying to get these things from observations. And unfortunately, we have many areas where, well, unfortunately, the globe is not, we're not symmetric here, and the best hope of getting some good signal would be over the Pacific, where the continents don't come in the way. And when we redo this by looking at only the Pacific, which is just that zone, then the signal becomes, well, there's a big amplification of the La Nina at the beginning of the decade, but then after that, the trend becomes a lot more obvious, both in the actual observations and in the European centers. I'm toggling back and forth just so that you can see it. And so, of course, the obvious question is, what has precipitation been doing? And we had pointedly actually asked Graham, well, what is precipitation doing? And it's like, it's not really clear that anybody knows what it's doing. So I figured, okay, well, let's try to find out, again, from observations. So we're not, there's no modeling here. So from observations, what is it doing? And so what you're seeing here are estimates from the TRIM radar of the cloud top heights, the mean cloud top height in different regions. So not knowing how local, ideally you'd like to look at the evolution of that cloud top height. And this is cloud top, not in the sense of like the highest cirrus or these are the clouds that can be detected by the TRIM radar. TRIM radar is not very sensitive to anything that's not, you know, a substantial amount of condensation, on the order of 0.1 grams per cubic meter. So these are really storm top heights. And so what you want to see is, you know, can I get an idea? I wanted to get an idea of the actual probability distribution of the storm top height locally over small regions, and look at its evolution over intra-annual and interannual. And I had asked our postdoc to do it, and you know, he politely did something, not quite a distribution, and then I figured out why, and I'll show you why in a little bit. But at first he did just the average. So this is what you're looking at, is the mean storm top height for these different regions. So these are the different regions. These are degrees of latitude. And in this one is just for the North Pacific. And what you can see is what I'm charitably calling a mostly positive trend in the Northern Hemisphere summer. I mean, the trends, these are the slopes of the best fits to the curves. And you do have a positive trend, but away from the equator, which is very interesting. And what it indicates, I'll get to the interpretation later, but what it does indicate is that the heights are getting higher, but not, you know, right at where you would expect the ITCZ to be. And then when we look at a different box in the Southern Hemisphere, then we get positive trends for all, you know, just pretty much everywhere. And when I asked, well, why can't we can we please do the histograms like I wanted? And I wanted actually smaller boxes than this. And this is where I realized what the real problem is. This is the counts, actual, how many data points there were. So this is the number of data points that went into doing the mean, the statistics. And you can see that, you know, with 100 samples or 300 samples, I mean, you're not going to be able to give me a distribution, especially knowing that when you get one sample instantaneously, you're really getting about 40 or 50, because that's how the radar, I mean, the radar just has a pass and it collects a whole bunch of data and then it doesn't come back. So when this is showing 300, basically it sampled a handful of storms, 3 storms in that area. And based on that, you're not going to have very good statistics for what the trend is over a decade. So what you'd like is at least an order of magnitude more data to be able to do this. But the radar isn't going to provide that. I mean, we're already very lucky that TRIM had a tropical orbit. GPM has a much more inclined orbit, and it gets even fewer counts, assuming that it has the longevity that TRIM has. So to counter that, the best hope that we have, and I'm still trying to cross-calibrate the sensitivity, because the radiometers don't have the same sensitivity. The constellation of radiometers provides about 50 times more data than a single radar. And so with 50 times more data, then we can try to do a distribution, and at least if not a distribution, we can try to get the curvature of the cumulative distribution and see the transition between the shallower storms and the deeper storms, and see if the deeper storms are getting deeper or more numerous, as the indication seems to be in these signals, which are based on a very tiny sample. So that hasn't been done yet, and that's actually the reason I wanted to mention this, is because it's an opportunity if somebody is interested in working on the problem in a novel way, because you'd be using observations that are obtained from radiometers that are very sensitive to them, but that nobody else is using for that purpose, describing the storms. And the second application, which is in process, and I will just show you one demonstration, is to the analysis and nowcasting of severe convection. So right now, just about all the operational agencies have systems to try to forecast the rapidly develop. So there's different names: are rapidly developing thunderstorm, rapidly developing convection. They basically using infrared, geostationary infrared, because it's available very regularly, frequently, and it is sensitive to the height or to the temperature of the cloud tops, which is an indication in the tropics of depth, but not exactly. But you know, it's a proxy, and that's what's being used. There are essentially 2 different approaches to taking these time series of infrared observations and turning them into diagnostics of storms, and therefore then later nowcasts of storms. One of them the broad categories, this is my nomenclature, so I don't know that everybody agrees with this, but when you look at these methods objectively, one of them is an image overlap method, which consists in delineating all the portions of the IR data that are colder than a certain threshold. 235K is what's used by, well, at least the two that I have looked at. And then you look at the connected components in 2 consecutive images, and you look at intersections, and you track those intersections over time. And based on what intersects with what, you call it a storm or a squall line, or it's a separate storm or a separate squall line. And when you don't have any cold cloud tops, you get nothing. Fine, that's one way. That's the image overlap, just consecutive pairs of consecutive images. The other one is broad technique. It's implemented different ways by the CMA, by China, and anyway, but the different agencies have different versions of this, but those are seed and grow. Basically, instead of looking at connected components and how they intersect, they look at the local minima of the temperature, and then they grow connected components out of the minima, not instantaneously and not with just 2, but with at least 3 consecutive images, so that even if there is no cloud top that's very cold on an image, you can still have it produced, because at the next time step it did become cold. The areas tend to be very similar, the ones that are detected by one method versus another, except that how they're classified, I mean how they're identified is different. This method tends to, these methods tend to identify more, yeah, we'll skip the explanations. They tend to split a line of squall into individual squalls, where the other one tries to group them. And it's for that reason, this is another case over Brazil, this is one of the reasons why we decided to just implement this and to try to merge the microwave into this method, because it seemed to me that if you're trying to forecast or to nowcast the growth or failure to grow of an MCS, you would want to take into account the organization of the whole system, not just of the individual pieces of it. And the nowcasting is going to be based on the very simple notion that if I build a large history of these storms, so I build an archive from the past of the evolution, the time sequences of all of these IR delineated storms. And I can learn, therefore, from these that if I now observe this portion, I can, by comparing with the archive, I can try to forecast, well, what's the next size going to be, and how the size is going to evolve. And from the history of evolution of, say, the centers, you're going to try to forecast the evolution of the centers, the direction, the orientation, so forth. The method, when you just try to do it based on IR, so this is what this diagram is trying to summarize, there's different ways of obtaining this function f, which is trying to forecast the IR size based on the history of IR sizes, or the IR location based on the history of locations. You can try to do many different things. Regression gives you an okay answer. It doesn't work very well. And so the idea now is, if in addition to this IR, I actually had a microwave pass, which I have very frequently, radiometers come over any point about once every 80 minutes, then by inserting that, instead of just basing my regression on the IR, I ought to be able to do better in the forecasting. And so this is my last slide. This is the test that we did on 2 years worth of data, either with or without Saphir radiances. What you're seeing here are the half-hourly time steps into the future. We tested it on half of the data that we did not use for the training. And what you're seeing here is the correlation of the nowcast size versus truth, without you lose skill very quickly. But with the microwave, you're doing not too badly even after 2.5 hours. And what's perhaps more interesting is that the error does not grow in time, no longer grows in time. It is normalized error. So that's it. This is the invitation for all my visits to India are recruiting drives, sort of. These are the problems that I basically touched upon, and I would be very happy to work with whoever would like to work on this. A lot of it is going to be labor intensive. So the derivation of the formulas or practically computable relations, sensitivity between the microwave radiances and the structure of condensed water and water vapor can be done in a semi-empirical manner. The results can do fairly well, but we can improve them if we use machine learning for data assimilation. We can use this to look at the climatology of convective storms, which we haven't done, but it's really the only hope to do things empirically, because radar simply doesn't have the sample size that would be required. And we're launching actually now a full-scale implementation of the nowcasting system. We're having our meeting in February, to which actually somebody from IMD, she's one of the main motivators for this application, will be participating, Suman Goyal. So anyway, these are 3 opportunities that I would be very happy to collaborate with our colleagues here on, or their students. Thanks.
Okay, thank you very much, Dr. Jad. So, if any one question, burning questions or comment? From youngsters, because he posed the problems for the
So while
youngsters.
comparing with the GPM reflectivities, how can you distinguish the hydrometeors? Because GPM only detect reflectivity more than 10 dBz, and we can't say which one is which. So when you're comparing with the GMI, we used cloud water and water vapor. So
No. There's no water vapor.
Okay.
We're only looking at the condensed water. You're absolutely right. That's the reason to do the two separately, is that the radar cannot tell me anything about the water vapor, and I am not trusting anything the radar is saying about habits or about species or about anything like this.
Yeah.
In fact, there's no point in trying to pretend that the world is made up of either, pristine ice and graupel, and you know what I'm saying. But there is every reason to believe, because that's what the models do show, that the signature is coming mostly for the radar from the condensed water, depending on assumptions about how it's distributed in size and all, definitely. But and there is room for improvement. But we're only relating it to the content of the condensed water. The water vapor is coming from comparison with model simulations of the residual. That's why we had the 2 steps. So when I showed this here, so this is done in 2 steps. This way. First, we pretend that this comes from only that part. I'm ignoring this part, and I'll get this by fitting with radar, and just by looking at the precip, just the condensed water. That's all. That's the condensed water part. And then I subtract this from that in simulations, and I compare the residual, that difference, to the water vapor from the model. I'm not trying to.
So here it is like background you are providing through that HS kind of.
This is the background. This is the mean. That's basically a debiased mean, that's coming from the GPM, from the radar, yes.
Okay.
And then the rest is coming from simulations.
Okay, and
Okay, thank you
what
very
about, just one question, sir. So you using this GPM, so is there any possibilities of assimilating the GPM reflectivity also, because it has a beautiful vertical structures?
Yes.
So any work is going on that?
Assimilating which again?
GPM reflectivity.
Yes. So there's different people that do it. You have to be careful. So the reflectivity is not necessarily going to be very easy to assimilate per se, because it's mostly sensitive to the condensed water, which is not necessarily the variable that's most coupled, that is coupled in the best way. In other words, so assimilation has 2 pieces in it, right? There's the observation together with a quantitative evaluation of the error in your representation of the dependence of the observation. But then there's also the background covariances. And the background covariances carry a very heavy burden, because they are the ones who are going to be, you're relying on that representation to translate any adjustment in one of the variables to all the other variables in a dynamically consistent way. The precip variables are not well coupled. I don't know of any covariance, or not just covariance, ensembles don't do it by covariance, but I'm saying there's no reliable way of coupling the 2. So yes, there are ways. At JMA, the Japanese, I think they have a very nice set of approaches. First, because the problem is not Gaussian, you have to relocate it's a slew of issues that I can talk to you offline
I think
about.
this can be discussed.
I'll meet you in the afternoon.
Lunchtime maybe.
Yeah, by lunchtime I'll
We are
meet you.
across the time, so thank you very much, Dr. Jayad. And our next presentation by Professor G.S. Bhatt from Indian Institute of Science, Bangalore.
Very pleased to be here and thank the organizers for inviting me. But this topic is different from what we have been talking about, tropical cyclones or other extremes. But there is an element of extreme here, but it looks at the wind that occur away from the coast. So therefore, it's not related to cyclone, but something else. I have Srinath Palleri, he helped in collecting the data, and she was a summer intern who part of the data analysis, and would like to acknowledge the MOE Monsoon Mission Program. It is a part of the MOE's Indo-UK collaboration that helped in collecting the data which is used in this analysis. The motivation for this came from one day's devastation that happened in Bangalore last year. On 24th April, there was gust wind in Bangalore. And this is a report from Times of India, which is 26th April 2018. It said that heavy winds on Tuesday afternoon brought down 111 electric poles in west and north Bangalore. And you know, in a city where electric poles are brought down, there won't be power for the next several days. And without power, you can imagine the urban life. And that's what happened. And so essentially, there was no loss of life here, but it certainly was cause of a lot of misery. And I got a call from NAL saying that they had installed one test wind tower windmill in southern Bangalore, and that blade of that wind tower broke on that day. They were interested in knowing what was the wind speed and why it happened. And there was a glass dome of a shopping complex. These days, you know, you have nice shopping complexes, and they make things which look very appealing. And for that, they use glass. And because of this, there was a crack in one of these domes of the windmills. Luckily, it didn't fall down. If had it, people would have more injured. And essentially, such wind caused gust wind kind of a damage was not heard in Bangalore earlier. But this year, again, there was some devastation. So it seems to be there is an element of climate change built into it. And again, last year, May 2018, this is a report from the Washington Post. It was a nightmare. Killer dust storm blasts India, leaving at least 125 dead. You know, that's happened in the North Indian plains. And another report on 8th May, at least 124 people were killed and more than 300 others injured. So now, if I compare this with the injuries or loss of life which is caused by cyclones, in fact, this number is much higher because we had severe cyclones in the last 5 to 10 years, but we never had that kind of a loss of life. And therefore, the thunderstorm and dust storm, they have not received much attention, but when you compare to the loss of life now, also to the property, in fact, their contribution is not at all small, but I don't see much attention is being given to this problem. And yesterday there were talks on predicting the tropical cyclones, both intensity as well as the track. And in fact, IMD, I would say India, because Dr. Sahai made a presentation where IIT also developing, predicting this tropical cyclone tracks, has good success in predicting track of Bay of Bengal and Arabian Sea cyclones. And loss of life due to these cyclones is almost zero now. Means there are few cases, but where that is negligible. And in this study, I'm going to look at gust winds over land, which are unrelated to cyclones or synoptic systems. It is very localized, and what is their nature. The motivation is that there are many parts of India experience extreme gust winds and dust storms during the pre-monsoon months. Essentially, mostly it is April and May, it is during that period this occurs. And these events do cause a lot of damage to plants as well as properties, and sometimes also cause deaths. In fact, if you look at the 2018 season, more than 300 people died in India. And despite their annual recurrences, their physical nature, for example, temporal and how long they last and what the actual wind speed, and the mechanism that remain unaddressed in the Indian context. And it is a work in progress. I started looking at this data because Partha invited me to give a talk on extreme, but I don't work on that. I thought maybe this is a good topic to discuss here because that's something which has been ignored. And so I'm going to present 2 case studies of pre-monsoon damage causing extreme winds, and also look at triggering what is their nature and triggering mechanism. And the approach is, it uses in situ observations plus INSAT 3D infrared channel imageries. So it has IP4 has prediction of extreme. So what I'm going to use is there is something to do with the extreme, and it is a number is assigned based on some population distribution. Like for example, you have top 0.5 of the values. You have to prescribe a threshold to define an extreme. And as part of this Indo-UK program, we had installed flux towers at 7 locations: Bangalore, Dharwad, Navagam, Jaisalmer, and Kanpur, Samastipur in Bihar, and Bhubaneswar, spreading across the country. The ones which are in red color, they are by my group, and the one which are in blue by Center for Ecology and Hydrology, UK, our partners who installed that. And this is how a typical mast looks like. That we at a height of about between 8 and 9 meters, we had this sonic anemometer, and it sampled at 20 hertz. That was the advantage of this system, that we could measure wind speed at very high speed. That is a very reliable system, and the measurement height is about 8 meters. And looking at the wind statistics, what is shown here is the wind speed versus the frequency. And this is based on the data collected in our campus in IISc at a height of 10 meters. Again, it is an AWS, not that flux tower data. So it is the average is 1 minute. So data averaging period is 1 minute, because this is very important when you look at extremes. And if you look at the average wind speed in Bangalore, the mode is somewhere between 1 and 2 meters, okay, very low. And in fact, when you look at these numbers, so what you see in green line is the cumulative probability distribution. By about 5 meters per second, more than 99.9% of the cases are over. And this is the case of Jaisalmer now. This is looking at 1 second average. Earlier on was 1 minute. Again, here too, if you look at the distribution, we see very small number of points, about 10 meters per second. And if you expand this tail, and then if you see this is for the period of 2017 April, is that a few cases which exceed about 20 meters per second, very small numbers, okay, very few numbers. And incidentally, this Weibull distribution is a good approximation to the speed distribution of this wind speed measured at both the places, Bangalore and Jaisalmer. And only at the high extreme ends, there is some departure. So if I just look at the top 0.01% of the wind speed, this is at Jaisalmer in the month of May, it starts with somewhere around 14 meters. So the threshold of 0.01% is at 14 meters per second. And this is it's kind of gamma distribution fits it fairly well. And in case, when you look at May, again you see very small fraction of cases which exceed even 24, 25 meters per second. But those are very, very few, small in number. So if I go to the definition of extreme now, at Bangalore, 1 minute average, 99.5 percentile is about 4.7 meters per second. And top 0.01% cases is about 8.9 meters per second. So in the statistical sense, even a 9 meter per second is extreme at Bangalore. And at Jaisalmer, 0.01% threshold is based on the 1 second average, it's about 14 meters per second. So these are extremes, yes, because by going by just a statistical measure, but they don't pose any danger to life or property because they are about 10 meters per second. It is not such a damage causing. So therefore, one has to distinguish between extreme in a statistical sense versus something what can cause danger, because everything which is extreme need not be damage causing. So now I ask the other question, right, is that what wind speeds start affecting us adversely? Okay, that what starts our normal life. And again, we search the Google, there are so many suggestions of these things. So now this is what I found, is that branches will start falling somewhere between 60 to 75 kilometers per hour. That is the speed at which trees start feeling this wind. And anything which is about 80 kilometers per hour or more, they start calling it gale winds. And it can knock down people if they are not holding to some support. And 20 meters per second, because so far I have been talking about in meters per second, and here these numbers are in kilometers per hour, just to get a connection between the two. 20 meters per second is 72 kilometers per hour, somewhere in this range, and 80 is 22.5, that is this range. So for this work, anything wind speed which is around 20 meters per second or larger, we take it as extreme. And if we associate physical damage to trees and structures as well as discomfort to people and injury to people, that's what they should take that. And how does that this wind speed data look like? Again, this is 1 second average. The data is, this is from the IISc campus, starting from the early morning of that day, it goes up to about 20, that's 8 in the evening. And this is the time when the actual gust wind came. So if you look at the pre-gust event, so this is 2 meters per second, there's 2.5, there's hardly any wind at all. Suddenly you see a spike, and again there's a calm, it prevailed. And on the top of that, I have also plotted 10-minute average wind speed. If you see that comparison between 1 second and 10 minutes, so there's a big difference between the two. And this is the vertical velocity. Especially when it comes to vertical velocity, you take 10 minutes average, there's almost close to 0. Even when there was this gust wind, you could see there is a small spike. But when you look at 1 second, it reached 5 meters per second. That is the turbulent fluctuating vertical component of velocity. And this one, sonic anemometer measures the virtual temperature. So that's in magenta line. And if you take the 10-minute average, again, you see this line that fits fairly well. And this data is from Bangalore. So next one, I'm going to show from what we saw in Jaisalmer. This is all 1 or 2 case studies. This is, if you look at the time when it occurred in the afternoon. So this is occurred around the time when land surface temperature normally peaks. That is the time around between 1:30 and 2:30. That's the time when it peaks. That's the time when it occurred. That's important here. But when it comes to Jaisalmer, I was thinking that the ones which occur in the afternoon, they're the ones which cause this gust wind. But here it starts around 8 in the evening, goes all the way up to about 6 in the early morning. This is the time of 7, 8 May. Remember, about 120 people got killed on this day. And at around 9:30, there was this thing which touched about 20 meters per second, and then it decreased. Again, in the early morning, around 3:30, again there was another gust wind. This exceeded 80 kilometers per hour. So in northern plains, you do get these gust winds even at night time. It's not just the daytime. Again, if you look at the velocity distribution, 10 minutes average, you hardly see any this thing. I'll tell you why I'm talking about this 10-minute average and 1 second average. But 1 second average, again, you see a lot more turbulence. And every time you have this gust wind, you see a rapid drop in the temperature. That's very important. So in the same night, you had 2 extreme winds. And this is in Bihar, which is on the other eastern Indo-Gangetic plain. And again, if you see, the winds were about 5 meters or less till this event occurred. Again, it occurred in the afternoon here. This is the Julian, that's the day of the year, 97, that is the 7th April. And again, you see, it has gone up to about 20 meters per second. It lasted for a very short duration. I'll come to that time again. and associated with that, again, there is a big drop in the temperature. So if you have to look at the broad inferences from all these ground observations, is that the flow is highly turbulent, highly fluctuating. That is the first. In fact, if you look at 1 second average and even 20 hertz, this thing, there is a lot of turbulence you can get. And duration of this extreme wind is almost always less than 10 minutes. In fact, if you look at the most intense part, it lasts only from 1 to 5 minutes, not more than that. In fact, 5 is also on the higher side. And it is accompanied by a decrease in air temperature is of the order of about 10 degrees centigrade, the magnitude varies. And this 10-minute average completely underestimates the gust intensity, because one is more than 20 meters per second, the other one is almost about 10 meters per second. Remember that routine synoptic observations, they mostly are most likely to miss because they are programmed to report 10-minute averages. Sometimes they report half an hour or 15 minutes or even 1 hour averages. So if you have an AWS, if it is reporting this wind data, obviously it will underestimate the actual wind speed. The next question is, what drives these winds? The key to that is this diagram. So what is, again, this is a Bangalore, starting from 6 a.m. in this thing to 20, that is the evening 8 o'clock. And this shows the moist static energy, 340 to 360. So the value was hanging after about 8, 9 o'clock between around 355, 360. And this is the time when the gust came. When you see this, there is a rapid decrease in the moist static energy, because normally moist static energy is conserved. A decrease clearly pointer to that there was a downdraft. Okay, that is the first information. You can look at this. This is the relative humidity. It was around 35%. It shot up to almost close to 100%. That is so there was precipitation there. And this is the actual air temperature, and this is the wet bulb temperature. So the minimum temperature normally you get when you cool air is wet bulb temperature. But in this case, we went below the wet bulb also. The contribution came from the fact that there was a decrease in the moist static energy due to the downdrafts. So therefore, the line in the green is the specific humidity. So specific humidity is high. Again, it decreased. Again, it picked up, because once there is rain, evaporation, it adds to it, recovers in a period of about few hours. That's all we need. So what is plotted here at the bottom in this small thing is the rain, 1 minute rain rate converted into millimeter per hour during that. This is the scale there. See, at the time when you had this heavy precipitation, this gust wind, you can see the rain rate exceeded 200 millimeter per hour. And I think that is a critical component of this one, is that moist static energy decreased from about 360 kilojoules per kilogram to about 340. And moist static energy is conserved quantity in moist adiabatic processes. The fact that there is a change of about 20 kilojoules per kilogram clearly points to that there is a strong downdraft. That's what this one. So evaporation of raindrops decreases the air temperature, but the resulting lowest temperature is the wet bulb temperature, TW. The fact that you have downdrafts, it decreased TW further by about 4K compared to pre-gust conditions. So this also added to creating a much stronger cold pool. And if I look at the case in Jaisalmer, we don't have that many detailed observations. There too, this is the moist static energy. Again, it slight decrease and went up, because the starting value itself here is about 325, 330. So it's a very dry place. There is not much scope for decrease, but by downdraft. So again, evaporation increased the moist static energy. Again, you can see the increase following that. So this one is the water vapor concentration. Following the gust, there is an increase. It is a clear indication that there was precipitation. Okay. And so sharp decrease in temperature. So it is a cold pool, cool is present. So increase in vapor concentration points to the rain. That's all I could make, because that rain gauge there, it was measuring only daily rainfall, not this one. So if you have cold pool, this is a dust storm, for example, then it is there is horizontal gradient in temperature, which leads to density difference. So it causes this gravity current And if you have gravity current, then your gravity speed is proportional to, that the h is the height of the cold pool, then TE minus this environmental temperature ahead, this is the cold pool temperature, this TC by this, so you multiply it by acceleration due to gravity. This K is an empirical constant, values vary from 0.7 to 1.45. If you assume K to be 1, for delta T is 10 K, use 20 meters per second, you need about cold pool height, which is about 1,200 meters. That's the height of this thing. If delta T and wind speed are related, if I get a plot of these two on different years in Bangalore, there is some relationship, but not one-to-one. The reason is that this height could be variable, because we have no, it could be, because we have no idea of what the actual height of the cold pool is. That could be one of the contributing factors. And the next question is, if the cold pool is there, it lasts for about an hour. But why this duration of maximum wind is so short? It is of the order of a minute or even less fraction of a minute. And to understand that, so this is a simulation which is a numerical simulation of thunderstorm outflow taken from Drogemer and Wilson, this one, is that there is a cold front, this is a warm here, this is the cold front, and the maximum wind speed lies not near the surface, but at a height of about a couple of 100 meters above the surface, because the friction slows it down. And here, the maximum wind speed, what you see here, is about 24 meters per second. This is comparable to the kind of wind speed that we had. And so driven by the falling hydrometeors and downdrafts, so with the intense precipitation, jet core, which is there here, it gets pushed to the surface. And because these hydrometeors are falling and the downdraft is coming, the jet core gets pushed, and it is this high momentum air which is coming to this one, that is the one which is causing the sudden gust wind. And as long as we have very strong precipitation, that lasts. But moment that high precipitation is over, again the ground friction takes over and you don't get that this thing at all. So there is a strong link between the strong precipitation rate. And therefore, the damage caused by the gust winds is disproportionate to their, in fact, short duration. And most intense gust time coincides with the heavy rain rate of more than 100 millimeter, because this is looking at other cases too. Perhaps the downdraft momentum of falling raindrops plus the water loading, because once the precipitation, it falls on the tree, it holds them, plus strong vertical velocity, plus turbulent added to that, along with the momentum which is transported by this, that may be responsible for causing this falling of tree branches, even when the exposure is so short. And this is one example of when the precipitation rate is about 100 millimeters per hour, then the kind of drop distribution that we have, this is measured with a 2D video distrometer. And so when you have rain rate of more than 100 millimeter per hour, then there is hydrometric concentration is quite high. You know, that's what the total water adds to that and the momentum. So are the gust winds predictable? That's the next question. To do that, we try to look at the satellite pictures, because what we had was only point measurements. So this is at a time when we got the gust wind near Bangalore. This is the INSAT 3D imagery. So this is the coldest cloud. What you see is, this is the point where we have the AWS is away from us at that instant. And if you look at the contours of 220 and 210, these are taken at different 7:30 UTC, 9:30, and this one. Our gust came somewhere around this time. Okay, so if I look at this red and magenta, and this is the point where we measured that, you don't see any magenta where here at all. This is the Bangalore, that AWS is located here. So the time when the gust occurred, an hour before, there was no sign at all. So this entire convection developed within a span of less than 1 hour. And you don't see any large cloud system. Only after that, you do see, this is after that gust is passed over that area, it is spreading towards southwest toward of that location. And this is the case with Jaisalmer, and this is the point of measurement. The gust is moving like this. And again, it's color coded here about 1 hour before the event. You see that there are two contours are there. One is 210, the outer one is 220. So there was a cloud system present even 1 hour before. And the one which in the gust came is this color, that was there. So therefore, there was a well developed on at Jaisalmer on 7th May. Even first event when it came, there was a propagating mesoscale convective system. The second one came around 12 UTC. When you look at that data, again, about an hour before itself, there was a MCS, which is more than 100 kilometers in one side. So that was a mesoscale system. It was propagating rapidly from west to the east. And so it was a well-developed MCS was present there. So when it comes to these observations, at Bangalore, gust winds started at around 2 p.m. Deep clouds developed in less than 1 hour. Driver in the cold pool intensity, delta T is of the order of about 10 K. In fact, Bangalore it was 15 K. All cold pool cases of about 10 K intensity, they do not result in gust. That's one has to remember that whenever you have that 10 K, no, it won't lead to gust wind. There was no clue from satellite IR data about the rapid development of associated convection. In fact, 1 hour before, nothing in the satellite imagery of a deep cloud at all. In fact, I thinking that a radar may help in trying to, especially if you are looking at trying to predict such gust winds, the radar may be needed. And nowcast using a numerical model, I don't know, there are more experts in this audience. You can talk about this kind of an event, whether you can do it or not. And at Jaisalmer too, gust is due to a propagating deep convective cloud system. And both at 11:21 IST on 7th May and 3:30 IST on 8th May, there were eastward propagating deep clouds at least a couple of hours before. So it was a well developed and propagating system. And this gives hope for nowcasting of gust winds here using DWR or satellite data. In fact, they last for several this thing. And no strong correlation between delta T and gust winds speed U. Lack of information on the height of that cold pool could be the reason, because we don't have any information on that. At the locations where 20 hertz winds data are available, thunderstorm driven gust intensities are always less than 30 meters per second. But an important concern in a warmer climate is the possible increase in the intensity and the frequency of gust wind over land, and will the maximum wind speed become more than 30 meters per second? We don't know what this thing. So that's it. Thank you.
Thank you very much. Any question, queries?
A very interesting talk. Thanks, Bhatt.
Thank you.
My question is, how many of these gustiness events, of course data is sparse, so but were related to some kind of thunderstorms which happened in that
No, all these are actually, I have not used the lightning data because that would have told me whether that's, because invariably if you have afternoon wind like this with precipitation, invariably it is accompanied by thunderstorm. Yeah, most of the thunderstorm, thunderstorm. But it is a MCS, means I won't say MCS, but there is a deep cloud system, yes, it is there. Right.
And they were predominant in the post-monsoon or the pre-monsoon?
No, pre-monsoon. Because I looked at post-monsoon as
lots
well as
of
monsoon
thunderstorms
season.
in Bangalore, but
yeah, no, only pre-monsoon. Because even at all the places where we have AWSs, we do get strong winds. In fact, but they are related to monsoon systems.
Okay.
Yeah, it is not this one.
So this is basically pre-monsoon.
Yeah, very localized and short time duration.
Yeah. So I think we'll close here. And there are 5 very interesting talks by 5 dignitaries, and let us give a big clap to all of them. Is there any question left? Yeah, please. Yeah.
Just one small comment. The reporting, WMO reporting practice on gas is a 3-second average. If they are reported on the WMO. And in these cases of mesoscale convective systems, do you have a strong shear? Is it with a strong low-level jet you have the strong gust, or better correlated than with the precipitation, or not?
My guess is that when you look at the cold pool, because you have temperature gradient a difference of about 10 K. So it has a strong shear, but that's elevated a few hundred meters above the surface. Only when you have strong downdraft and precipitation coming down, that's able to push it near the surface, and when you get those most intense gust wind. Otherwise, the normal, if I look at on either side of that peak, the wind speed, even 1 second average, is in the range of 10 to 15 meters per second. Because of the friction which slows down, you don't get that kind of strong intensity. But when there is strong precipitation, in all the cases, at least in Bangalore, I have detailed data of precipitation because we measure there, that whenever there is a strong, intense this thing, but it's very short duration. Moment you have that intense rain gone, more than 100 millimeter per hour, that this thing vanishes.
Just a short question.
Yes.
You have identified a mesoscale system associated with this.
Right.
But can you then say seeing a mesoscale system? Because there are many, many mesoscale systems that come in April.
Right.
So is there any distinguishing feature of the mesoscale system which gives you such gusts?
Yeah, no, actually, right.
Unless
Yeah, it is a good question. See, as I said, that one is the cold pool. That is a necessary condition, but not sufficient, because that low level jet in the cold pool is not near the surface but elevated. Unless you have strong downdraft and which is related to this heavy precipitation, that will not push to the surface. So therefore, in many times, even when you see in the cities, these damages are highly localized. I think only in areas where you have this, when you look at these convective clouds, you have shaft of heavy precipitation coming down locally, but it's not there. So even when you see the cold pool spreading, but damages are highly localized. So when you have this strong precipitation reaching the ground, there the damage is more. But in places where you don't have such high precipitation, gust is there, but it is of the order of 10 to 15 meters, not this core. Yes, you need detailed prediction of where the core is.
That is very difficult.
And also rain rate, it has to be high enough.
So, okay, with this, let us give a big clap to all the 5 eminent speakers today morning. And we are already late, so I think.
Thank you, sir. Thank you. We are just ending the pre-lunch session. So I kindly request the chairman of this session, sir, to hand over a small token of appreciation to Dr. Ziad Haddad. And to Dr. G.S. Bhatt. Professor G.S. Bhatt. Huh? No, others, they have already got. We break for lunch right now. Lunch is arranged at the basement of this auditorium, and we will assemble here at 2 p.m. Thank you.
so we developed such a rainfall retriever. Especially my part is a passive microwave radiometer, but overruns the primary source of rainfall retrieval, primary error source of rainfall retrieval from satellite microwave radiance measurement is a vertical structure of precipitation. This is example, again, tropical cyclone Oki, vertical structure observed by GPM, dual frequency radar. You can see such a AB cross section. And this is heavy rainfall, but not so deep, relatively low, at least lower than 10 kilometers. And the rainfall algorithm implicitly assumes that the deep cloud with active cold rain processes are more likely to produce heavy rainfall. But sometimes the warm rain processes was found to be frequently responsible for such heavy rainfall events. It's leading to underestimation satellite algorithms in heavy rainfall cases. Next slide is more very clear case. It's yesterday Tao-san already told this case, Typhoon Marapot case over Taiwan. Many people died due to this typhoon case. And this is topography, and this is Turin precipitation radar. Its radar is very accurate over ocean and over land. So radar capture heavy rainfall in this mountain region. But this is microwave radiometer. Ziad already introduced in the morning. This is NASA G-Prof. This is our old GSMAP product. It's the same color, but totally underestimation. Such a heavy rainfall. Okay, I would like to introduce why such an underestimation occurs. Ziad already talked, but in this case, Hurricane Katrina over ocean case. Over ocean case is passive microwave algorithm is very good. This is because weak upper energy emitted by surface. So we have a background is a lower brightness temperature. So if we have a heavy rainfall, we have such a big signal. So we can easily estimate heavy rainfall over ocean. On the other hand, over land totally different. Sorry, this is upper energy emitted by cloud water and the liquid hydrometer. So we have such a red signal. On the other hand, over land case, again, this is Typhoon Marapot case over Taiwan. You can see this is lower frequency brightness temperature is corresponding with such China or Taiwan. So this is because strong upwelling energy emitted by land surface itself. So we cannot distinguish rainfall from this lower brightness, lower frequency channel. So we have to use a high frequency channel like this. So in high frequency channel, as Ziad already told, it's a scattering out of the beam by ice hydrometer. So we have to use this signal to estimate rainfall over land case. So the land case is error is bigger than ocean case. So okay, anyway, so that's why passive algorithm underestimation rainfall over land generally, and this is because generally microwave radiometer algorithm over land assumes that heavy rainfall results from deep clouds. Like this. So in this case, such a deep clouds, very strong scattering. So we, if we get observations, strong scattering, generally speaking, we estimate heavy rainfall. And if we have an observation of weak scattering, we estimate light rainfall. And but this assumption doesn't work for heavy rainfall cases, especially orographic case. Okay, this is one example. This is rainfall over Western Ghats associated with a cyclone Yemi observed by Turin precipitation radar. We have such a maximum rainfall more than 100 millimeter per hour, but the precipitation top height is not so high, less than 10 kilometer. So it's not such a shallow, but yeah. Anyway, not so strong scattering, but still we have a heavy rainfall. In such a case, algorithms seriously underestimation. So yeah, again, back to the Marcotte case. Again, radar, spaceborne radar capture heavy rainfall, but passive one, no. And this is topography. And usually, again, we assume such a deep cloud, cold type cloud. And so in this case, we have very thick ice layer. But the typhoon case, sometimes we have something like that. This is this axis rainfall rate. This is height from the 1 degree level. Yeah, and but the typhoon case is very shallow. But still, we have very heavy rainfall. If usually we use this precipitation profile calculated relationship brightness, temperature, and rainfall rate, and then we estimated surface rainfall rate. So if we use original one, this black line calculated from these deep clouds like this, but if we use this orographic warm rain type relationship, red color, so totally different estimated rainfall for given observed brightness temperature. So yeah, if we use this profile to estimate rainfall, yeah, totally overestimation. So we have to distinguish where is a warm type or where is a deep type, cold type. So we have applied such a scheme. Yeah, using this is JMA GNR global analysis radar, and this is topography data, and we can estimate upward forced motion using horizontal wind and gradient of topography. And then if we have upward motion and also surface moisture convergence, we using shallow convection, orographic lookup table. And the other area, we have original lookup table from cold rain type. If so that, yeah, this is, yeah, estimated orographic host lifting using a object analysis and topography, we can see red color is upward motion and the blue color is downward motion. And this typhoon case, yeah, we have a convergence of surface moisture flux. And then we only use a shallow warm rain type lookup table, only these red color region. Then we have a very good agreement from passive one to then with active radars. So yeah, I would like to say, yeah, generally speaking, remote sensing, especially rainfall, it's something like an ill-posed problem. Yeah, such as solve x plus y equal 5, but we cannot get a unique solution. But if we, so algorithm improvement, it means make a better posed problem. For example, this case we have, if we have a upward motion and we assume the shallow orographic rain type, we can better answer. Yeah, it's in this case, we have get a unique answer. Okay, so, but I want to say one caution. Yeah, we don't use the original topography data. Original one is almost 1 kilometer resolution, but we smoothing 50 kilometer and 100 kilometer, and we check the correspondence, such as upward motion and radar surface rainfall rate, and the correlation between the radar surface rainfall rate and upward motion. 50 kilometers resolution is most appropriate for estimate upward motion. Yeah, this is because GNR data is not so high resolution, 0.75 or something like that. So if you only topography is very high resolution, it's something like indicates just topography. So we need something smoothing topography 50 kilometer. If we have a 100 kilometers smoothing, it's too low resolution. So yeah, 50 kilometer resolution is most high correlation. So we use 50 kilometer resolution. Okay, so now, previously, old one, we don't capture the heavy rainfall over Taiwan, but current, our algorithm, we introduced such a dynamic selection lookup table based on upward motion and moisture flux, so we can now have such a heavy rainfall captured. Okay, and also this is Indian subcontinental case. Yeah, radar capture heavy rainfall over Western Ghats, but passive microburadimeter doesn't capture heavy rainfall over Western Ghats, NASA and our old one. But if we apply such a scheme to distinguish orography or non-orography, we can get agreement. We can get a heavy rainfall over Western Ghats. Okay, so I would like to say some caution to Indian colleague, because you probably use a GPCP or TRIM 3B42 or something like that. Yeah, radar capture heavy rainfall over Western Ghats, but generally speaking, GPCP is heavily dependent on the IR. So, but in this case, yeah, Western Ghats case, we have a shallow convection here. Orographic one, we have shallow convection. And also we have a wind shear produce anvil cloud here. So if we IR technique tend to heavy rainfall in this location, so we can see such a upstream rainfall maximum over ocean. This is also true, TRIM 3B42 or some tendency to overestimation over ocean compared to over mountain area. So yeah, this is heating profile. Western Ghats, we have such a shallow convection, and yeah, this is wind shear. Okay. So anyway, but so we try to apply our orographic scheme to over world, but we have some problem. Yeah, this is a global application of the scheme, and this is TRIM PR, and this is NASA product GPROF minus PR, and our old one, GSMAP minus PR. Yeah, this is Mexico, US or Mexico, and yeah, GPROF is a little bit overestimation. Our product is a little bit underestimation. This is no orographic scheme. So if we apply orographic scheme, result is worse. So too much overestimation. So yeah, probably this is because precipitation profile characteristic is totally different of Western Ghats or Asia, Taiwan case, or from the United States or Mexico. So this is our precipitation type over land. This is, we examine statistically TRIM precipitation radar precipitation profile and determine some rain type, severe thunderstorm, afternoon shower, shallow rainfall, using a vertical structure of precipitation or lightning activity. And yellow color or red color is a strong, generally speaking, strong lightning activity. It means active cold rain processes. And US and Mexico is generally such a lightning cold rain processes dominant. On the other hand, Asia, generally speaking, organized system type is not less active cold ice processes. So anyway, we switch off this scheme in this cold rain active area. So previous version, we just switch off, so we have such a so good result. Okay, but this result indicates we have using upward motion and convergence of surface moisture flux, but probably convergence of surface moisture flux does not fully constrain precipitation profile. Yeah, warm type or cold type. So we, with Chris Kumero, we try to examine what thermodynamic parameter determines precipitation processes. Yeah, warm rain type, active warm rain type, or active cold rain type. Yeah, this is example, heavy rainfall orographic cases over Western Ghats. Yeah, this is same one from cyclone Yami. in this case, very high rainfall rate here, but the precipitation top height is less than 10 kilometers. But in this case, probably this is mesoscale convective system. It's such a heavy rainfall, and the precipitation top height is very deep. And yeah, this case we call warm type. So this type we call cold type. So fat thermodynamic parameter determines precipitation top height is relatively lower or relatively higher. So yeah, this is a result from our paper. I don't time to detail this one. Anyway, some 6 thermodynamic parameter here, and this color is precipitation top height. So you can see this is we can found low level static stability is most important. Yeah, if we have a strong static stability, we have find relatively low precipitation top height. But compared to that, yeah, weak strong stability, static stability, we have deep convection. So yeah, we found this static stability is most important parameter to determine the precipitation top height. So yeah, this is not surprising. Yeah, this is textbook from Bob Hause. This is most simple stable upslope mechanism, and another is unstable upslope mechanism. And yeah, stable one is correspond to this shallow one, and this unstable one correspond to this deep one. And but generally, this diagram says such a stable upslope correspond weak stratiform rainfall, and this case heavy convective rainfall. But yeah, this is but in Asia we have even such a stable case. We have a heavy rainfall. So yeah, such a textbook is generally speaking coming from the observation United States and Europe. But in Asia, we have very humid environment. So even static stability, stable case, we have heavy rainfall. So our assumption from US or Europe is doesn't work in such a heavy rainfall events, especially in Asia. So, but the next step, we try to using static stability to, instead of surface moisture convergence, to determine the precipitation top height. So yeah, this is a stable case, neutral, and unstable case. Yeah, you can find a stable case is relatively lower precipitation top profile. So we apply this scheme to globally. So one typical case I would like to show you, this is trim data for Pakistan rainstorm. This is coming from the BAMS paper, Bob House's group. They said this flash flooding storm does not necessarily accompany extreme strong convection and intense lightning. You can see this is a vertical structure, almost 8 kilometers vertical extent, not so 15 or 16. Yeah. So yeah, if we apply previous one, this is all our product. In this case, we use surface moisture flux. So orographic flux only this red color region. But if we use static stability, if a stable case, we use a relatively shallow lookup table. And then we get better agreement. Yeah, we have some heavy rainfall, especially in this inland case. Okay, so so far I talk about mainly orographic case, but this is my colleague Hamada-san and also Takayabu-san. I got this slide from Professor Yukari Takayabu. Yeah. They statistical study using trim PR data in such a 12-year period. This is rainfall extreme cases. It's a top 0.1% each these grid point in terms of surface rainfall rate. This is top 0.1% in the echo top height. It's something else. So very high type. And this one is both rain and anyway, but we would like to focus on this case. Yeah, you can see the heavy rainfall extreme case not so high compared to this one, but you can see very big slope, less than, this is 0 centigrade, so melting level or something like that. So you can see this slope indicates very active warm rain processes. So this is not only Orwell case. So you can see such an extreme case. Yeah, this is rainfall extreme case. This is height extreme, deep convection extreme case. Yeah, so in such a warm rain type corresponding such a system. And also they investigate what thermodynamic parameter associated with such a heavy rainfall cases. They also, moisture also important, but also atmospheric stability, relatively stable case associated with heavy rainfall case. And the deep cloud is associated unstable environment. Okay, so now we have a discussion about next satellite program. So yeah, this is something match-up data, GPM, DPR, and CloudSat and Calypso shows such a synthetic simulation observation of triple frequency, double band, Ka band, Ku band, and also LiDAR. This is LiDAR backscattering coefficient and double band CloudSat CPR. And this is GPM KPR. This is KUPR. Such a for thick cloud system, it is difficult for the double band or Ka band to determine where it is weak precipitation here or attenuation due to strong precipitation. On the other hand, Ku band can capture such a low-level heavy rainfall. So again, warm rain processes is not only important for rain onset, but also such a heavy rainfall cases. So Ku band is very important for capture such a heavy rainfall cases. Okay, summary is heavy rainfall is not necessarily associated with a conventional high echo top height, but rather than with a relatively low echo top height, we call warm type. In particular, in coastal mountain of Asian monsoon region. Low-level static stability is inferred to be a key parameter to determine precipitation top height. And furthermore, Hamada et al. Shows that the heaviest rainfall within the uppermost 0.1% in tropics and subtropics are not linked to such a deep clouds, the tallest storms. So these results suggested warm rain processes are very important, not only for rain onset, but also heavy or extreme rainfall events. So I would like to say continuation of Ku band observation in future satellite mission is very essential for understanding response of warm rain processes in heavy rainfall, extreme rainfall events to global warming. Okay, thank you. That's all.
Thank you, Professor Shige. Questions or comments?
Shige-san, thank you very much. That was a very nice talk.
Thank you.
What about the Myanmar coast? There also it is shallow clouds, and whether that that orographic
Myanmar,
model that you are using that will work for the Myanmar coast.
Yeah, Myanmar is a little bit actually different. Yeah, it's a little bit deep situation. Yeah, Western Ghats is very simple case, but Myanmar is complex. But yeah, still, but we need such a scheme to capture the orographic rainfall. So not so.
Yeah, and it is also coming into the ocean,
yeah,
the Bay of Bengal.
Yeah, yeah. So it's an interesting topic. Yeah, thank you.
Any other questions or comments?
Thank you. Recently, I also had the chance to participate in the OTREC campaign, and one of the main things that comes out is, of completely consistent is the mass flux and precipitation. Most of the time it maximizes around 700 hectopascal, and there you can get out a lot of precipitation from these clouds. So this is actually most important mode in the tropics, if you want.
Yeah. It's a comment. Yeah, thank you.
Your modified new scheme, how good is the estimation over land?
Over land?
Yeah.
Yeah, generally good. Yeah, modified one. Yeah, you mean this using a static stability? Yeah, it doesn't work relatively well. Yeah, but we need still validation. Yeah.
I have a comment.
Yeah, thank you.
Actually, last December, heavy rainfall occurred in central Vietnam, Da Nang. At that time, 900 millimeter rainfall was observed, but the cloud top height was not high. In that case, actually, I think the precipitation was not orographic one, but there was a cold surge in lowest level, and then the warm and humid air converged and uplifted over the cold surge.
So yeah, actually, we are now in future. This is now only orographic case. It's an upward motion area, but in near future we extended not only orographic one, more wider cases. Yeah.
And also, I guess your statistics may have some suggestion to the convective parameterization in numerical model.
Yeah. Thank you. Comments.
Okay. Any other question? Remote question. Okay. Are there any remote questions?
Yeah, it's a previous talk remote question. 1 o'clock.
No?
Previous question. There is a question again.
What? Are there some comments?
Regarding this CO2 transfer process, what happens is that we have not calculated the fluxes because very short duration, and also there is not flow is not stationary. So when you want to use any of these eddy covariance methods, we assume there's some kind of quasi-stationary or stationary process. So therefore, we have no estimation of this one. But the CO2 transfer mainly from the plant activity, right? So unless there is a biological activity, I don't think there is a CO2 process as such. Thank
you. Okay, so we would like to move on to the next presentation. Next talk is by Dr. Rajagopal from National Center for Medium Range Weather Forecasting of India.
I think I'll also come to the front. Good afternoon to all. So the topic was suggested by Partha, and I will mostly concentrate on the tropical cyclone prediction activities that has taken place in NCMRWF and some ideas on future what we can do. So just before going ahead to this audience, NCMRWF has major mandates. We maintain 2 data assimilation systems, global for the GFS system and for the unified model also, 2 data assimilation systems. And we also maintain the unified model which we call as NCOM under the UN partnership. So MOE is a core partner in the UN partnership, with members from other countries. And currently operational systems for data assimilation, we have 2 data assimilation centers for global. One is an 80-member hybrid 4D ensemble VAR, similar to what is at NSEP, and at 12-kilometer resolution. And there's a hybrid ensemble 4D VAR for the which we call NCOM, 12 kilometer. It's a 22-member hybrid. And the great thing is that we have a 22-member ensemble also at the same resolution. The regional 4D VAR is there for at 4 kilometer for the Then we have a ocean sea ice global data assimilation for the coupled system at, with NEMO at NEMO VAR at 0.25 with level 75. And operational models are that our global model runs twice in a day from 0 and 12 for 10 days. And we have global ensemble system with control plus 11 member 10-day forecast both for 0 and 12, which we merge and bring out 22 members. Regional 4 kilometer every day for 0 and 12 UTC, 25 hour forecast. And recently this monsoon, we implemented a 11-member regional ensemble also at 0 UTC. The coupled model runs daily for 2 weeks for coupled NWP scale, once a week for extended range prediction, once in 2 months for the seasonal prediction. The atmosphere model in this very course, 65 kilometer, and oceans is 25 kilometer, the NEMO. This basically shows the suite of models displayed on the map on a globe. So we also have a model 330 meter which runs normally in the winter time for the fog visibility predictions, and a 1.5 kilometer model over this area which caters to mountainous areas forecast. And all the details, I think I will not, it's already mentioned by me. And being a leading data assimilation center, we assimilate a lot of data. So most of the data which goes into whatever is going to ECMW or Metoffice or NSEP, we assimilate. We have a direct feed from NOAA and NESTIS and UMetCast. So we get about 200 or 300 GB of data per day. And all this is possible because we have a computing which is about 2.58 petaflop. And it was commissioned last year, January. So in NCMRWF and access on the production, it's around 936 nodes goes into production environment. So research suffers, it's only 370 which is available. This is distributed among 3 institutes, the NCMRWF, IMD and INCOIS. Out of 2,320 nodes, this much only 1,306 is only for NCMRWF, 224 IMD, and INCOIS has got 784. So coming to this topic on which I will talk. So initially I will touch upon the global and regional atmosphere model, how they have performed the last few years. Then about the global and regional ensemble prediction system. Then I'll talk about something about the issues in TC prediction, about cyclone vortex initialization, what are the other issues, and global regional coupled model into each. So some of these may not follow the same way, but I think I will try to make it more coherent when we go ahead. So it begins with, we had set up the in 2012 at 25 kilometer, and then an evaluation was done for TCs of North Indian Ocean, basically for this period. These were the cyclones which were considered, 47 cases, different cyclones. This basically shows small models. The initial errors also are large because the analysis positions are different. So for different cyclones, what are the initial position errors? As the initial position errors are more than the forecast also will be deviating. So even the mean sense, it's about, for all the cyclones for that numbers, it's about 75 kilometer error, initial position. And then comparing with how the model performs with the Clipper, the climatology and persistence forecast, which IMD used to deploy. Definitely the NCOM 25 kilometer is outperforming the Clipper. This for the North Indian Ocean, Arabian Sea, and the forecast lead time, you can see clearly. And this for the Arabian Sea. And skill is in terms of the Clipper, and definitely improvement. The red is the Clipper. Then the direct positional error kilometers. So if you can see for severe classified into severe cyclones and cyclonic systems. Here the DP is more for cyclonic systems, not for severe, as forecast length leads. Similarly, the gain in skill also you can see. The skill again is calculated based on the clipper. So here again the skill is much more for the severe cyclonic cases because the vortex is much more organized and formed. Then it was further classified into recurving cyclones and straight movers. So in the case of direct proportional error, it's more for recurving, which is actually recurvature is not very easy to predict by models, which is under the influence of the upper levels drive, this one, flow pattern. So DP is more for recurring TCs, you can see very clearly. And landfall errors, basically for all the cyclones together, its mean is about 162, and for each cyclone it is varied. And all these errors are computed based on the actual data provided by IMD after the system has passed away. The mean absolute error, again is shown here, and skill of mean absolute error. This is against IMD actual observations. This for the blue is for NIO, red is for Bay of Bengal, green is for Arabian Sea. And this is the percentage of skill of absolute error. Skill is again calculated based on the clipper, this one. And RMS is also you can see for the maximum wind for various cyclones. So Bay of Bengal seems to have more errors. Again, for looking at mean absolute error in kilometers for severe cyclones, and it's this one. So you can see AE is more for severe cyclones as forecast length increases, and for severe, this is for the mean for all cyclones together. Again, for recurving cyclones, AE is more for straight movers. Then at that point of time in 2013-14, we had a regional model also at 12 kilometer. So we did a comparison how the regional model performs in terms of that. So what in nutshell is that the income regional, which we call R, performs better for DP, CT, and AT errors, which demonstrate that resolution matters. Further ahead, I think previously also some people have told resolution really matters. So these are the cyclones which were considered for this study. I don't want to get into details of the systems. We'll just go to some statistics. So the mean DP at initial time and different forecast hours, you can clearly see the case to case. The income regional has comparatively less initial position errors. And with for different forecast hour also, definitely income regional is outperforming. And skill also you can see is definitely much better compared to this one. The mean CTE and ATE also different. Here also again the story is same. The regional model does definitely much better. The mean landfall error for each TC, overall mean and gain in percentage with respect to the global. Again, you can see very clearly for all the 3-4 cyclone plus the mean also, the regional landfall errors are much less. This is again for absolute error for mean maximum sustained wind, MSLP and radius of 34 kilometer winds, which again brings out the same picture that the regional model outperforms the global model. And at this point of time, the 12 kilometer model was basically a downscaler and we did not have a data assimilation in it. And down the line, the models, higher global model resolution changed from 25 to 17. The dynamic code changed from the new dynamics to the end game. End game has been found and documented as a better cyclone in its prediction. So as expected, the higher the resolution, the better is the prediction. But one thing you should also remember is that along with this side, the data assimilation also has improved. The data ingest also has gone into. So it is not just because of this, but still all other activities which We went along with the model upgradation, and mostly most of the upgradations in the model happens, and the system happens only when we have a computing upgrade. So in 2015, we had a computer upgrade, and we went to 350 teraflop Bhaskara computer. And these are the few cyclones which we considered. Here also it's very clear, case by case, you can see clearly the 25 kilometer and 17 kilometer. The 17 kilometer outperforms the 25 kilometer as expected. This is for mean gain is about 21 to 18% absolute, mean absolute for 10 meter winds and MSLP respectively. So I mentioned about the initial vortex position, because initial errors, initial position of the errors was the tropical cyclone itself was having a lot of errors. So we looked up, there's originally ideas of bogussing, then came tropical cyclone relocation, which ends up adopts, and wherein they modify the location of the vortex in the initial guess, model guess, which goes into analysis. We went to the vortex initialization method, which Australia Bureau does, and we implemented it in the global model. So details of the vortex initialization are given here. Basically U, V, T, geopotential light, and RH at all pressure levels, surface temperature, all these things are taken. Water initial works in the 4 steps: the filtering the analyzed circulation from the original analysis, construction of an inner core of cyclone, relocation of the inner core to the observation location, merging of the relocated vortex with large-scale analysis. So this is basically based on the vortex initialization method of Davidson et al. MWR 2014. So this again mentioned. Synthetic observations of mean sea level pressure produced by vortex initiation scheme for the cyclone were used in 4D data assimilation for both 25 kilometer global and the regional also. By the time we had the regional model also, data assimilation 3D war in place. So you can clearly see that this is a control which is basically without the vortex initialization, where the system will be displaced. So you will find large, about 50 to 60 kilometer error in the initial position errors. And the global and regional you can see clearly. And as time passes by, you can clearly see the regional model definitely does better, as previously shown also. The global model, the global vortex initialization also does better compared to the control run. Okay. So these are the cyclones we considered. Basically all these cyclones here, case 1, case 2. This basically compares only the control and the global and the vortex, this one. This again shows all their statistics of cross track error, along track errors, and mean initial positional errors are all much better when you have the vortex initialization. Here you can see here for this particular case, it's about 80 kilometer the initial error. So definitely it has improved the initial position of the cyclone, so thereby resulting into a better forecast of the cyclone along and the track and all the details. You can see landfall errors. I don't want to get into each slide and go by each of them. And the last years we went to a 12 kilometer model, the global, and we had a regional model 4 kilometer, which had a 4D VAR in it, and just few slides on the 2018 TCs. I think this is TC Maha over this one, this period. So rapid intensification is clearly brought out by the regional model. You can see very clearly. It has got better skill. This MSLP skill, also here you can see the regional model outperforms the global. And mean sustained wind here in this one. Also here you can see very clearly the regional model, the errors are much less. This is for the other cyclone. I think each cyclone you can see very clearly. These are JTWC, this one, this is the regional and this one. The regional model has definitely outperformed the global model in most all the cases. That's very clearly seen in all these view graphs, where for each variable, this one, this is the average storm relative helicity. Also, you can see potential term instability pi. So, which means that high values of SRH means more convective cells or more updraft in the vicinity of the TCI wall. Less values of PM means high thermal instability and leads to deep convection. This for average for all the TCs, definitely brings out the same picture. The regional model outperforms the global model. So we didn't talk about, we'll talk about something about the ensemble system also, recent improvements. These are some cases of the recent cyclone Fani. So here we have also attempted to compare the global, regional, ensemble. Now this global ensemble, global model, deterministic, the regional model deterministic, and access TC, which is the Bureau's TC model. We get data from them also for this period. So from the income G analysis, you can clearly see the cyclone positions. Here the best track locations on IMD are marked in the star position here. Different days, 26th to April to 4th May. These are a particular initial condition, how the forecast was based on this initial condition. Definitely these tracks are slightly away from when you come at higher lead times. Up to here it was okay, here it's definitely it is low, it has crossed further southwest. This for another date, same thing. So this, all the displacement errors will be reflected, and then we looked at the genesis potential also from the for the cyclone from 25th April. This one for based on initial condition of 25th, day 3, day 4, and day 5 forecast, and this basically shows an animation based on 26th initial how the genesis potential is moving around. And what made the cyclone to recurve, you can very clearly see. It goes along that. We looked at the latent heat flux. I think I will run through these slides. Different initial conditions, the latent heat fluxes, the mean sea level pressure. These are all from the global model. These for different initial conditions. And then we looked at the meteograms which we generate, and we could find a large fall in the MSLP. You can very clearly see from the global model from the initial condition of 30th August. These were two places, Bhubaneswar and Kolkata. And this basically shows the track for this whole period for different initial conditions, and the black one is the observed track. So clearly in the earlier part, 27th and 28th, the track was putting it here, but towards after the recurvature was indicated, the models are much more closer. And this is the regional from 27 to 4th. You can see clearly the second one here, third one here. They are very close, tightly along the observed track. So these will be also reflected in the. So we have a web page in which all the four cyclone for the cyclone prediction models, like similarly access, NEPS, observed, and regional and the global are all tracks are generated. Now I think the ensemble prediction system for all the basins also are generated, and they are available on a web page. So this basically shows the track of the 11-member ensemble with the strike probability. This is the same thing for another day. Just it's basically comparing these three cyclones here, the tracks, and then the NEPS. Same thing, let's go ahead. So forecast track errors for the whole system based on the whole period for all the four models. The red one is the deterministic model income. The green one is the NEPS global. region is the blue one. And access definitely has outperformed. And I would like to mention here that for these cyclones, I think the vortex initialization scheme has not been active in our center, and whereas they have, that's why the initial errors are also much less in the bureau's TC axis. The same thing it says about low initial position errors is lowest because 34, whatever I showed in the slide, are second best, and this one. So initial position errors are much larger in this ensemble system. The direct position error also is clearly brought out. Whatever I seen there is clearly just reiterated on this slide. Along track error is less than 50 and cross track error is approximately 50 in the initial position. You can see very clearly here in this one. So most of the models, but Axis definitely has outperformed. The along track errors, same situation, most of the cases Axis has done much better. And the sustained maximum mint regional model is the green one, IMD one is this one, Axis is this one, different this one. So what we find, strong intensity to income in APS and UM regional. Maximum wind is underestimated at higher lead times. You can see very clearly because the actual wind was maximum here. The models are not overestimated by regional model at many points of time. Different this one. And minimum SLP also accurately predicted in income in APS, underestimated by Axis and overestimated by UM regional, income regional. This for another period starting from 29th. It's the same story, I'll just go ahead. Then mean absolute error and minimum SLP. You can see very clearly what was mentioned in the previous slide, Axis has got more errors in this one. And the income is the blue one and NEPS is red. UM regional is this one. So around 10 hectopascal up to 72 hour, error grows rapidly from 72 to 120 hour. Maximum wind around 18 knots to 72 hour and error grows rapidly after that. Very clearly seen in the global model forecast. So ensemble system we had in 2015 set up a 33 kilometer ensemble based on the Met Office MOGREPs. And in 2018 June we had a 12 kilometer global ensemble system which is the highest resolution compared to what ECMW runs at 18 and Met Office at 20 kilometer. This again will demonstrate that higher resolution does better. This just shows the cyclones considered, tropical cyclones considered. So you can see the red one is the upgraded one, the errors are definitely much less for AT, CT or DP, whatever it was, look for. Landfall errors, maximum wind speed errors, everything. The higher the resolution the model, it has performed better. And last year in 2018 we had severe flooding in Kerala which prompted us to think of setting up a regional ensemble prediction system. And we managed to set it up after the event, and then this monsoon season it became an operational system. So this is basically 11-member ensemble system running at 4 kilometer resolution, and it's again a downscaler. It doesn't have a data assimilation because we don't run an ensemble data assimilation for regional yet. So this shows the 3-day forecast of MSLP for cyclone of 3rd May 2019, initial condition 9. So you can just close the 6 members cross the coast while 7 members lie west of Puri. It just shows how each member initial condition had impact on the forecast. And this is a forecast from the global model for the same system, and this is the tropical storm strike probability, this one, and this is the regional model. This, you can see black is the observation, ensemble mean is blue, and control is red. This is again same thing, NEPSR for the whole initial condition May, 1st May 2019, blue is for global, and red is for regional, and red you can see very clearly red is much close to observation. So rapid intensification of Fani was something which was noticed, and you could see also that the MSLP in even Calcutta or Bhubaneswar are dropped down in even the meteograms. So you can very clearly see that the NEPSR is able to bring down, get the mean sea level below 940 940 hectopascal. The rapid intensification from 45 knot to 94 knot between 0 and 9 UTC to, I think, 15 UTC. You can see very clearly around here. Again, this shows the cross-track errors and this one. So initially CTE of NEPSR is large, but after 12 hours it does not exceed 40. After 30 hours DPE becomes less than the global. Because this, you have to understand that this is basically a downscaler, doesn't have many data assimilation, so initial errors will be larger. So coming back to issues in tropical cyclone, I think I have about 10 minutes left. So this part I already covered. I'll just say same thing. I want to just say that what all ways to do the initial position things. ECMWF assimilates only real observations. METOF is assimilation of hourly TC vitals, minimum sea level pressure. There's no boggusing, and only BOM does the initial vortex initialization operationally. So this comes to a picture. We are thinking what we should be doing. So there are publications which shows that coupled models do better prediction of the intensity. So if you see regional models have one has the resolution of the model increases, the winds become much stronger, and actually the central pressures are much high, more than actually what is observed. So what is here, the over prediction of TC intensity is high in high resolution global and regional atmosphere is now well known. A possible reason for it is the fact that the main energy source for TCs is the heat transport from the ocean. By not coupling the atmosphere, the ocean, the heat exchange at the surface is misinterpreted, and the ocean acts as the undiminished source of energy for the atmosphere during the forecast period. Basically, it means that the SST, you start one day, that SST is persisted for next 10 days or next 3 days. So it doesn't have the impact of the actual cyclone cooling the SST. This allows the TC to intensify to increase unrealistic noted in most of the high resolution models. And previously, when we are not having the atmospheric model, only models were never having initial pressures, center pressures properly done, because previously errors resulting from lack of coupling were partly compensated by opposite sign errors by under prediction of the core pressure, weaker TCs resulting from low resolution models. So using a coupled model introduces negative feedback between TC and the SST. As strong winds of the cyclone enhance the heat uptake from the ocean, SST may decrease, which in turn reduces the energy available to cyclone. So this is what is missing when you don't have coupling. And tropical cyclone interact with SST in 3 ways: heat transport to the atmosphere, vertical mixing to the ocean, and upwelling by the Ekman pumping. The first 2 processes could be simulated by a ocean slab model, which used to be there and before in some of the modeling centers. The second requires a model of well-mixed layer of the top of the atmosphere, and to simulate all 3 processes together, a 3-dimensional model is required. This is especially important for slow-moving cyclones. So when we are talking about coupled, then we have a HWRF set up at NCMRWF along with IMD, this one. So those details are here. I think there's a poster also by somebody here from my center. It has a 3D GSI and hybrid 3D VAR implemented, has both POM and HICOM versions of the ocean regional, and is a stationary parent domain and moving nest. And they're finally go to a hybrid data assimilation system, which already been tested. It may get into operation soon. So this basically shows some cyclones based on HWRF predictions. What you find is that when you compare, definitely HWRF does better for all the cyclones. I think I will rush through this because for enough time. You can see this slide. Recent developments, GSI inside 3D radiance has been assimilated. Few results from that. This one, green one is the POM, and this is for HWRF, 12-hour forecast errors. So at the higher lead times, you can see very clearly HWRF with HICOM is definitely better. And this is with HWRF, HICOM plus inside radiance assimilation. Errors are definitely little more less. This average absolute intensity forecast error This is the track error forecast, direct position errors. Here also you can see very clearly at the higher lead times, the coupled system with ICOM definitely does better. And with the radiance simulation of InSight also it is. So we do have a coupled NWP modeling system operational at a very coarse resolution at 65 kilometer and L85, the UM. The NEMO is 25 kilometer and we daily do a 15-day prediction. And this was basically, I think that the coupled system, initially the coarse resolution models were not able to predict initial cyclogenesis better and higher lead times. So this is a clear demonstration. I mean, I'll just show a few slides later. This is what is there in the model. The UM and the land surface joules, 3 eyes, and the coupler oasis and the NEMO. The same thing in 4 details. So this is where I wanted to show them. This is for a case of October 15, 2017. The coupled NWP for 10 days ahead could predict this cyclone system here, whereas the deterministic model had a very weak system, and the global analysis had a system here. So coupled model seems to be doing much better. So this initial prediction, vortex initial prediction is much better the coupled system. That's very clearly seen not only for 1 day, even for 16th October. This was 17th October. And for the TC Fanny, we looked at tropical cyclone heat contention potential, looking at favorable conditions with this one. This is unfavorable and this favorable, more than 100 kJ per centimeter squared. I'll just rush through these slides. I think this is analyzed TCHP from the global ocean data simulation. We have a NEMO-VAR which generates the ocean data simulation over this area for the TC Fanny. You can see very clearly the high values of TCHP. This is for day 1 forecast. You can see very clearly how it starts moving northward. So the way forward, I suggest we should go very high resolution coupled model, and I am prompted by a report from ECMWF, ocean coupling tropical cyclone by these people, wherein they have run the IFS at 9 kilometer coupled to a NEMO 25 kilometer, and they also have a wave model, and definitely you can see it just outperformed the deterministic model. This is basically the SST predictions, fantastic predictions with that, and the tracks are also much better. So on the same lines, under a collaboration with Metaoffice, under WSSC, SSP, I mean this basically again just coupled system outperforming, and all the things are lying in between this area. We have a collaboration with the Metaoffice on this one, and there's a work under the work package. We are developing a regional coupled model, which will also have a NEMO ocean and a wave model. And this just shows just a few results from recent cyclone, which they attempted a few weeks or a few months back. So this slide is basically the atmosphere only actual value, and this is a coupled minus atmosphere results. So much lower wind speed over along the cyclone track in coupled model. Actually, it's not very clear. No. Yeah, you can see here wind speed, because we are saying when it's not coupled, the system is very intense. So you can see where with the coupled system you get negative values. That means it is able to reduce the over intensification much better. I'm sorry that plots are not that very visible, clear to me also now. And thank you. All of you are welcome to NCMRW. We are organizing an international conference on ensemble methods in modeling and data simulation in February 2020. Thank you.
Thank you. So any questions or comments?
Yes, very nice talk. I confirm, I mean, we couple the high resolution at the European Center also because of intensification of the tropical storms, was one of the reasons. But I was wondering whether you compared the results from your ensemble to the ECMWF ensemble, which has been coupled for many years for tropical cyclone Fani or for any other? Whether you have any results or any statistics or so on?
No, because we have direct access to the UK Met Office products and TC access. We CMW will have to maybe make a special effort, or we have to take it from TIGI will be much more coarse.
Yeah.
Portal. We'll find out. I'll tell.
Yeah, but I think if you contact TCMWF, they would be probably interested in working with you on comparing.
Thank you. Interested in how good the access forecasts were. Do you think the fact that they're doing the vortex assimilation is the critical thing there?
I think the vortex initialization is the main thing, because that's I think it's a 12 kilometer which set up over Indian Ocean area. It's a regional model, not a global one.
Oh, it's a regional model.
Yeah.
Oh, okay.
The access
So
TC is around, I think, 12 kilometers that time. Now I don't know what's the exact resolution.
So resolution as well.
Yeah. So they have a vortex initiation for the storms, and they have been doing very well as per many studies. Their initial vortex position is very good, so the forecast also much better.
Thank you.
Other questions or comments?
Any remote?
Yeah. Remote? No, no remote question. Okay. Okay, so thank you very much. We move on to the next presentation. Next talk is by Professor Mohanty from Indian Institute of Technology.
Very good afternoon to all of you. So this is a talk of myself and my co-workers with me, and there are three of them in this hall. They are here. So we'll show some of the results and on the recent developments in prediction of tropical cyclones over the North Indian Ocean. At the outset, I like to acknowledge the work which is done in academic environment with very much support from various groups, in particular the Hurricane Research Division of NOAA, Frank and Gopal, and NSEP with Vijay, and also from India. Actually, this collaboration is done with IMD, INCAES, and we got enough computing support from IITM, from the Supercomputing Center. So that made us possible to join in a forecast demonstration program which IMD launched in 2007. And I'll show you that the developments that lead to the improvement in the tropical cyclone prediction. So my outlook, in the introduction, I'll tell some real-time prediction under the FDP, that forecast demonstration program, which is WRF, and performance of the HWRF systems, and rapid intensification of tropical cyclone over the North Indian Oceans, and impact of the high-resolution multi-scale interactions, and coupled HWRF high-com prediction. And also, I'll show you some results of prediction of associated storm surges, and why it is that I will tell in my next one. And now my work is very simpler because Dr. Rajgopal has very clearly demonstrated two more aspects, that regional model performance and as well as coupled models. So the North Indian Ocean is very unique, though it consists of two bays, Bay of Bengal and the Arabian Sea, but it is only contribute over 7% of total global tropical cyclones. Bay of Bengal about 4% and 3% by Arabian Sea. But if we see last 300 years of cyclones having death rule of more than 5,000, their count is 24. And out of that, Bay of Bengal contribute 18, almost 75%. And most infamous are the Bhola of 1970, where 3 lakh people died, and more recently, Nargis of 2008, when in Myanmar, more than 1.5 lakh people perished. And this North Indian Ocean have 2 cyclone seasons, in contrast to other ocean basins. It has one in the pre-monsoon in the month of April and May, and one is by post-monsoon period, generally October all the way up to December. Here cyclones are relatively less intense because the life cycle is only short, making small bay configurations. But in this basin, we get storm surges as high as 8 to 12 meters and thickly populated coastal area of Bangladesh and the east coast of India. And there's a large stretch of river basins, and that also contribute. So as a result, there's a such type of loss of life that is what found in the Indian ocean basins. So here I am showing you just 2 comparisons of last 20 years. One is in the year 1999, which is we call the super cyclone of the Odisha, and in that more than 10,000 people died. And the other one in the almost same region in 2013, that is Helene, and in which the death toll was only 21, and out of that 10 are actually due to hydrological effects in a long distance. So cyclone contributed only 11. So this is mainly attributed, that time the IMD and as well as in research institutions, we have MM5 and semi-Lagrange model, very coarse models. Computer resource was very few, data also quite not adequate. So as a result, the error was quite large. And whereas the next cyclone, which was Helene, which Dr. Rajagopal has shown very elaborate way, you see that all the way, every time step, 5 days in advance, the forecast was almost pinpointed. And this is the cyclone in which the state government has evacuated more than 10 lakh people within a span of 2 to 3 days. In fact, this dramatical change of 99 to 2013 is, though it mainly contributed the forecast, as a forecaster we claim, but it has 2 other aspects, that is the dissemination of the forecast and public awareness has tremendously increased in India from 99 to 2013. Now we have more than 200 news channels in various regional languages, and who can really provocate people to leave the place and go away. And second thing, that after 99, first time India started a disaster management agencies. Up to that, we have only post-disaster relief measures were taken. In 99, after cyclone, Odisha started first, and in 2005, we have National Disaster Mitigation Authority, so that they can evacuate in very short time, 2 to 3 days. And the Pune, the cyclone which recently passed, they could evacuate 15 lakh people within a span of 2 days, so that the casualty also reduced dramatically. So first I'll start with real-time prediction of tropical cyclones. This is the cyclone Pune, which was Helene, which was predicted 5 days in advance, and white is the track that is observed, and the red one that is predicted, and that you can see that it is almost like a dot prediction. And this is the intensity prediction with that cyclone that passed through Gopalpur, and this is the barograph of that place, and this is what is simulated by HOR system. About 9:38 was the pressure drop, and it was simulated up to 9:45 or so. And this is actually track prediction, and whereas this is the intensity prediction, which is WRF model. And this is the mean track errors predicted by various groups. from IMD to JMA, UKMO, and IMD, MME, and also ARW, IIT Bhubaneswar. So these are the different groups. So you can see that there is a widespread in the mean track errors, but the track errors by Indian predictions are quite less compared to that from the other places. This is the precipitation prediction associated with that tropical cyclone Phelan. And you can see that though it passed through the South Odisha, the actual maximum rain was in the North Odisha, about 400 kilometers away in the spiral band, and which was well simulated, but it was not taken the government the stand that there will be a fraud, which caused the casualty of about 10 people. So this is the next year's almost same time, the cyclone Hudhud, which crossed unusual place of Visakhapatnam, and this is the track prediction, and this is the mean track errors, and this is the model predicted 10-meter maximum wind, so which you can see that it is very close to that of the observed. And this is the precipitation rainfall prediction, and this is the Visakhapatnam, we have a Doppler radar, and other one, and this is the what is the model simulated reflectivity, and this is the reflectivity that you observed from the radar. In fact, actually, in last few years, we have about 12 Doppler radars along the east and west coast of India to have very good observations of reflectivity and radial velocity along with the satellites. So this is the most recent cyclone Phony, which passed through Odisha coast, and it has a devastation. Puri, Bhubaneswar, and Cuttack, three major cities of this state, and where more than 60 people they are perished. But in this one, they could evacuate 15 lakh people, so that you can imagine the loss was minimized, because this was cyclone which remained a very extreme severe cyclone, and it remained very severe cyclone even over the land for about 12 hours or more. This is the various time prediction. Again, it is 5 days in advance. It could show that the cyclone is going to pass through between Chilika and Puri. That is a small stretch in Odisha coast. This is the intensity prediction with HOR system. The black one is the observed and mean forecast errors. And this is the storm surge associated with this cyclone. As the cyclone glazed through, so that's why the storm surges are not so large. It is about 1.5 meters. So as I told you, from 2007 onward, IMD started a program of forecast demonstration program in which various groups, along with the IMD, they provide the TC Vital, and various groups, they run their models and provide the results to IMD for its to making their ensemble and also multi-model ensemble system to predict. So I will show some verification of that. So this is again actually make my life simpler, because as Dr. Rajgopal told, the observed TC location error is around 60 kilometers, and this is because we use in our case NSAP, initial condition, GFS. And whereas we make verification with the IMD estimation, which is best track. So their error is around 60 kilometers. So mean errors at initial time is about 60 kilometers. And it again emphasized what Dr. Rajagopal told also, with increasing resolution, 27 kilometer, 18 kilometer, 9 kilometers. If you see the results, it also again shows that though initial time they are almost similar, with the increase of time, the resolution have a big impact, and that could be able to improve, reduce the track errors, and also intensity error also reduce, and this percentage improvement is given here. Then we have seen the two difficult things. One is that mean errors for recurring tropical cyclones, and mean errors associated with intensity of the initial position of the cyclone from which the forecast was made. So this is of the three, there is a prediction. So mean error for the recurring cyclones, as you see, with increasing the resolution, then it shows that the errors are reduced substantially with the time. And so also it shows that if you see that depression stage starting cyclone stage or severe cyclone stage, then with severe cyclone stage, the forecast also further improve because the vortex is well defined and which could be able to better simulated with the models. So we have done some experiments with non-conventional data assimilation with N-shape initial GFS data. So we have used the Doppler radar, reflectivity and radial velocity, as well as satellite radiance assimilations. So these show that a number of cases impact of satellite data assimilations. So this is for the cyclone Gonu, Nargis, and you can see that actually with observed track, that black one and the control one, and one with assimilation of the additional satellite data. So you can see that the error is decreased, and if you see that also for the up to 96 hours, you can see that control versus the one with satellite data radiance assimilations. So this is the percentage improvements that we can see. And similarly, we have seen the impact of the Doppler weather radar reflectivity and radial velocity. And at that time, we have taken mainly to this Doppler radar data was free domain available, Calcutta and Chennai. So we have taken a number of cyclones to see that key impact of that. So there are total actually about this 9 kilometer model resolution, and we have taken a number of cases of these cyclones. And here actually we have done experiments with the control run and taking the GTS data and assimilating and taking the Doppler radar data and GTS data together and making the assimilations. And this is the cyclone for the Cedar cyclone, and which was covered by the Calcutta satellites, Doppler radars. And so this is, you can see actually from Doppler radar compare and the black one that is observed. So you can see that that is more close than the other two. And this is the vector displacement errors of the control and with the Doppler radar data assimilations, and this is the percentage improvement that we can see from 24, 48, and 72 hours. And because of Bay of Bengal, actually we don't have any aircraft data, and we don't have very few, we have the buoys, so almost it is a data void region having no data. So therefore, whatever data is available from the coastal radars and satellite, they could able to give a big impact. And similarly, this is the, we have now a INSAT 3D and 3DR, which give the radiance assimilation is possible because these, that we have taken for the recent cyclone with INSAT 3D and 3DR data. And that you can see that it is the, this is the cyclone Titli, which is a very severe cyclone storm. Again, it crossed the Odisha coast also. This is the cross track errors, and this is the along the track errors in that time. So you can see that in both the cases, there is improvement is found that with inclusion of the satellite radiance, but that is more reflected when you go to the intensity prediction, and particularly mean intensity error, which you are taking as a wind at 10 meters, because ultimately that is used for the prediction of the storm surges. And so here you can see that this is the IMD best observations. Control run is the blue one, red one is the assimilation of the INSAT 3D and 3DR. As Dr. Rajagopal told also, that the same way you can see that there is a lot of improvement. You can see as you increase in the time length with the increase of including of the satellite radiance data. So also we can see that if you go to the diagnostic of the temperature field, and you can see that there's a lot of difference between control and INSAT 3DR, and particularly the theta E profile, you can see that which is not there's a large difference. And precipitation is also little improved. This is what is observed, but anyhow, still a rainfall prediction needs to be improved, and ensemble prediction or 4D or assimilation may be better solutions. So here we have made some comparison because in 2010 we switched over from ARW to HWRF, and so then from 2011 we have run both the models, ARW and HWRF. And that also we are more encouraged by the prediction of the intensity in particular, because this is the TC Fallin case, this ARW model prediction. The black one is the observed intensity, 10 kilometer maximum wind, and the other one is from different initial conditions. So you can see that ARW is under predicting, and whereas HWRF have a little over prediction or very close to the what is the observed. So then we have carried out a large number of Bay of Bengal cyclones. These are the cyclones, and we have taken 10 cyclones with the 72 initial conditions to see the performance of these two models. And this is the satellite derived. So this is for the another cyclone Varda, which crossed in Chennai, close to Chennai. And here also you can see the satellite derived wind fields for Varda and Ronu. And this is what is with ARW, and this is with HWRF. HWRF shows more confined and little better, close to that of satellites. And this is the initial position errors, because the HWRF have already inbuilt vertex initialization and relocation. So therefore, the error of 60 kilometer, which I was telling you that it's minimized to 0, the position errors, and also intensity could be able to improve. So this is actually errors with a WRF position, because here we have not done any vertex initialization or relocations. And this is the initial position errors, but whereas it became 0 with HWRF because of the it is vertex initialization. And similarly, intensity also error is confined to about only about 4 meters, but whereas it is quite large, about 13 meters or so. So this is the prediction of position and its errors. And as you can see that this black one is again observed, and here green one is that of the HWRF, and red one is the ARW. So you can see that definitely HWRF is doing better. And this is all the 72 cases that I told for this. These are track errors with ARW and HWRF. So this shows that almost, and the shaded one is the ARW errors, and the bar one that of the HWRF. So this you can see that the improvement of, and similarly this the directional track errors and landfall errors associated with negative is left to the storm, positive is the right to the storm. Similarly, negative is that slow down, and positive is the faster. So you can see that in all these cases, landfall error, position errors, or landfall time errors, as well as cross track and along track errors, if you can see it is clearly demonstrated that there is improvement in that of the HWRF system compared to that of WRF. And this is the intensity prediction and gains in the scale. So again, this intensity prediction of WRF with HWRF, if you see here, black one is the HWRF and the gray one is the WRF. So here also you can see that in the same picture as we go in the time, the HWRF intensity prediction is substantially improves in this basin compared to that of the ARW. And the gain in the, and this gain in the intensity we calculated based on the 2013 to 2016 IMD operational forecast as the benchmark. With that, what is the improvement? So where actually ARW go negative side, HWRF, so that a positive scale are better than operational. The present challenge in the prediction, though track, we have seen that it has substantially improved, and almost all the tracks of the all cyclones in the last 5 to 6 years were very dramatically improved and predicted by IMD and almost 5 days in advance. And as Professor Bhatt told, now we are so happy that the cyclone is not the main killer now, which was even 2000, up to 1999, it was considered the greatest killer for the population in east coast and west coast of India. Now it is shifted to the lightning and thunderstorms. And whereas it is substantially decreased, except few cases of aberration like Titli and this Pune, where 60 was the death toll, otherwise it is less than 20 or so. So, but intensity still is a problem, and which particularly the rapid intensification process coupled with the ocean models, land surface interactions, and shear vertex interaction. These are the problems which are really quite important problems in prediction of the intensity of the tropical cyclones. And even much more problem is the precipitation prediction associated with the tropical cyclones. At the same time, if we see the Bay of Bengal, suppose from 1951 to 2016, so this is the pre-monsoon cyclones, and cyclone activity was North Indian Ocean, that is this is a pre-monsoon period, and this is the total number of cyclones of a Nile region in post-monsoon. Both show that the number is decreasing, but if you see that there is a significant rising in the rapid intensification or more intense cyclones in very short time, because most of the cyclone life is 4 to 5 days generally. So this shows that whatever we know for other machines, that is by Peter Webster and others, they have published that all the almost machines that the intensity of the cyclone, when intense cyclone is increasing, whereas less intense cyclones, they are decreasing or not so dramatic increase. The same picture also for the North Indian Ocean, where the rapid intensification or intense cyclone cases are increasing, whereas the number of cyclones are almost reduced. So I will tell you the two recent cases of 2013. In one case, that is Philin, in which case the cyclone have a rapid intensification, and where within a time span of 18 hours, it is intensified from cyclonic storm to very severe or extremely severe cyclonic storm, and we define rapid intensification as 65 knots in 24 hours. Similarly, another case of the same year, after 1 month, Leher case, which was a very severe cyclone, but it crossed the land with a depression, which again also in almost about 18 hours, it weakened from a very severe cyclone to depressions. So this is the cyclone track. So as you can see that both the models, that is this is Philin and this is the Leher, in both the cases, the prediction was quite okay, the track. And this is the intensity prediction. And again, this is IMD estimated. The black one, the red one is that simulated by HWRF. So as you can see that HWRF could be able to simulate the intensity and also decaying process very accurately, and that is also very important because otherwise a lot of evacuation measures taken, and which also cost a lot of money and also lose the faith with the public. So in this case, IMD actually declared that there is no evacuation required because cyclone is though severe, very severe, it is not going to cross as a severe, it is going to as a depression. So in both the cases, 4 to 5 days in advance, the track and intensity were predicted reasonably well. This is the Philin intensity with HWRF in 3 kilometers resolution. This is the wind speed, and this is the observation, the circles are observations, and this is the pressure drop with Philin, and the other one with the Leher. Again, the blue one, that is actually the intensity, that is wind that decrease, and this is the pressure that rises very fast, and these are the observations, the circles. So we thought that it may be due to the SST problems, or it may be due to the land surface. So we have carried out some sensitivity experiments, both with the SST and to see that why the layer was weakened. So we have removed the SST gradient by modifying the entire basin with a constant value. We modified the gradient specifically at the location where the weakening took place. And also we update the SST every 6 hours, taking the help of in-case assimilation of a GODAS SST assimilation in-case provider data, and we have taken that one. But all the experiments show that SST is not the main reasoning for the weakening of the cyclone layer. And this is a thing I am showing that the rapid intensification of the TC Fallin versus the weakening of the TC layer. If you can see that here, there is a dry, we can take place because this is, if you see that this is the relative humidity, and there is a low level minus and middle level, there is a dry air incursion to that region, and that is you can see in the subsequent one that you can see that this is what is the Fallin, and this is what in the case of layer. And in the layer case, it is actually the humidity quite less, and this is what we have seen, like where from the air came to enter to the layer. So this shows that from the north and northeast, a dry air was entered to the core of the layer, and which was not so in the case of the Fallin. And this is what is the middle troposphere, and this low troposphere, and this upper troposphere. So you can see that in the middle troposphere, we have a lot of dry air incursion is there. And that's why if you see the equivalent potential temperature, then you can see that it is quite less in the middle and the low troposphere, and that lead to actually the, and also strong wind shear is there in the vertical, so which was the cause of the weakening of this cyclone layer, and it is not due to the SST. So this is also seen again theta E and for the both layer and Fallin, so they show that the same pictures. And then if you see the vertical structure of the core of the both the cyclones, then you can see that in the case of Fallin, it is really a very intense and deep vertex, and whereas it is tilted in the case of layer, and also that is weakened, that is what we have seen. So therefore, what we have done that actually we have done a set of experiments with the soil moisture to see the impact of the land surface. So we have taken Fallin and a layer, and in both the cases we interchange the soil moisture and soil temperature that replace in case of layer with that of the Fallin one, and we increase that by 50% in the layer cases. And then we have seen that by doing that, the layer intensity actually which was dropping very fast, it is arrested for some period. And that is also seen with the before rapid weakening. So instead of a shear vertex tilted, so that is also not there at that time. So this is the layer with Fallin soil moisture and soil temperature, and in the layer case with 1.5 times of the soil moisture and soil temperature, because these both are in the same year with about 1.5 months apart. So we want to see that what is the really the impact of the land surface processes. So it shows that the land surface processes which provide the dry air, and with the increasing the soil moisture and soil temperature, it could arrest the weakening for some time. So this is a high-resolution multi-scale model. That is what HWARF system actually, which was previously 27 and 9 kilometer, then it is 27, 9, and 3 domain. So that the mesoscale convective processes that can be only represented 3D, and that is what is lacking. And this both inner nest are moving, and this is the only the one nest that is moving, 2-domain configuration and 3-domain configuration with SOR. And here, actually, as just told by Dr. Rajgopal, you can see in all the cases, the 3D one, it shows that mean track errors and intensity error both are decreased, and compared to that of the 2D. This is the case of Helen. Also, this is with the 2-domain, and this is with the 3-domain. So you can see that also it is the Hovermall diagram, which also shows that the intensity of the H3D is much larger than that of the 2D cases. And similarly, the radius of maximum wind. This is again IMD observations, and the 3D one and the red one is the 2-domain. So here again you can see that with increasing the resolution and making 3-domain, it is also improved substantially that of the. And we try to calculate the genesis potential RI index, and based on the work that is done by IMD, taking various parameters, and then you can see that this is H2D and the H3D. So this is the place, this box where actually the intensification took place, actually rapid intensification. So that is what faithfully reproduced in 3-domain configuration with high resolution inner vortex simulation here, and which was here, but it was shifted, and it did not produce at the same time, and it is worse. So, so this shows that the RI, which was also very well simulated with a 3-domain and high resolution model, and similarly, so one core temperature anomaly of the structure of the Helen. So that you can see also, this is the dots are observed, and this is with the 3D, and this is the 2-dimensional, 2-domain and 3 domains, and there also we can see that and this is vertically integrated vertical velocity. So both the cases it shows that the intensity was better predicted with the 3-domain configuration, and this is the deep layer of main wind flow to show that how it is reproduce the trough lines and the movement of this cyclone Helen. So here actually this is the FNL analysis for verification, and this is with 2-domain and 3-domain. Again, you can see that the 3-domain one better simulated the flow patterns around the cyclone Helen for its intensification. And so also the vertically integrated precipitable water. The ocean coupling, actually, we have again this we have done again with support from the HRD, and this is what we have done with IMD and INCOES and IIT Bhubaneswar together. And I am showing only one case, and again it is that as already shown by Dr. Rajgopal, you can see that this is the cyclone Oki, and the same that when actually we don't have a coupling, and you have seen that SWARP is intensifying more than that of the observed, whereas the ARW is less. But then actually after putting the coupling, so it is reduced. And so also we can see that the means level pressure, this is the observed one, and this is the coupled model simulation, and this green one is the uncoupled one, and so also 10-meter wind. So in both cases you can see that the higher intensity of strong wind and higher intensity of lowering of the pressure, which was seen in the uncoupled system, it was become more close to the one that of the observed one when we put the coupling of the high com with that of the HWARP system. And this is satellite derived wind 10 meters, and that is what is the uncoupled system, and this one is the coupled. And again, if you see that the coupled one is more close to the satellite, and so also core average enthalpy flux also, if you see, which was quite large in case of uncoupled system, because the SST is remain strong in uncoupled case because it remain a constant source of heating. And whereas here, due to interaction of the ocean and atmosphere and the fluxes and a lot of evaporation, it is substantially decreased. So that also justify that why it is the intensity was changed. So last one, I want to present our storm surge prediction, which is the more main culprit of the casualties that I have shown you. And this is what the expected storm surges in the Bay of Bengal. You see that there are some regions where we have 12 to 15 meters of storm surge generated. One is this region, one is this region, and so on. So therefore, this is the potential one. So here what we have done actually, instead of going to the classical way of estimating that only 12 hours or so we try to take, this is the IMD, what they take IMD base track, fit observations, and based on that, this is the prediction of the storm surge, and this is the track of the cyclone, of the Falin. And what we have done, we have taken the 10-meter wind, which is reasonably good, and we try to predict the Falin from 96 hours, 72 hours, 48 hours, and 24 hours in advance. And this is what is observed. Of course, we don't have any observed tide gauge along the coast. It is only post-survey data which is seen from the indirectly from the tree leaves or some person's interpretation and so on. So therefore, it is not so accurate of observations, but this is the observation and this is what is estimated by the models on different times in intervals in advance. And this is with a HVAR system, and HVAR system being wind is more intense and intensity, so it is little more, but this observation is also questionable. And so this is what is the prediction of the storm surges by the storm surge model of IIT Delhi. And this is again at different locations and with different times. So this shows that the prediction of the at point of landfall at different locations, left and right of the storm surge. And this is the cyclone Phony, which was more recently passed through. And this is again day 1, day 2, day 3, day 4 in advance, the prediction. And this is what at Puri, about 1.5 meters was storm surge. And because actually the cyclone was moved as a glazing angle, not a perpendicular way. So, and this is what is predicted by the model with the HVAR wind, WRF and HVAR wind. So the summary of my talk that in recent years, the tropical cyclones tracks prediction is improved significantly with the introduction of the high resolution ARW and HVAR systems, and the initialization of the forecast demonstration project, which IMD initiated in 2007. The incorporation of non-conventional data in the very data sparse region of Bay of Bengal, it is so clearly demonstrated that with satellite and Doppler radars, there is a extensively improvement in the tropical cyclone track predictions. The intensity prediction is also improved over the years with high resolution models. However, ARW underestimates and HVAR intensified more in terms of 10-meter wind. However, the intensity prediction improves with the coupled HVAR HICOM coupling systems because of the coupling system there, and the one-way coupled atmospheric storm surge model with that of the output from the HVAR and ARW significantly improves the storm surge prediction with a lead time of up to 4 days. Thank you very much.
Thank you, Professor Mohanty. So, are there questions or comments? You have? Do you have a question? No? Do you have questions or comments? So I have one question about
Yeah,
the Doppler radar, Doppler weather radar assimilation. You said assimilating the Doppler radar data improved the TC track forecast. But I'm wondering, the Doppler radar locates only inland of the Indian. So the typhoon track improved before landing?
Yeah, you said what happens, you said we have a large number of Doppler radars, and when satellite, it is not cost, it is for the whole, cover the entire region, Bay of Bengal and Arabian Sea, and otherwise without that we don't have any data. We don't have a aircraft, and we have only few buoys are there, which only surface. So therefore, we have seen actually in the core and also environmental impact of the Doppler radars. So we saw that even the environmental improvement also improved the track.
Yeah. Okay. So, any other questions or comments? No? So how about the remote questions? No, okay. So if not, we would like to move on. So thank you very much.
Thank you.
So next presentation is by Dr. Francis of Indian National Center for Oceanic Information Service.
Good afternoon. First of all, let me thank the organizers for inviting me to give this talk. This topic is slightly different from the last two talks. It's on the intense rainfall events in the west coast of India. To be honest, I have not been looking at the intense events for the last few years. And thanks to Partha for asking me to look at it again. So I will be talking mostly on the work which we have done some time back and some new analysis which we have done in the recent years. So if we look at the climatological rainfall distribution over India for June to September, this is very familiar to everyone. What we can see is that there is a lot of rainfall in the west coast. In fact, two subdivisions in the west coast, the Konkana and Goa and coastal Karnataka, receives the maximum rainfall in India during the summer monsoon season, followed by Kerala and of course Northeast. But we can see that the area of these three subdivisions are quite small. But if you look at the events of rainfall above 20 centimeter which happened in 2019, there were 213 such cases all over India. And if you increase the threshold, then the number comes down, 29, 19, 8, and even above 50 centimeter per day, there were 4 cases in the last season. If you look at the same statistics for the 3 West Coast subdivisions, it's interesting to see that about 20 centimeter per day we had 41 cases in the last season, and 35, it was 7 cases, and 40, it was 5 cases. If you look at this in comparison with this is about 25% of the cases just in these 3 subdivisions of over India. But very high case intents like 45 and 50 are rare. So let me give a brief outline of the talk. First, I will talk about the intense events over the West Coast, its space-time variation, and the systems which are generally get associated with these intense events. And then I will talk a little bit on the recent events in the recent years. I will introduce equatorial Indian Ocean oscillation to understand these recent events a little better. So I'll take a pause here and then introduce Equino, and then again come back to the events of the last few years and the convective systems associated with that. Now, if you look at the West Coast, we know that West Coast has a good orography. So we have to choose the stations carefully that we don't get the orographic rainfall into this analysis. So we made sure that the stations are really coastal stations, and we should have sufficient data to analyze this. So when we did this analysis, I had station rainfall data for several years, 1901 to 1990 or something like that. But we found that if you want to have a good statistics, we can select only 30 stations because these 30 stations only have sufficient data, continuous data for about 37 years. So the analysis was restricted to this period, 1951 to 1987, and these 30 stations. So we have published this some time back in Meteorology and Atmospheric Physics. Again, going into the statistics of these rainfall events, we know that the West Coast receives rainfall on almost every day. If one or the other station must be getting rainfall every day in the season. So it is not surprising that 99.37% of days of these 4,514 days we consider for the study, at least one station received rainfall. We should not say that's a good rainfall, but rainfall. But as we increase the threshold, again, if you're looking at 10 centimeter per day in any of the stations in this 30, that number comes down to 58, then 15, it is 28, and if you look at 20, it's around, if you go to 20, it comes around 5, and heavy intense rainfall events in that period was really rare. So to have a good statistics, we should have good number. So we thought 20 centimeter per day is a good threshold because they are not very frequent. At the same time, we get enough sample to do the analysis. So we fixed the threshold for looking at this analysis is at 20 centimeter per day. And if you look at the individual stations with this threshold, what we find is that on an average, about 0.5 to 1% of days, there is a possibility of getting rainfall about 20 centimeter per day in these stations. But it accounts to about 5 to 10% of the total rainfall in these stations. So a very small fraction of events can contribute to 5 to 10% of total rainfall, seasonal rainfall. And in some stations, it has gone up to 17% of the seasonal rainfall. At the same time, the low intensity rainfalls, less than 5 centimeter per day, 80 to 90% of the time, this is the kind of rain we get, but that accounts to only 50% of the total rainfall in the subdivisions in the west coast. So it is important to see how these heavy events contribute to the total seasonal rainfall. So a good method is to look at the burstiness index. It is nothing but we have to arrange the rank the rainfall in descending order and just compute the cumulative rainfall from the top. So if you have a evenly distributed rainfall, that means every day equal rainfall happens. This is what the kind of line you are going to get. It will be a diagonal line. But naturally, it's not going to be like that in all the cases. So if the events are more or less, heavy events are more frequent, we may get a kind of curve like that. But events are very rare, but they account for the maximum rainfall or the total seasonal rainfall. It may look like what we have seen for the Porbandar. You can see that in Porbandar, which is in the northern part, 20 days which has heavy rain has contributed to almost 100% of the seasonal rainfall. At the same time, in Karwar, the distribution is little better. They were more evenly distributed than Porbandar. So if we look at the variation of these events, about 20 centimeter, and of course I have shown the 15 centimeter per day case also here. If you look at these events with variation along the latitude, what we see here is that maximum number of cases happens somewhere in the central part of the west coast, which is like coastal Karnataka and Konkana and Goa. At the same time, the events in the northern side and the southern side are not very frequent. But you must remember that the station which I talked about, Porbandar, which is in the northern part, this rainfall also is very important because that accounts for the maximum of the seasonal rainfall. So this is the kind of variation if you are looking at the along the latitude. At the same time, if you are looking at the probability of happening these events with time, so you have 37 years of data, you use that data to find the statistics on a daily basis. And what we find is that there is a potential for getting intense rainfalls. We have different thresholds, 15, 20, and 25. So let us focus on 20 centimeter, which is these dashed lines. The probability is high somewhere in the second half of June. Then we have another in the second half of July and maybe in the first few days of August. These are the time when you can expect very intense or intense rainfall events in the west coast. And this is consistent with the seasonal distribution of rainfall, that we have a peak somewhere after June. So this is where the peak of the intense events happen, and then the second half of July. So this is how the rainfall also evolves. So seasonal rainfall reflects the pattern of the intense events, distribution of the intense events. So next, what we have done is that for the period of 75 to 87, where we had satellite derived outgoing long wave radiation, we looked at the spatial pattern of OLR day after day on all these events. We could count 100 intense rainfall events. In this case, events are like if you have, in a given station, if you have 2 or 3 days consecutive intense events, we consider as a single event. So like that, if we count, we got 100 such events. So we looked at one by one and classified into different categories. The first category is a kind of longitudinally extended pattern, which we can consider as a tropical convergence zone, which goes all across the Bay of Bengal and to the Pacific. And this accounts for about 63% of the total events. So majority of the systems are or majority of the events are associated with large-scale systems. And the second category is convection confined to the west coast or maybe to the western Indian Ocean. This is about 15%. So in this case, you don't find much convective activity in the Bay of Bengal or rest of the place. This is the second category. And the third one is metropospheric cyclone, which is another important feature which occur during the monsoon time specifically, but relatively rare. So this accounted for about 6 cases, and that too happens mostly in the Gujarat region, and that's where the station Porbandar situated. So most probably those events were associated with the MTC systems. And we could only identify only one system which is relatively isolated and not associated with any large-scale convective systems. This is the kind of statistics which we got, and there were events which were combination of different things like offshore plus TCC or MTC plus TCC, but they are relatively rare. But majority of them we found that are associated with large-scale system. So when they are large-scale associated with large-scale system, it is possible that other stations also must be getting good amount of rain. It may not be intense as 20 centimeter or so, but they also must be giving enough good rain. So they need not be very isolated rainfall events. Now, with this background of study which we had done some time back, I started looking for some data for the recent years. One important source of information is this IMD's Climate Diagnostic Bulletin. The problem with analyzing this rainfall data is that it's huge amount of data. But luckily, the Climate Diagnostic Bulletins gives the list of events, which are about 12 centimeter and 21 centimeter per day. So you will get all the stations, all the subdivisions where it recorded above this threshold on a daily basis. And here I considered only 3 subdivisions, as I said earlier, coastal Karnataka, Konkan and Goa, and Kerala. And the data was available with us from 2008 to 2019. This is available in IMD's Pune's website. So we could easily get the access to this. And it's what I have plotted here is the total number of events in a season as black stick, and then individual months, you will see June, July, August, September, and every year. What is very interesting to note is that the years 2018 and of course 2019 stand out as years with or seasons with large number of extreme events. If you look at the number in 2019, we had almost 35 cases or 37 cases of intense events in these 3 subdivisions. That means once in every 3 days, there was a possibility to get a intense rainfall in the west coast. And so as in 2008, it was quite good. And even 2011 was a good year with a large number of intense events. And if you look at the monthly statistics, July and August of 2009 had several events, and June of 2018 was having a large number of events. And surprisingly, another year in which I got a large number of events is 2009. Remember, 2009 was a huge drought, but still we had good number of events in the west coast. So this is something to be noted, that we need not look for extremes of monsoon to get extremes in the west coast. We can get independent of that also. But you have to remember 2-3 points. When IMD gives this data, if multiple stations of a particular subdivision recorded about 20 centimeter per day, they count only one of it. The highest rainfall only they will report. So it is possible that the actual number of stations are much more. But since it's in the same day, we can count it as an event. And in my analysis, if multiple subdivisions recorded more than 20 centimeter per day, that also I counted as a single event. Otherwise, the number would have been quite large. And as I said, 2019 is really fascinating. We had 2 months, consecutive months, with large number of events. And we may remember that 2019, by August, the western, the states like Karnataka and Kerala, and to some extent Maharashtra also got severe floods. And that could be because of these events in consecutive months. Even in 2018 also we had flood. In fact, June had several such events, and then followed by July, August with quite good number of events. So these events might have helped or triggered these floods in these regions. Now, for 2019, if we look at the Euler pattern, what I have plotted here is the latitude time section of Euler, and I have shaded only 180 and 200 watts per meter square. This is at 90 degrees east. So what we can see is that, and the intense events are marked in the axis. So you can see that all these events are associated with the northward propagating phase of the TCC. And particularly in this case, July, several days, persistently there were intense events. This was associated with a lot of convection in the Bay of Bengal, and maybe this is the culmination of the northward propagation phase. And in other cases also had several, all these cases were associated with the northward propagation of the TCC. And if we look at the spatial pattern of a particular case, like 27th July, somewhere here, and what we can see is that a good convection over the bay and a continuous TCC. But what is more fascinating to see is that there is a strong link with the convection over the western equatorial Indian Ocean. This is particularly important because 2019, we had seen this in several days consistently. So I will pause for a while here to discuss on the discussion of 2019, and then introduce the main drivers of intra-annual variability of monsoon, because the definition of equino is important for understanding our next few slides. And we know that one of the major driver of monsoon is ENSO, and I'm not going to explain that here, but the another mode which affects the monsoon significantly is the equatorial Indian Ocean oscillation. This equino is nothing but an oscillation in the convection between the eastern and western sides of the equatorial Indian Ocean. When there is a positive equino, we have enhanced convection over the western Indian Ocean, suppression over the eastern Indian Ocean, and the negative phase, it is just opposite. What is interesting to note is that associated with this, we have winds, equatorial winds. In the case of positive equino, we have easterly anomalies, and in the case of negative, we have westerly anomalies. So the wind anomaly at the equator can be a good indicator for the strength of this equino. So we earlier we used this equatorial wind as an index for the equino. But since we have now good amount of data on of outgoing long-wave radiation, this may be much more reliable. So now we have defined the index for equino based on the difference in the Euler anomaly between east and west, which we term as equino-Euler. And we can see that in a, if you look at the correlation between the convection or the Euler over this box, this is the eastern Indian Ocean box, with Euler everywhere, we can clearly see this oscillation. It is clearly negative correlated to the western Indian Ocean. And if you look at this one, then you will see the opposite correlation here. So this is the phase of oscillation, which has a significant impact on the intra-annual variation of monsoon. And if we look at the climatological convection over the equatorial Indian Ocean, east and west, which is shown in blue and red curves, we can see that the East Indian Ocean convex almost all the time. What I have plotted here is the OLR, so lower OLR means larger, more convection. The convection in the East Indian Ocean is kind of low during the monsoon time. But if you look at the West Indian Ocean, most of the time there is no convection, and convection happens, if at all something happens, that only happens from kind of end of May to August. So this is the time when both the region has equal probability to have convection, and that's the time you can see that equatorial winds are almost close to zero, because there is a probability to have convection both sides. So this suggests that if there is a, and with the correlation of this opposite correlation between an east and west, this suggests that if somehow we can suppress the convection over the East Indian Ocean, chances for getting convection over the west is high, because climatologically both have equal probability, and there is an edge for East Indian Ocean, but if it is suppressed, since this opposite relationship is there, it can trigger the convection over the West Indian Ocean. But we should keep in mind that to keep the convection going, we need the SST of the West Indian Ocean to be above the threshold for deep convection. What I have plotted here is the percentage of grids in which OLR is in different bins, but I have divided it in two classes. One is SST less than 27.5 and another is 27.5 and above, and this is for the West Indian Ocean. So when the SST is below 27.5, you can see that a mode of OLR, or even large fraction of OLR, is about 240 watts per meter square, and this is monthly time scale, so 240 can be considered as a good indicator of deep convection. So you can see that majority of the grid points do not convect if the SST is less than 27.5. At the same time, if you increase the SST, then the mode shifts, and you can see that many grids, or most of the grids, more than 50% of the grids get convection. So keeping the SST above this threshold of 27.5 is very important. But if you look at the climatological distribution of SST in the Indian Ocean, of course, May is warm everywhere, but as the monsoon set in, the West Indian Ocean starts cooling. This is partly because of the upwelling and partly because of the heat flux loss due to the strong winds and convection. So this is a challenge to keep the SST above threshold. And you should know that SST in the West Indian Ocean is mainly determined by the heat flux terms in the due to the monsoon winds. What happens if the SST goes below threshold? The classical example is 2003, where the convection in the West Indian Ocean, here I have defined an index for convection. This is nothing but the sum of OLR minus 200 of every grid point, where the OLR is less than 200 watts per meter. It's nothing but I just picked up the points where the OLR is less than 200 watts per meter square and then subtracted from 200 so that I get only the values where it is below 200, and that I summed up. So it gives the spread as well as the intensity of the convection, and this is done for the West Indian Ocean and for the East Indian Ocean. You can see that 2003 there was a lot of convection going on the West Indian Ocean, and here in this case I multiplied the East Indian Ocean with -1 so that it goes in the opposite direction. So East Indian Ocean remained more or less suppressed. This itself will show us how the relationship between the relationship of convection of the East Indian Ocean and West Indian Ocean changes. Once convection happens over the west, east remains suppressed. And then as soon as, and this is what the SST looks like, the continuous lines are climatology. The lines with dots are actual 2003, and 27.5 is marked here. East is red, blue is west. And we can see that west was really warm to begin with, but it cooled rapidly, and by about end of July, it crossed the threshold of 27.5. And you can see that soon after the convection switched off in the West Indian Ocean, and as soon as the convection is switched off in the West Indian Ocean, east picked up. And there was a speculation that 2003 would go into a strong Indian Ocean dipole, but it just got aborted because of this switchover. So the main problem was that SST went below the threshold for deep convection. So it is important that the SST in the West Indian Ocean to remain above 27.5 degrees Celsius to keep the convection going. So with this background, let's come back to 2019 story. And again, I have plotted the Euler and Euler anomaly pattern for a larger region in July 2019 and August 2019, where we had several events of intense rainfall in the west coast. What we can clearly see is that there is a strong link in the convection between the West Indian Ocean and the convection over the west coast, and it's much more clear in the actual Euler, and even in August also you can see that very clearly. So this happened very frequently because we had several such events in the west coast in 2019, July and August. So even the mean picture of a month for July and August, we can see this pattern very clearly. Now, when we looked at this 2019 monsoon, it was really interesting for us that the June was below normal, so there was a kind of speculation that this year is going to be a drought. Then July started picking up, but then onwards we started seeing the convection over the West Indian Ocean keeps going, and then we analyzed the ocean and atmosphere system, and we could speculate that, okay, this year is going to be good because the West Indian Ocean may keep convecting. But the challenge in front of us was to make an educated guess on how the SSTs of the West Indian Ocean going to be. So we made this educated guess, and recently we have submitted a paper to Current Science with a validation of this because it turned out to be a good speculation. So the reason we could give a good speculation was that when we analyzed the data from equatorial Indian Ocean, there was a buoy located at 80.5 degree east and equator. It's part of the Rama buoys. What we could see is clearly there is a deepening of the thermocline. 20 degrees Celsius isotherm is considered as the kind of depth of isotherm. So we can see that somewhere after April, we can see a sharp increase in the depth of 20 degree isotherm. And this, again, there was another event sometime towards the beginning of July. And when we looked at our equatorial winds, what we found is that somewhere in April, we had a strong westerly burst. This was associated with an MGO propagating from the West Indian Ocean, and it reached the East Indian Ocean. Then it split into two cyclones. First was the southern one, and then the northern one came subsequently. It became a very extremely severe cyclone. So this wind was associated with the passage of that system. And associated with this wind, what we could see is that there was a deepening of, what I am showing here is the sea level elevation. So there is an increase in the sea level right at the equator. This is a signature of a Kelvin wave. We can see that it propagated to the East Indian Ocean, and this is the signature of a downwelling Kelvin wave. And then we can see that subsequently it got reflected as downwelling Rossby waves and started moving this direction westward. And you can see that it is constantly moving with the speed. We calculated the speed, and that was something matching with the speed of oceanic Rossby wave, first mode Rossby wave. Then this is the location where we picked up the buoy, and you can see the timing. This was on 5th June. That's the time it reached the peak. So we know that there is a downwelling Rossby wave propagating from the East Indian Ocean to the west. And previously this happened in 2007. Similar system happened, and we could establish that the deepening of thermocline and isothermal layers in the West Indian Ocean with the arrival of these Rossby waves. So this time also we calculated that by end of July, this can reach here and lift the thermocline there and, deepen the thermocline there and keep the ocean warmer there. So this is this was the theory behind our speculation, and it turned out to be very true, because if you look at the SST of the West Indian Ocean in 2019, the blue one, it started dropping with the deep convection going in the West Indian Ocean. And even when in July, end of July, it even crossed that 27.5 mark. But immediately after that, it came back, because this is the time when that oceanic Rossby wave arrived there and stopped that cooling tendency. At the same time, the East Indian Ocean kept on cooling, and we could get a sustained convection over the West Indian Ocean and suppressed convection over the East Indian Ocean. So this was the proof of that concept, that we can get a sustained convection over the West Indian Ocean, provided we have the right oceanic conditions. Now, if you look at the other two cases, 2018 and 2019, there also you can see a strong link to the West Indian Ocean. May not be that spectacular like 2019, but still that convection is linked to the West Indian Ocean, even in 2009 also. So this gives us a hint that not only for the seasonal predictions, for the predictions or understanding the extreme cases of rainfall in the West Coast, we need to keep watching the convection over the West Indian Ocean, see whether the conditions are favorable for that. This may give a good hint to understand, maybe to give an educated guess again on these events. So let me conclude this with the following statements, that we can consider 20 centimeter per day as a reasonable threshold for the intense rainfall events in the West Coast. And of course, this need not be true for other subdivisions. So for the West Coast, this is good. And in many stations, these contribute significantly to these events contribute significantly to the seasonal rainfall. And most of these events are associated with large-scale convective patterns. And there's a strong link between the rainfall, intense rainfall over the West Coast and the convection over the West Indian Ocean. So it is important to keep a watch on the convection, ocean atmospheric processes that lead to the sustained convection over the West Indian Ocean. Thank you.
Thank you. So, any questions or comments?
It sounds very, very plausible. The only thing that you could have added is from the ocean reanalysis or something that to show the Kelvin wave better, to show the thermocline.
Yeah, that's right. I have not done that analysis, but we can do that. There are a few buoys also, we can check with that. But for 2007 case, we have done this analysis and shown that heat budget and how it deepened it. For 19, we have not done it yet. Thank you. Yes.
Hello, Francis. Very, very nice talk.
Thank you.
So you showed those events more than 20 centimeters per day, west coast of India, and you said that most of them are linked to the TCS, and then offshore convection, and then the MTCs.
Yes.
I agree, and actually, I want, tomorrow maybe we have did some work on MTC,
yes.
And all the three are in a way related.
Related, yes.
So they are not really independent.
They are not really independent. In fact, we have seen that MTC may originate from the TCCs
exactly.
itself.
So they are in a way MTCs. Many of them are related to that.
Yes.
And the second thing is 2019. Many of the cases which you showed, they had MTCs.
Okay.
So out of 5, about 3 or 4 were with MTCs.
Okay. So, yeah. I have not done that analysis for
so
19.
I'll present it.
Okay.
Other questions? So corresponding to the Shige's presentation, I guess some extreme rain may be given by warm rain process, not by deep convection. Do you have some comments or statistics?
Yeah, in fact, for 1985 to 87, we looked at INSAT data that time when I was doing that analysis. And we found that almost all the cases had very deep convection. Probably maybe that's true for those cases. Only one case I could found a shallow cloud giving an intense rain. But that was only for those 4 years analysis we have done.
Use the microphone.
Partha has just stepped out, but Partha will tell you that the 2018 Kerala intense event, I think Bhatt is here, he knows that. The 2018 also Kerala had intense events. And of course it was a collection of events that gave the intense flooding that everybody read about. But I understand that several of those were warm rain in the sense, and I think Tara, she's not here, maybe somebody from this group could answer. So we have had significant intense events, which are also warm. But in terms of statistics, we did not find that there were too many of them.
Okay, thank you.
Okay. So any other questions, comments? Are there remote questions? No? Okay, so thank you very much for Dr. Francis. So we would like to move on to the final presentation in this session by Dr. Partha Mukhopadhyay of IITM.
Okay, so good afternoon to all of you. And presentation of my talk is recent developments in short-range forecasting, challenges and future roadmaps. Preparation of this talk was very difficult because we were in the middle of dance till late yesterday evening. But anyway, I am fortunate that I have a very big group of talented, colleagues and students, and also some of my earlier students, also people, scientists from IMD, and also from NCMWF. And there are also informal collaborations that you will see in the slides, which is from ECMWF, like Peter and Niels Wedi. Also Jimmy helped us in some development. There is Dr. Han from Dr. Hong's group in Kiev and so on. So outline is very straightforward. What I will do is that I will not advertise too much about the strength of these models. I will mostly emphasize about the weaknesses, but also I will tell about some of the strengths. And I will also try to tell about the recent new approaches, what we are trying to add in this, and there's challenges, and then possible future roadmaps. So in India, I think yesterday Dr. Sahai was telling, we have a monsoon mission, and under that we have a suite of models for various space and time applications. Like on the top, you can see that it's a dynamical model for seasonal monsoon predictions, which currently use CFS version 2 at T382, but it started with CFS v2 T126. But what needs to be kept in mind that the dynamical core of these two models till today is Eulerian. And there is a large number of papers have been published using this activity of this group, which are available in this website. And then there is a development of extended range forecast, which Dr. Sahai yesterday elaborated. And that use actually an ensemble of multi-models, CFS v2, T126, T382, bias-corrected GFS, and so on, but they are all, again, in Eulerian. It has to be kept in mind. And the reference of this group are available, again, in this website. And what I am involved, or my group is involved, is this in short-range ensemble forecasting, which started with GFS Eulerian T574 with 21 members, and it was there till May 2018. And then, in between, we started running the deterministic semi-Lagrangian. So this is the first switch over from Eulerian to semi-Lagrangian dynamical core. That happened in June 2016, very recently. And then we switched over, and we started running a very high resolution, TE1534, 21-member ensemble forecast system since just last year, 2018. And you have just heard that we started this ensemble forecast in 2018, and we got the Kerala rain in August 2018. And then this was not exactly under monsoon mission, but this suite of model is a huge promise from India, which is now participating in CMIP 6. These are the two prominent references one can see, which tells about the full development. And this is based on, again, CFS v2 T62 in Eulerian. So this is the whole suite of model for which IITM is dominantly involved in this development. And finally, all these systems have been transferred to IMD for operational forecasting. Having said that, I have added this, 3 tables just before lunch. So, I mean, we were discussing about model, but it is not just model. It is not just the problem of model. I mean, what we have heard in the last 3 days, these are the list of issues with the model. And what are those issues? We expect the mean state should be perfect. We also expect models should correctly capture the variability. And we also expect there should be a seamless modeling system, meaning rainfall from my terrace to backyard to MJO. We also expect the model should do cloud radiative feedback and balance perfectly. We have learned from Graham that high cloud is an issue, and we expect models should do it correctly. Low cloud has a prominent problem in all model, and we expect models should do it correctly. Diurnal variability also should be correct. And finally, model should produce a correct forecast with longer lead time in all space and time. So this is the expectation and list of expectation from a model. But what is involved with this, I mean, we should not, I cannot ignore these two. I mean, if I'm working under a boss or if I'm working under a funding agency, they will expect this. They will expect reliable forecast from, from a system like fog, few hundred meters to monsoon with longer lead, with minimum uncertainty. They don't like any uncertainty. And, they will ask me to connect my forecast to the last mile, to the last person in the society. And you do not really know who is this last person is, okay? And also, they will expect a lot of publications with high impact. And this box has very less time. They don't have time. And then another group, which is very important, is our students, which we have to guide. They need degree, and they have a career. They also don't have time. So these two boxes are running out of time. But this development, we really do not know how much time. So this whole problem is ill-posed, okay? You cannot close it, okay? So we are starting from this ill-posed problem, which cannot be closed, and we are trying to solve this with the two very important boxes which are running out of time. keeping this in mind, this is a very popular figure. Everybody knows it. The story starts from CMIP 3. CMIP 3 doesn't change in CMIP 5. Looks very similar, although many of the things have changed. This is a very old paper of Dae-Hoon Kim, now a faculty in University of Washington. So he used so many models, and he was desperately trying to see whether the models are capturing the MJO properly. And he was frustrated. No, I mean, of course, this is observations. Apart from that, and don't look at this, none of the models could capture the MJO properly. And this slide I borrowed from long back from Emilia Jean, and this was slide from Athena, that big project where many models were compared. And here what you see is ECMWF-IFS running from T159 to up to T2047. This is TRIM, this is NICAM. And you can easily make out that there is not much difference between 159 and T2047, except like using a very high pixel camera, you get the error more prominently by using a high resolution model. If you look at the variance, story is even more sorrowful. It doesn't capture the variance at all. Okay. And now this was some time back. We were just analyzing the TIGI forecast. And what we found is that the models are good, in capturing the mean. The red is ECMWF, blue is NCEP. The mean is good, but if we go to the synoptic scale, the skill falls down. So here is very clear. These are all skill for the mean rainfall, and this is mean, and this is for synoptics. So there is a big, So this is all these slides should be kept in mind. Now, keeping this in mind, what are the issues in CFS and GFS? So CFS, the lower resolutions has a colder tropospheric temperature bias, but the higher resolution has a warmer tropospheric temperature bias, and I'll come back to this. In spite of contrasting bias, the rainfall bias of both these models are same, and both are having large dry bias over the land, over the global land, and large wet bias over the global ocean, in spite of colder SST in this and warmer SST in this. And in both these models, synoptic variance is highly underestimated, and the ISO, which is the intraseasonal variance, is overestimated. And diurnal life cycle is equally incorrect. And this is one sample of this slide where you can see that this is precipitation. Blue is negative, red is positive. You can see clearly the double ITCZ. All over the global tropics, tropical ocean is raining. Lands are missing rain. Here SST is cold, here SST is warm. The lower level wind are weak in both the model. And this is, of course, a climate-free run where you can only see the model bias. And this is the tropospheric temperature is cold, it is warm. And this is a picture which says that, this is the GPCP variance. If you take TRIM, you take any data, the story is same. If you go to CFS V2, which is the lower version, you can see these ISOs over these regions are overestimated, like it is 50 to 60%. And whereas the synoptic, you can see lots of green and blue, so it's underestimated. So it means that it is perhaps not doing very good for capturing the synoptic disturbances or synoptic systems. If you go to the higher resolutions, story is broadly same. You can see here, this is the ISO, it's overestimated. And this is the synoptic, and this region is missing. And this is the diurnal. So, and the story is not encouraging at all. So, the whole day CFS keeps raining in a similar manner. Only thing, because it is high resolutions, there are many more grid points, so you get a thick broom. Here you get a thin broom. That's all. Nothing changed. So, yeah, and okay, this is just a scatter plot of precipitations and velar. It basically shows. So what it shows is that 180 watt per meter square velar means it is deep cloud. So there you can see there are a lot of rains, at these rates, which are coming from the deeper cloud. But in all these models, right from T62 to T126 and T8, you can hardly see, you can see very few dots. So one of the reasons for this, what we found is, this is a very prominent metric many people have used, right? It was used, I think, first by Dave and Catherine in their paper. So what it shows basically, in the x-axis we have a logarithmic of rainfall. So when I have 0 means 1, 1 means 10, 2 means 100, okay? And this is a pressure level. So the observations suggest that when I approach towards the heavy rain, so there is a gradual deepening of the moisture, right? This is the 90% level. And then I get heavier rain. But if you look at T62, T126, T82, if I don't tell which one is what, you cannot make out. They all look same. So the moist process, the treatment of the moist process remains same. And that actually spoils the skill of this, the skill of rainfall process in this high resolution even worse. It affects the high resolution model even worse for not having correct physics of, for moist process. But this figure looks broadly similar. And this is a recent paper by one of my group colleague, Snehata. So what we found, actually, this is precipitation efficiency. It is a precipitation rate divided by total grid box cloud water path. What we found is when the rainfall is a lighter rain rate, so they all, they are good friends. But when we go to heavier rainfall, and this fellow with the green, his efficiency is decreasing. So because there are lots of, you are adding many more grids, okay, where the model is fumbling to produce rainfall. It doesn't know what to do. So it is actually, its precipitation efficiency is decreasing. Whereas T126, although you cannot compare with observation, but still, to some extent. So this is one reason why, okay, this is another plot of Villa clad is, and things are not in place. I think the Bolium also showed this. Okay, this is another paper by Avik et al., where you can see CFS, high resolution, doesn't have, hardly has any Kelvin wave, right? There is no existence of mixed Rossby gravity wave, and this is consistent with lack of synoptic variance. So the deficiency is consistent. Okay, so yeah, I feel the story starts from here. And this is a very, these are the famous papers, which Dave also referred, many other people referred. This is one of the problem. We are assuming quasi-equilibrium. We assume that my moist convective process will be always be a function of large-scale process, and that it doesn't happen. And if I increase the resolution and still believe in this, then I'm in more problem, right? And these are all connected, and this is, at the center is the cloud process. And this is also a very important initiative by Mitch Moncrief in BAMS, where actually they explained the interaction of the scales, and they emphasized the importance of the mesoscale parameterization in the global model, which is completely non-existent at this moment. So to summarize, so if I start walking from equator to pole, I come across this type of clouds, right? They're all different types. And as Dave was mentioning that Arakawa Subert, although today I'm happy because since morning I'm finding many people are appreciating SAS. That makes me happy. But SAS, of course, doesn't realistically capture all this variety of spectrum of clouds. That is one problem. And second was this quasi-equilibrium. Now this is one of the paper we recently published because we started running GFS from 2016. So it's a mean of 2016 and 2017 GFS, 1 day, 3 day, 5 day, and 8 day rainfall bias. And the correlation, and you can see, if you just look at the correlation, you will feel very happy. But if you look at the details of this map, you will not feel happy. That's why we should not always look at the correlation. So you can see that, I mean, anybody can see, a child can say that these pictures are too much red. So it's raining too much everywhere. But there are some strategic points where it is not raining. For example, this bay, this Bay of Bengal, Head Bay, where is a breeding ground of low pressure and monsoon depressions. And you see in all the lead times, it is either white or it is blue. So it's still not capturing. We have gone to T1534, we have gone to 12 kilometer, but that systematic error is still persisting, okay? And if we go to one single year, 2019, this year, that problem comes more prominently, okay? And we know this year, as just now Francis told, there were a lot of activities here, and see in all lead times, it is missing. There were lots of activities in Arabian Sea as well, and in all lead times, it's missing. But somehow, pattern correlation, it will give. So this is a serious problem. It needs to be fixed. And you remember those boxes, okay? And this is the this is the rainfall PDF over different regions, Central India and Bay of Bengal, Northwest India and Western Ghat. You can see that the model is still producing lighter rain sufficiently, but when you go to the heavy rain, model is not able to capture that. And this is also consistent with its climate, the coupled counterpart. And this is 2019 to bring more prominently the problem of the model. Okay, this is the IMD GPM data, and you can see this, we start from 6.5 centimeter, which is as per IMD, the heavy rainfall category of this thing. So our scale starts from 6.5, where many people don't like to evaluate their model. But so 6.5 to 11.5 centimeter, 11.5 to 19 beyond 19.5 centimeter. And this is observation, and you can see there, Francis also was showing there was a huge rain in August and September. It's very, very clear. And if you go to model, day 1 forecast, of course, you can see the numbers here, and you can make out your own conclusions. So it is falling apart. And day 3, so by the time we are reaching day 3, the model is groping, okay? And so you remember the last mile you have to connect. And so this is over Maharashtra, but this region also experienced, huge flooding. And although in the day 1, for this category, it is capturing in July and August, but in September, it's not so. And when we go to day 3, again, it is the same, story is same. And we go to Kerala, okay, and for the heavy rain category beyond 11.5, conclusion is same. And this is the ensemble, okay, the 21-member ensemble, the rainfall time series, and you see this is for, I think, 24-hour lead, this is 48-hour lead, and this is 72-hour, and this is, I think, for, this is for August, this is for July, and this is for Mumbai, Pune region. This region also experienced a lot of rain, and what you see is that, in 24, and for black is the observations, you can see that in 24-hour, some peaks it is trying to capture, but by the time it goes to 48 and 72, all the members unanimously is going flat. And you can see it here even in August, so irrespective of month. So, so this makes someone very, gloomy. So you may feel then, let us leave the room. What is the point in doing business? But But there may be some strengths. Now I will advertise a little bit. So this is in statistics, it looks good, okay? And this was the older model, T574 Eulerian, which I told. With respect to that, this T1534 is doing better. And you can see, this is PR skill score, and if I draw some line here, I can see the blue dashed line is actually coinciding with the black solid line. The black solid line is day 5 forecast, blue dashed line is day 3 forecast, so it is good. So we have actually gained 2 days in statistical sense, but if you go to individual event, individual year, region to region, huge problem. And this is another statistics, and this is from 2012 to 2019. And this is bias means forecast divided by observations. So if it is more than 1, model is having over-predicting. If it is less than 1, model is under-predicting. And you can see, this red curve is for 5 centimeter and black is 2 centimeter. And you can see in the recent year, the bias is reducing. That's a good sign. Whereas probability of detection for both this rainfall threshold, it is improving. That's also a good sign. The false alarm ratio in the recent, from the time we are using the semi-Lagrangian 12 kilometer, it is showing even day 3, it's showing a dip. That's also good. And this is CSI, another measure. This also shows a increase. So if I show these last 2 figures, you will feel very happy. We also feel happy. And this is another metric people nowadays use. This is called chiclet diagram. This actually looks like a chiclet. So this is the rainfall time series. This is the lead time. And this is forecast minus observations. So if you see a lot of blue colors, it means model is underestimating. If you see a lot of red colors, it means model is overestimating. So this is T574 Eulerian, which we used to run. This is T1534, and this is for this year. That is for some other year. So one major thing what you can see is that earlier we were doing up to 3 days, and now we are going up to 8 days. Actually, we are going up to 10 days. And even if we are going up to 8 or 10 days, I don't see totally blue, right? Initially, there are some blue shades, but then August and September, over central India, it is light red, right? So that's good. So again, statistical sense, model is good. And this is another good part. Cyclone, we are doing pretty well. And this is the probability derived from these 21 members, which Roberto was talking. It is working well. And the last man in the society also feels happy. They're getting some meaningful warning from this ensemble forecast. And this we have recently developed, which Secretary was mentioning on the first day. It is the percentile derived from the deterministic. We could not still compute the EFI because we don't have the hindcast for the ensemble GFS. So we cannot compute EFI. But we could because we have the deterministic model hindcast, so we can compute the 90th and 95th percentile, and we can give the extremes. And this also is working pretty well. Because when we cannot get the number, you give the percentile and you give the probability. And this is the cyclone, I think, funny. It's a very, very success story of all of us. And you see, even from 29th April, initial conditions, spread is not very large, and the probability of strike, this is a strike probability, 50 to 90%. So this is also a good part. And this is the recent cyclone, so Bulbul, which just crossed to West Bengal and Bangladesh coast. This model ensemble has worked better. So in a sense, ensemble actually is working relatively better than the deterministic. And okay, this is what we are discussing about the Kerala rainfall of last year. This is a NASA animations, okay? I can see this is the rainfall. If I go to next slide, this is the GFS, but 24-hour lead time. You can see these two blobs, which will eventually come out very prominently. Okay. Yes, these are the 2 points. And now if we compare with our model along with the CMWF and NCMWF unified model, the event actually happened on 8th and 9th August and then 15th and 16th August. And 8th and 9th August actually model did not give much. And okay, and this red line is the climatology. Okay, climatological daily rain over that region. And it could not actually, so model was actually producing climatological rain. And ECMWF slightly gave some indication, and this is day 1, okay? This is day 1 lead time. actually produced on 9th August, it could produce on day 1, almost what is observed. And in 15-16, many of the models could capture on day 1, but the problem was with the lead time. With the lead time, we could not capture this event. It was neither captured in extended range of NCEP. It was neither captured in extended range of ECMWF. But following Peter Webster, he made publications of Pakistan rain, and we followed a similar strategy. And when we tried to plot the probability of the rain plus 1 standard deviation and then 2 standard deviation and 3 standard deviations in this way. This is for GFS and this is for ECM and this is for And we find that, yes, I mean, all these models are actually able to give some indications, even up to 4 days. And this probability goes up to 70%. So the deterministic model, which was appearing to be meaningless, when I extract the informations from ensemble, the information can still be meaningful. So that is one thing. But this is the last mile story. So even with all these biases and all these inaccuracies, so we are doing all these things in India. And this is solar and wind, and some solar wind company was telling me, can you give me 15-minute wind forecast at my farm 1 month in advance? That's a problem. You don't know what the last man will ask. But we have to do that. We can't avoid. We can't tell that you wait till I make my recipe accurate, then I will serve you. So you have to serve. So these are all the things we are serving, and people are accepting it with reasonable satisfaction. But so everybody will agree that we are in a deadlock, okay, in terms of model development, and then deadlock was was attempted to be broken many times. And once it was attempted by Dave Randall in 2003, then again he wrote another paper in 2013 beyond the deadlock. But still we are in deadlock in 2019, right? And these are the prescriptions, he said. So LES and CRMs and GCRMs and MMF and so on. And we have tested everything, okay? And so, yeah, this is an example. We have tested superparameterized CFS, and we have tested this, Bolium has elaborated the multi-cloud model and so on. So what it comes to my mind is that, so these are the possibilities based on all Arakawa, Dave, and so on and so forth. One is MMF, which definitely we cannot use for operations. We can use it for learning and understanding. There is another possibility that we learn from SCM and go to GCM. This is feasible. This is very consistent scientifically. This is the most plausible path, but it's time taking. Physics suit, changing the physics suit, this is most popular. We are also doing, many people are doing. And this is relatively easy. And then there's a dynamic suit. It's time taking. So out of these 4, this is partly, what people tries, and you can get some paper, your student can get PhD. But others, you cannot tell your student to develop a dynamical suit. So these are the challenges. Okay, so I will skip some of these things. So this is, SPCFS. When we use it, we find the MJO and the power improves. Among these things, CFS V2 is completely odd man out. You can see now this is matching better, but we cannot use it. I mean, this cannot give any, help to our operational forecast. This is one model, one approach with Han and Pan. Morning, Lucas was mentioning Han and Pan to 2011, and they revised simplified arc-of which has now been used in our ESM as well. And in this model, we found that you can see this double ITCZ has reduced a lot, and this dry bias also has improved. But this has actually happened due to improvement only in convective rain, not in the large scale or stratiform rain. So we tried with Dr. J. Young Han of KIAPS, of Dr. Hong's group, and using their fractional cloudiness methodology, this paper elaborates that, and we improve even the forecast. We improve the CFS. We also improve the GFS. And we find that, the chiclet diagram also improves. So this is one way. And we also find that the cloud radiative forcing, this is the old SAS, and this is the this revised SAS, and this is the observations. You can easily make out that this two goes better than this one. So other than this, there are other hypotheses, like Jiang suggested one hypothesis, which was further put forward by Frank Lee of JPL. And they said that the model cloud should look like this, okay? We tried that to do in our CFS as well as in GFS. And we also, this is a cartoon, so by using this WSM6, what we found is that while the control CFS is not able to, the cloud or the cloud hydrometry is not in phase with the rainfall, when you improve the microphysics along with an improved convections, there is a coherence in the rainfall and the clouds, okay? So that improves, and many other things. This is the cloud hydrometry, I think Tau was showing, and we are here. Not exact, but some extent improved. This is CFS, this is CloudSat. So there is definitely some improvement. This is the low cloud, and this is the transitions, okay, over the southern oceans, which is completely missing in the and this is a recent paper by Monsoon Mission. All of you can see it. And when this model, with all these revised SAS and new microphysics we ran, a reforecast is run. This is the high resolution operational CFS stands here, and this is standing here, although it is T126, but it competes almost with the high resolution operational model in terms of variability and also correlation. And we find that eastward propagation also improves, northward propagation improves. So there are many improvements. Yes, even the synoptic variance has improved now. Okay, I will skip some of this. Yeah, so this is the new development which we are working. We are thankful to Peter and Nils. This already, all ECMWF suits are in this coordinate at present, which is cubic octahedral, and it has lots of advantages. What we have done is that because NCEP is going to FB3, and I have to remember the central block, okay, funding agency, boss, etc. They will not like, we already, a lot of time and resource have been invested for CFS, so we cannot again follow FB3. So we have to improve this existing CFS or GFS. So we thought, let us try TCO. We will be still in spectral, but we can, from Gaussian linear, we will go to cubic octahedral. When we go, and so we ran, we have just completed, just before this conference. So we have run TCO 765. TCO 765 is actually equivalent to T1534. So what do we expect? We do not expect any drastic improvement. At the same time, we should not get any surprises. We should not get the forecast that we are getting in T1534 is getting deteriorated in TCO 765. And this is for June 2019. these observations. This is day, I think day 2. Okay, this is day 3, day 4. Okay, and you can see they look very same, and we expect them to look same. Okay, this is day 5. Again, this is July. Okay, and it looks same. So, and last few slides, I will finish in 2 minutes. So this is one of the way which I told that, starting from single column model, use various observational experiment data and correct, mostly for students, correct the physics of the model and then put it in the 3-dimensional box. So we are trying that, and when we use the TWPI's data in GFS single column model, we find that, it's really suffering from very low moisture in the lower level, and also in the, QV is very, very less. So we need to improve this, and this is the another thing which is coming as the breaking the deadlock, which is deep learning or machine learning, and this is a new way we are trying this. What we are doing is we have this SPCFS, and we have saved the tendency of temperature and moisture of from the CRMs. We are using those to train these deep layers of this network. And what is coming out at the end out of this deep layer is actually used in GCM. And in this process, I get rid of that quasi-equilibrium. I get rid of all these other constraints. But I take advantage of the CRMs, okay, which are supposed to resolve the clouds. And so where we are and where we want to go. So we are here today. Resolution is T1534. Vertical levels is 64, and this unfortunately remains same for all the CFS, right from T62, T126, T382, and T1534. Vertical level remains 64. And we are presently running modified revised SAS and also revised SAS in scale aware. We have added this, and we are using STTP, okay? And present scale, as you have seen, it is 3 to 5 days. And where we want to go is here. We want to increase the resolution 5 to 6 kilometer using cubic spectrahedral. Vertical level, we would like to increase to 91. We would like to use convection stochastic scale and also a unified club. We would like to change from STTP to SPPT, and we would like to enhance the skill to 7 days. And then this version can actually be used seamlessly to other. Yeah, I'll stop.
Thank you, Partha. So, very nice talk. Any questions or comments? Okay.
Nice talk, Partha. So, I think there's a temptation when we see systematic errors in convective precipitation to blame the convection scheme. After all, a lot of the rainfall in the tropics is convection, but there's a long history of us finding out sometimes otherwise. For example, in the 90s, the European Center model was not generating a Walker circulation, which is a rather severe error. And they kept messing around with the convection scheme, not getting anywhere, and they finally discovered the problem was that when the winds dropped in the Western Pacific, as they often do, to near zero at the surface, their surface fluxes went to zero. And they sort of put a minimum in the wind and the surface fluxes, and the problem went away. Maybe today the problem is, and this is going back to Graham Stevens' talk, that we're not paying attention to the coupling of convection and high clouds, and it causes all kinds of problems that might not be obvious that that's the reason, but I'm wondering if we should be paying more attention to that problem.
Yes, true. I mean, there cannot be anything more than true what you're saying. We need to couple more physically, I think what Graham also was insisting, and more realistically, that's not happening. We are representing things per our wish and the way we want, not the way the nature wants. So, but as you told, that issue of ECMWF took how much time to resolve? So we really do not know. We have to work. All the students, everyone, the whole community should work to resolve this. But that is the only way. I mean, yeah. Sure. Yeah, Peter.
Very well done. In the first slides, you really summarized all the pressures and problems we have. And
do you like it?
I liked it very much. Yes.
Thank you.
You should keep that. And just another positive note for the octahedral. Actually, are not the same. They are better. If you look at the precipitation over Indonesia over orography, this is actually where you should improve. It's much smoother. You go before the slide before, where this is very noisy.
Mm-hmm.
The linear grid, because it is less accurate projection from the 2 point to the spectrum, and that's where you expect the improvement.
True.
So you can be happy.
Roberto.
Yeah, going back also, first of all, thanks for a very nice talk. Going back to your first slide, I think with expectations, we should really communicate that forecast will always have an uncertainty. That's it. We will never ever, even if they give us 100 times or 1,000 times faster computer, get rid of the uncertainty. And we need to educate people about this and to educate people to take decisions using probabilities. Probability can be translated in different ways according to the user. We need to work with the users so that they can use it, but there is no way out of this. So I think we need to do this for sure. And then, so this is a comment. My question is about some of the results that you showed. I mean, a lot of the results you showed were mainly based on CFS. I wonder how general they are. Mm-hmm. Because you painted a picture that, if I remember now the results of the European Center, it doesn't seem so bleak to me. It seems that we are not, no, it's a bit better than how you painted it. So I wonder whether...
I could have painted it in a different way, but, you know, I told the truth. And these are all published in paper. I mean, I have not painted anything specially for this conference. I didn't have any time. So all these figures are available in published papers. And if you put them in perspective, it really looks like this. But there are ways by which I can paint it in a different way so that it looks really very beautiful. Like, you know, the GFS I showed, if I don't show all your 2019 and I show only this skill score and the other the retrospect time series skill, then picture becomes different. But the fact of the matter is, there is an issue, okay, and we need not hide it. If ECMWF has overcome this issue, this is a lesson, we should learn it. We should learn it from you, how you have done it, and then we should, as Kerry and Graham has already suggested, we should go into the process, revisit, and try to resolve it. There is no other shortcuts. But coming back to your educating people, as I told in the first slide, the box 2 and box 3, they don't have time. They are running out of time. So if you tell someone that I will educate you about the probability or the uncertainty and so on, you know, it's a big challenge.
Yes, but we need to say that there is always going to be uncertainty in whatever comes out of any forecast or any climate projection. Right? That's it. We can try to reduce it. We can try to make it as small as possible, but it will never go away. We will never get the right answer, even at 1 hour before the event.
See, as you told, ECMW started this ensemble forecasting since 1992. We have started since 2018. Right? So I mean, these high resolutions, yeah. So I think down the line, definitely the last mile will be educated and the forecast will be valued. Yes, Ken.
Part I was thinking when you said it, the same thing that Roberta said. The other thought I had about ensembles, because you showed some cases where all the members of the ensemble failed in the same way. That, of course, an ensemble is really important to handle the uncertainty, but it is only as good as the model that's in it. If the model can't represent an extreme,
True.
then the ensemble won't predict the extreme even at the lowest probability.
True.
So the ensemble fundamentally has to have a good climatology in the model of a phenomenon in order to be able to predict it. So
True.
all the bias issues and things in the models will apply to the ensemble as well.
I agree.
And in terms of the picture you paint, I think it is true for really all the models.
Yes.
We've addressed it over many, many years with incremental changes and improvements. But you're right that many of the long-term biases are very hard to get rid of. I think the thing I was most interested in some ways, you came to right at the very end, your idea of using neural networks, which is, of course, what everybody wants to talk about these days. And we are looking at possibility of using neural network to represent some of the parameterization in the UM. I think ECMWF have tried it in the past and moved away from it again. But it is certainly an interesting idea, and particularly if you can use a cloud resolving model to train something, get the benefit of that high resolution at much cheaper cost. It's a very interesting concept, but it's a long way to go in research.
Thanks. Any other?
Any other questions or comments? Okay.
Jimmy.
No, I want to go back to the issue that we are facing, which is, I mean, I wonder whether we should, we as the centers who have the knowledge and develop these global models and are trying to resolve problems, to do more thoughtful and careful intercomparison. Because if all models get wrong a certain type of phenomena, well, I think we should all sit together and think of, okay, what can be the cause? Because if we are all missing something. And I don't believe that for certain phenomena that we're trying to predict, we need resolution. I don't believe it. For certain things, yes. But there may be other aspects that if we all sit together, comparing how our models behave, we should be able to make progress. And we don't do that. We compare scores, but we never sit and compare how phenomena are simulated in the model. Again, we cannot just look at one event because we will not, but pick 10 similar cases, 20 similar cases, sit all together and try to see how they are simulated. If we are all models fail, well, there is a message there and we can learn something. If some of the models do it consistently better than others, again, we can learn something. So I wonder whether this is something we should think to promote.
Fully agree with you, and this is one of the reason behind organizing this conference, and we organized another conference in 2017, so that we learn from each other, we learn from each other's strength, and we understand each other's weakness, and intercomparison is only the plausible way to do this. I agree.
Now, I want to comment on this from somebody who's outside the weather modeling community pretty much, which is to say that, when I go to meetings like this, but some other things, I often get the impression that there's a competition in modeling centers to outmarket each other and how well the models do.
I don't do
that. So
we
have you violated that rule, thank God. That's why I liked your talk so much. But I think there's a cultural problem here that's universal, that we have to really focus on, in some sense, brag about the failures instead of marketing models and showing how well they're doing. We really have to, I like to think about building special test beds for breaking models. And I don't just mean with all the physics, but where do they blow up? where's all the dirty laundry? Let's get it out there, all right, so we can clean it. And how do we, maybe there's some ideas from people who are in modeling centers about how, whether we should change the culture, and if so, how should we go about doing it?
Sure.
Jimmy
wants to ask
yeah,
one question,
Jimmy.
maybe, yeah.
Yeah, going back to your early problems, the first problems you showed with not getting high intensity rainfall, which seems to be one of the leading problems you have. We know that if you turn off the cumulus scheme, you will get that, and you get too much of those grid point storms. And so there's some middle road there, which I think stochastic physics can get you to if you don't allow the convection to release the instability as soon as it develops at every grid point. If you have some stochastic method like Craig and Plant had, for example, where it selects points to activate the cumulus scheme, even though it may be unstable everywhere, it would allow some of this instability to develop, which appears to be one of the problems you have, where you can get the convection early in the simulation because there's some instability from the analysis, but later the model is never able to develop the instability and then have a quick convection.
True.
And so I think stochastic methods
True.
can allow this kind of thing to happen.
We are testing that in GFS, yeah.
Okay, maybe tomorrow, so maybe last question. Tomorrow we have panel discussion again.
Sure, sure, sure. It is almost becoming like a panel discussion. Sorry for that.
Sorry, I'm a member from outside this community and I'm not a modeler. But there is a I work on the monsoon, and there is a phenomena that Francis mentioned today, equatorial Indian Ocean oscillation. And together ENSO and Equino contribute something like 70% of the variance of Indian monsoon rainfall. So it's an extremely important phenomena, and we looked at models to see the extent to which A, they could simulate Equino, and B, simulate the link between monsoon and Equino. And we did that with this ensembles, set of data that we had with several models. And we found that none of the models get the link right. In fact, they get the reverse sign of the link. Instead of the eastern equatorial Indian Ocean being suppressed, being favorable for the monsoon, almost all the models, it is unfavorable for the monsoon. That is to say, it goes with the eastern equatorial Indian Ocean. In terms of the link, none of the models got it right except for ECMWF. Only ECMWF model in that ensemble run, whatever model they had, actually got the link right. So I'm all for the intercomparison suggested, because there was a time in 80s when none of the people got the monsoon link with ENSO right. And what people did was all the modelers came together, and there was an international program under WMO in which they tried to get simulate 87 and 88 right. 87 as a classic El Nino, 88 as a classic La Nina. And today, every model, whether it is atmospheric or coupled, gets the ENSO signal right. In fact, the problem with the models is that they are slaves of ENSO. They do not at all respond to the equatorial Indian Ocean signals. So I thought that the suggestion of intercomparison is a very valuable one, and in fact goes even outside the parameterization and so on. I think it will be highly worthwhile, again as Kerry said, not to compete, but to collaborate and try and figure out what is it about the equatorial Indian Ocean convection that so many models are getting consistently wrong.
We'll put it in the panel discussion recommendation tomorrow.
Thank you.
Thank you.
So, are there some remote
No,
questions?
nothing.
No? Okay.
I want to leave
so,
now.
Thank you very much. Yeah. Thank you, Professor. So this wraps up the afternoon session, and we would like to thank again the 5 presenters. Yeah.
So thank you, Professor Saito, for this chairing the session, and it was a very lengthy session after lunch. So I would now like to we would like to honor the speakers of this afternoon session by giving a small memento from our IP4. So I request Honorable Chair to do that for us. So I'll call all the speakers. First, Professor Shige-san from Japan. memento is there. Dr. Rajagopal, please come forward. Professor Mohanty, see here. Yes, please, sir. And Dr. Francis, see here. Okay. So our beloved Parthoji, please come forward. Yeah, thank you, Professor Saito, for chairing this wonderful session. Yeah, I'll hand over the mics to the logistic announcement, if any.
Okay, so thank you very much. So we are ending the third day session. So there will be the poster session right now, poster and tea. And for the persons who are staying in Sahaji around 6 p.m., the buses will be start right in front of the Megdut Auditorium.